Alright guys, for this first one we have that Saha, okay, is designing a bridge to cross a river. Now she believes that the weight of the steel needed for building this bridge is approximately this amount. On the other hand, we have the exact weight of the steel needed for the bridge is this amount, okay? And so of course Saha is a little bit off, and because she's a little bit off, there is a, for part A, percentage error in Saha's approximation. So just a quick disclaimer for this whole video, or what I suggest really, is that in order to face any exercise, you first need to identify buzzwords, keywords, key concepts. Okay, so whenever I talk about buzzwords, I'm talking about keywords, key concepts, important words, okay? Important words, important concepts. And so what you're gonna do is that after you identify these, okay, this will be a big hint for the formula booklet, which will then be a big hint for the procedure. Now, some of the buzzwords and keywords and key concepts and etc. are not going to be in the formula booklet, and you're just going to jump straight to the procedure, okay? But for a lot of these, you guys, there is going to be a tool you can identify within the formula booklet. And so what I highly suggest is to get familiar with these, which allows you to get familiar with that, which allows you to get familiar with that. Okay, so this is just the sort of mentality that you want to embark upon when facing these exercises. And so the level that I need you to reach is at the moment that you read percentage error, you remember that it's somewhere in your formula booklet. You don't have to know it by memory, but you do have to identify it. It should ring a bell within your brain. So you read percentage error and you go ahead and open up the formula booklet and you say, I know you're in here and I'm going to find you. So you start looking for it and eventually you find percentage error. Will you look at that? How friendly. So our good old friend percentage error, how does it work? Yes, the formula looks kind of nasty, but let's go piece by piece. On the one hand, you have VA. Okay, so VA, as you can see here, is the approximate value. On the other hand, you have VE on the numerator and denominator, which is going to be the exact value. And last but not least, you have these two fancy looking sticks, which no, are not a parentheses, they're actually absolute value. So these are called absolute value. Why do you use absolute value? Why is it useful in the first place? The absolute value of 3 is 3. The absolute value of -3 is 3. Guys, what's happening here? Absolute value makes whatever is inside positive. Okay, whatever's inside now turns positive. So absolute value of -x is going to be x. Absolute value of, I don't know, -7 is going to be 7. So all it really does is makes whatever's inside positive. So keep that in mind, you'll be fine. And the other small detail I missed is that you do multiply by 100% in order to go from decimal to percent. Okay, but I'll talk about that in a second. For now, don't worry about it. For now, you should really just focus that A. On the first place, this is a buzzword. And on the second place, it's in your formula booklet. So keep it in mind. ¿Vale? Let's go ahead and apply this formula. So on the one hand, you have the approximate value up here. So this is going to be your VA. And on the other hand, you have your exact value, which is right here. So this is going to be your exact. And if you follow the formula from the formula booklet, you can see that it's going to be, for part A, it's going to be absolute value of first the VA, so 53,632,000, minus the exact value, right? So the exact value is going to be 55,625,000 divided by the exact value again. Okay, so here I'm only following the formula from the formula booklet. There it is. See? And it multiplies by 100%. You'll see why in a second. See? So if you go ahead and open up your calculator, trusty rusty calculator, you can put a fraction just to make this more friendly. See? Like in theory, you could, do something like this. Or you can go ahead and put up a fraction using alpha, y equals, and these are all fractions. See, so you can put the first one, and here it's a lot more friendly, ¿cierto? It's a lot more friendly for plugging in, I mean. So from here, I'm going to go ahead and plug in everything I need, which is going to be the absolute value first, ¿cierto? So here goes the absolute value first. Make sure you put the right amount of zeros, double check, minus the exact value, which is right there. And here I divide by the exact value again, see? Now, two things happen here. On the first place, a decimal comes out, see? And on the second place, there's a negative value. And so if you want to be really rigorous on your approach, what just happened is that now you have the absolute value of negative 0.0358. And you still have a times 100% outside, see? And so what happens now is that the absolute value sort of applies, and this is now going to turn positive. Because as I told you, absolute value, all it does is that makes whatever's inside positive, right? 0.0358 times 100%. Also, I didn't mention earlier, but why do we want to make whatever's inside positive? It's because in the context of percentage error, you don't care about being like 10% above or 10% below. You only care about how off you are. So that's why we apply absolute value in this context. We just want to know by how much we're off. See, we don't care if we're above or below. We just want to know by how much we're off. So there we go. We put it as a positive value, and this is a decimal. See? But because we want to leave it as a percent, because we're talking about percentage error, whenever you want to go from decimal to percent, all you have to do is multiply by 100. And the other way is the same. If you want to go from a decimal, from a percent to a decimal, you actually divide by 100. So look at that. You just learned how to go from decimal to percent and from percent to decimal. So you take this decimal, you multiply it by, well, first of all, you make it positive. See? So times -1 will do the trick. And then we're going to multiply it by 100. So lo and behold, now it's as a percent. The answer for part A is going to be 3.58. 3.58%. Okay? And just as a disclaimer, I should have mentioned it earlier, but I am leaving it in significant figures. My final answer, I mean the long version, is 3.58 2921. 292135. So you can leave it as this long sort of version, or you can get comfortable with significant figures. Count 1, 2, 3. Do you round it up or keep it the same? You keep it the same, so you can just leave it as 3.58%. Okay. The answer on the left is significant figures. The answer on the right is the long version. Either of them works. Do what you want. I left it like that. You can leave it like this. Nobody cares. Do whatever works for you. Okay? And notice you have a whole method point for using the percentage error formula. So this approach here, I highly suggest it because you're going to net all those method points, which show up a lot during the test. See, a lot of times the method points is really just identifying the right formula. And what has a bunch of formulas? The formula booklet. Okay, so that is the approach that I suggest. Do what you want. That's my suggestion. See? Anyways, enough blah blah. That is for part A. For part B, we have that SA has this design is used to build 5 identical bridges. And so for part BI, you need to find the weight of steel needed for these 5 bridges to 3 significant figures. Now, in order to be accurate, all we really need to do is use the exact weight for the steel needed for these bridges. So all you're really gonna have to do for part BI, which is fairly simple, is take the exact value, which is 55, 625, 000, and that is for one bridge. See? So that is for one bridge. For 5 bridges, you multiply by 5. Pretty straightforward. So you take this number, 55625,000 times 5. That is the exact amount needed for 5 bridges. So your answer is going to be 27, 8125, whoops, 8125, and then a bunch of zeros, I think, and then a bunch of zeros. So that is your answer. See? Let me just double check because it looks a little weird. 27, 8125, 000, 55625, 000. Yeah, okay, looks good. The method is probably correct. So this is your answer for the amount of steel needed. See? But there's a disclaimer for part BI because the IB loves to put disclaimers. So the disclaimer here is that you need to answer to 3 significant figures. So unfortunately, this is something you have to learn, but hey, that's the point, learning in math. See? So let's get to it. How did you express significant figures here? What we're used to is expressing it with decimals, okay, which is much more friendly. It's what we're used to, etc. But in this case, you have a big number. So how do you express the decimal points? The significant figures for a big number. For a big number, the idea is still going to be the same. You read it from left to right. And so if you read it from left to right, you count 1, 2, 3, and ask yourself, do you round it up or keep it the same? Because it's a 1 next to it, you keep it the same. If it were 5 or above, you round it up. So from here, in significant figures, it actually ends up as 278,000, 000, 000, or million, sorry, right? Kilograms. And so there is your answer in significant figures. All that's going to happen is that all these values ended up as 0. See? That's pretty much it. I can't explain it any more than that. It's just significant figures with big numbers. We check our answer here just so that we all feel comfortable. And there it is. See? So for part BI, really just be careful with significant figures. Get used to using it with big numbers. See? So you just go ahead, count 1, 2, 3, see if you round it up or keep it the same, and the rest of it is going to end up as a bunch of zeros. Lo and behold, that is part BI. For part B double I, we need to write down the answer from part BI in this form. And just in case, if you want to Google it, okay, this is scientific notation. And I know there's a bunch of stuff happening here, but on the one hand, let's go piece by piece. They ask for A to be between 1 and 10. This is pretty standard for scientific notation. And they also ask for K to pertain to the values, to the, I can't find the word right now, but to the group of Z. And Z, you guys, is integers. What the heck are integers? Integers are whole numbers that are negative. So all your integers, okay, is going to be -3, -2, -1, 0, 1, 2, 3. Okay, those are the integers that you're going to be using in this context. Yeah? That's all it's really saying. K has to be an integer. Not it? Now, all it's really asking for is scientific notation, and it's actually a classic for IB. They really like to do this. Now, that being said, the other thing I can sort of point out is that part BI, whenever you have something with 2 parts, I and double I, see? Almost always, in my experience, part BI is heavily related to part B double I. And why do I mention this? It can be a very big hint to know what to do moving forward. See? In this case, it's very literal. It's like, yo, whatever you did in part BI, apply it now. See? But in some other context, maybe in some other exercise, when there is more than one part to it, maybe they're related. Maybe they can help you identify how to move forward. Okay? So that kind of hint is important to keep in mind because sometimes it can really save you. For example, here, see? Maybe you need to sketch the graph before finding the x-coordinate or to find it faster or whatever, see? So just keep it in mind, it doesn't always apply in this test. It doesn't really apply much at all, But in other tests, I've seen it be very, very useful. Okay, so any exercise that has parts to it, they're usually heavily related. It can be a big, big hint on how to move forward. See? So all you have to do in this part is leave our answer in part BI in scientific notation. So how the heck do you express this in scientific notation? So technically, and this is what I need you to understand initially, okay? If you take this number, the 278,000,000, and you divide it by, I don't know, 100, what just happened? You went from having 6 zeros to having 4. And that's because when you divide by 100, you got rid of, how many zeros does 100 have? It has 2. So, that's a way that you made the number sort of smaller. Now, take a moment and think about it. How can you also express 100? You can express 100 as 10 squared. Oh, that's interesting. That's very interesting. And so if you keep going like this, eventually, you can try to reach a number that is between 1 and 10. Now, which number is between 1 and 10 here? Is it 78? No. Is it 27? Neither. But you can identify, and this is huge, this is a big first step, 2.7. So technically, you can take 2.7, or actually, you can take 2.78, better said. You can take 2.78, multiply it a bunch of times, and end up with the same number. So let's see how that works. You can take 2.78, and if you multiply by 100, okay, you moved a little bit, but not enough. If you take 2.78 and multiply by, let's say, 1,000, well, now you're getting closer. And so eventually you're going to realize, how many zeros do I need to put? Well, how many times are you moving? You move once, twice, 3 times, 4 times, 5 times, 6, 7, 8. So if you take 2.78 and you multiply by 8 zeros, you end up with the same number. Now that doesn't look exactly pretty to put all those zeros, right? But I can express this as 10 to the power of all those zeros. And how many zeros was it? It was 8 zeros. There is your scientific notation. So all you really need to do is first identify your value of A, which in this case is 2.78, and then identify how many times you have to move the decimal place from here. And what we counted and found out is that you moved it 8 times. So that is how you identify that the answer is 2.78 times 10 to the power of 8. So all you really needed to do or review was how the scientific notation works. See, a lot of it has to do with identifying A correctly. Initially, I did the mistake of identifying 2.7, and that's not good enough, because if you use 2.7 here, what you actually end up with is something very similar to the answer, but without the 8. And you need the 8 in this case. You need it, because it's right there. So, I'm glad I made that mistake, because then we can review it together. For part B double I, that is my answer. We're all happy. We double checked here. There we go. Now, if we move on to number 2, we have that our good old friend Angel has 520 in his savings account. Okay, there's going to be a lot of context here. Okay, but a lot of this context is actually a big hint for the buzzwords needed to use for this exercise. Remember, whichever buzzword or keyword concept that you use will lead us to the formal booklet and will lead us to the procedure. Sometimes it will lead us straight to the procedure and the tools will not be in the formal booklet. Let's see what happens in this case. So, we have $520 in his savings account, and Angel considers investing the money for 5 years with a bank. The bank offers an annual interest rate of 1.2% compounded quarterly. And so for part A, we need to calculate the amount of money Angel would have at the end of 5 years. So at the end of 5 years with the bank. Give your answer correct to 2 decimal places. Important step there, don't forget it. So the biggest sort of buzzword or hint that should be happening here is that the moment you read something like compounded quarterly, you're talking about compound interest. And so from here, you guys, the big hint is that because you're talking about compound interest, you can go to the form booklet, search for compound interest, and here it is. And so as you can see, you can simply use this formula and get away with it. See? Now this formula has a lot to it, but plug in this stuff piece by piece and everything will be fine. There's two types of exercises that you can face um, with these compound interest problems. See? You could have a version with PMT, or you can have a version without PMT. And what I really need you to understand is that if it's with PMT, you have to use the calculator. And if it's without PMT, you can use the calculator or the formula booklet. See? So if it's without PMT, you can use this guy. If it's with PMT, you have to use a calculator in the finance app. Finance app. I should have put that parentheses earlier. The calculator in the finance app, which is this guy here. You press apps, the purple button, and go to finance. And TVM solver, see? So you can either use this, or you can just plug in like sort of manually. Okay, they both work. I'm not sure which one I'm gonna use. I think I'll use the one in the calculator just so that, you know, whatever. It's more friendly, I guess. See? Now, I'm talking about PMT. What the heck is PMT? PMT, okay, what is something you're gonna use whenever you have something that is like additional monthly payment. Okay? It's not compounded monthly. It's something that is like an additional sort of payment. And so the context for this could be like, I don't know, Polly buys a car, you know, and so my good old friend Polly bought a car, and in order to pay off the debt more quickly, he puts in an additional monthly payment. Okay? So PMT is additional, which is like an additional in respects to what you're already compounding monthly. Okay, so keep that in mind. PMT is whenever we're talking about something additional. For part A, there is no additional. Okay, for part A, there is no additional. And so here, because there's no additional, I could just use this formula, or I could use the finance app. I'm gonna use the finance app because, I don't know, it's what tends to happen more. See? Now, for the finance app, the annoying part about it is that there's a lot of different methods. See? If you actually go over here, for example, here you have two methods, right? You can use the financial app, but there's a lot of different stuff going on here, right? Or also, you can simply use the formula from the formula booklet. Okay, they both work. Now, the big problem when I try to explain the use of the financial app is that people get confused with what is PYCY, why is it different in this case, and why is it the same in this case? Which strategy should I use? Which one is more convenient? And what I suggest, okay, is sticking to the version where they are both the same. Now notice, the main difference between these two is that, well, yeah, these two things are different, clearly, but why? They're different because of how you express big N. Okay, this N is big N. In this formula over here, you have K times little n. Okay, what am I trying to reach here? The method on the left, okay, if you plug it in like what's on the left, this big N is going to be the same as little n, okay? If you use the method on the right, which is what I suggest, this big N is going to be the same as the formula booklet. It's going to be K times N. That is what I suggest. Because if you use the big N, which is K times N, you can simply leave PY and CY with the same value, okay? And so just, I know that maybe for now it's a little bit confusing. What is K, what is N, what is happening? For now, first of all, I'm going to say use the method on the right, forget what's happening on the left. Your big N is going to be K times N, and these two values down here are going to be K. For me, this is a lot more friendly to remember rather than trying to figure out why PY and CY are different. See? So that is just my approach that I like to suggest. For me, it's easier to remember because if big N is K times N, you can also remember that from the formula booklet more visually. Okay? So let's go piece by piece. See? Big N is K times N. What is K in this context? So K, let me use a different color because there's a lot of stuff going on here. So K is the number of compounding periods per year, while N is the number of years. See? So compounding periods per year, the big hint here is like, if you talk about quarterly, well, how many quarters are there in a year? There's 4. If you're talking about monthly, you would have 12. If you talk about yearly, you would have 1. See? So in this case, because it's compounded quarterly, it's a massive hint for saying that, K is going to be 4. What else do you know? 5 years, N is going to be 5. So, big N, for our approach, ¿cierto? Big N is going to be 5 times 4. Big N is going to be 20. That is why there's a 20 here. See? What else can you identify? Well, the I over here, which is I%, see, it's going to be the interest rate. It literally tells you here it's going to be 1.2%. So that is where that appears. See? So big N, we're going to put it as 20. The percent, it's already as a percent, so all you have to do is do 1.2. PV is your present value. Okay, it's your present value. And if you can see over here in the approach that they suggest, ¿cierto? They put it as positive or negative, right? And this is just a context thing. It depends how you think about it. See? You can think about it as that Angel just lost $520 by putting it in the savings account, or Angel still has 520 and leave it as a positive sort of value. Okay, what I like to do is think about it as Angel losing money initially. So Angel has 520 in the savings account. It went from his pocket to the account, so initially he loses. This is just a mentality thing. You pick your approach. See, so I'm going to put it as negative 520. PMT is going to be 0. FV is actually what we're trying to find because FV is the amount of money that Angel will have at the end of 5 years. See, so FV is actually what we're going to be solving for. PY and CY, as I said, is simply going to be K, and K we said was 4. See? So 4 and 4, bada bim, bada boom. Now, how do you solve from here? You actually have to use the solve button. Where is the solve button? Right above enter in green. So that means you need to press alpha, and enter is going to make you hit the solve button. Now, because you're solving for FV, make sure you press the solve button while standing on FV. Basically, you're asking the calculator, using all these parameters, what should FV be? FV ends up being that amount. And notice it gives it to you in a positive value, which for me makes more sense. For me, it makes more sense because Angel initially lost 520, putting it in the account, and he ends up with 552 or $552. See? So the answer from part A, using all that sort of lengthy approach, is $552.105. 4116, sorry. Now, the disclaimer, because the IB loves disclaimers, is that it needs to be corrected 2 decimal places. So different to significant value, which you would count from left to right, here you have to start from the decimal place. So you count 1, you count 2. Do you round it up or keep it the same? You round it up because it's next to a 5. So for part A, you actually leave it as 552.11. Is it dollars? It's dollars. There it is. See? If we look at the answer, here it is. Bada bim, bada boom. So that is for part A. See? Now, all that analysis didn't matter because for some reason, instead of investing the money, Angel decides to buy a phone. freaking millennials, am I right? Angel decides to buy a phone that costs 520. At the end of 5 years, the phone will have a value of $30. It may be assumed that the depreciation rate per year is constant, and so calculate the annual depreciation rate of the phone. Now, this is a little bit different, see? Notice that here we're not talking about any compounded quarterly, any compounded this, compounded that. We're talking about depreciation, see? So for these sort of compound interest problems, yes, like once you identify that you're talking about compound interest, you gotta talk about if it's PMT or not PMT, and there see if you use the finance app or not, see? But the other sort of type of exercise that can appear is either an appreciation exercise or a depreciation. So if something depreciates, okay, we're talking about an exercise like this one, see? And so for depreciation for part B, what's happening, right, is that like on year 0, ¿cierto? The phone costs 520. On year 1, it costs a little less, then a little less, then a little less, then a little less, then a little less, and on the last year, it's now worth $30. See? And so the exercise you sort of have to do is see by how much is it decreasing each time until it reaches $30. Now, because it is constant, right, that means that it is always multiplying by the same amount. See? And this is it's a very specific approach. See? So this is the kind of thing that it's not in the formula booklet. And so in this case, you're going to be identifying the buzzword of depreciation and going straight to a procedure. There isn't a formula in the formula booklet for this, but there is a formula that you can learn. So the formula that you're going to learn is that technically you take your value, you multiply it by the depreciation, and you have it to the power of the years that happens, and here you're going to have the final value. All right, so this is a sort of formula that you do have to memorize, you do have to remember. So you're going to have the 520, parentheses, 1 minus the depreciation rate to the power of the years will equal the final value. So I know that I changed the formula a little bit, but the reason this happens is the following. Think about it this way. And this is just for context of the formula. See, I'm not going to do the exercise yet. For context of the formula, let's imagine that the depreciation is 5%. See? If you use the one up top, which is like the wrong formula, so my bad, but I'm glad this happened because now I can show you the exercise. If you say that the depreciation is 5%, let's say that it's just for 1 year. See? If the depreciation is 5% and I use the one up top, what you end up with is 520 times 5%, which is 0.05. And what you end up with, if you notice here, you end up with 520 times 0.05. And so that means that in 1 year, you went from $520 to $26. Now, if it were depreciating 5%, you would expect the number to be a little closer to 520, right? But in this case, we literally ended up with 26. So what's happening here? What you actually just did is that you depreciated it by accident by 95%. Okay? So whenever you want to express the depreciation, you actually have to do 1 minus the depreciation rate. If here you do 1 minus, you end up with 1 minus 0.05, which of course is actually going to be the same as 520 times 0.95, right? And so that makes more sense. There we have a depreciation rate of 5%. My number is much closer to 520. See? So be careful about that. It's a classic mistake. The same for when it's growing. Okay, if it's growing, you gotta do 1 plus your amount, right? Same idea. See? So in this context, we're gonna apply the formula that is on the bottom. Now that we understand how it works, it's a lot more friendly. So we're gonna have 520 times 1 minus, and here we need to calculate the annual depreciation. So of course we're going to have 1 minus x to the power of, well, we're saying it's 5 years. See? So 5 years is going to equal my final value, which we said was 30. Now you might be thinking, damn, how the heck do you solve this? There's a couple different ways, and the main issue here is that you have 1 minus x to the power of 5, which is crazy hard to solve. No one expects you to do that by hand. I guess you could, but why would you? See? Because we have our calculator, what you can do is something a lot more friendly. You can ask your calculator, if this is y1 and this is y2, when do they intersect? If you express both of them as lines and find where they intersect, that's going to be where they equal each other. And wherever they equal each other is going to be the x value that you need. So let's see how that actually works. Go to y equals, and this is something you can always use, by the way. Whenever you have an equal sign and one value of x you need to find, you can just pop it into your calculator. It might take a little bit longer to solve, but it's going to work. So 520 parentheses 1 minus x to the power of 5 has to equal 30. So there's my y1, there's my y2. Go ahead and find the intersect. So calc, so second calc, right? I mean second trace. So hit calc, go to intersect, see what happens. Well, the first thing that happened is that only one of my lines appears. So think about context-wise, how can I make the other number appear? So this curvy sort of line has to be y1 because y2 is 30, so it's going to be a straight line. So let's go to window and let's try to make that straight line appear. So if I make my y max, for example, 40, I know it's going to appear barely, right? I don't care about negative values for y because we are talking about a because y equals 30. I need to see the intersect. It's not going to be at a negative value for y. It might be for a negative value for x. This is probably fine. Let's go ahead and graph it. See? So now I should be able to see my y2, and it shows up right there. So now, if you find the intersect of that, the first curve we check is the blue line, so we're good there. The second curve is the red one, and then we have a guess. Now guess is really whenever you have more than one intersect. Here we have just one, so just pop it near it. That is the value it gave me. So let's get good at interpreting this. So this gave me 0.43477, 0.43477 comma 30. So as you can see, my y2 is right here. Well, for my y1, or really my x value, is right there. So that is how you interpret the calc intersect trick. I used it because I had 1 minus x to the power of 5, which is very hard to solve. See? So the calc intersect trick is something that always works. And so for this context, you would say that the annual depreciation rate of the phone is going to be 0.43477 to 1. Or you can leave it, I guess, context-wise as a percent. It would be 43 point significant figures, you would leave it as 5%. See? So that is our answer for part B. Let's see how they have it over here. 43.5%. See, so as you can see, there is the same sort of formula that I used. You could have done it with the finance app. See, you could have done it with the finance app. I guess it also would have worked. But for me, the depreciation rate is much more friendly to think about it like this. Okay, this is a classic formula. It always appears. You can use it for depreciation or appreciation. I'd rather show the depreciation appreciation with this and the compound interest with the finance app. See? So both approaches work. That's the one I employed. I hope it helped. That is for number 2. All right, guys. So for the third one, we have that in a school, 200 students solved a problem in a mathematics competition, the best kind of competition. Let's be honest. Their times to solve the problem were recorded and the following cumulative frequency graph was produced. So the big word here is, well, of course, cumulative frequency graph, but the key word I would say is cumulative frequency. What the heck is that? So here's our graph. I'm going to explain it in a second. And as we can see, it's only parts A and B, needing to find the median, a bunch of stuff. See? So for part A, you're going to find the median, the lower quartile, the upper quartile, the interquartile range. And for part B, we're going to find whether it's an outlier or not. Okay, and just for now, quick heads up, the outlier is associated to the interquartile range. That is the introduction to this problem. Now, before delving into the graph, let's first try to understand what they're looking for in terms of what do they mean by quartile, what do they mean by median, upper quartile, etc. So a lot of times in statistics, these keywords help us understand our distributions better or our data better. So the best way for me to explain median time, lower quartile, and all that stuff is using a box and whisker. Okay, and this is just for the intuition of how a box and whisker plot works. And so in a box and whisker plot, you will probably remember that it looks something like this. Boom, 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 and then I don't know, boom, boom, okay? So what's happening here? Here in this box and whisker, on your x-axis, okay, you have like your data. So if this were like, I don't know, days of the week, or actually coffees drank per week. So coffees drank per week. Okay, and you're evaluating different students, whatever, etc. So over here we can have, I don't know, 3 coffees drank per week. Here we can have, I don't know, 4. This can be 5. Here we have a big jump over to like 7, and then over here's 8. Okay, I'm just making these numbers up. The important part is the visual part. So the box and whisker plot, when it looks like this, over here you have what we call the minimum. So of the students that I'm making the survey, they at least drink 3 coffees per week. Over here's Q1, which I'll explain in a second. Over here is Q2, which is the same as the median. Okay, and then this stick over here is going to be Q3, and over here is going to be the maximum. Now, what the heck is Q1, Q2, Q3? Well, Q1 is actually going to be the lower quartile. The upper quartile is going to be Q3, and the median time, which is right down the middle, that's why it's median, Q2, let's remember it's going to be for middle, okay? Now, because Q2 is right at the middle of my data, okay, because Q2 is right at the middle of my data, I can also think about it as like you are 50% like through your data, right? In terms of lower quartile, well, look at the word quart. So when something comes in quarts, well, how many quarts do you need to make a whole? You need 4 of them. So Q1, okay, so you have 4 quartiles in order to reach like your maximum, is what I'm trying to tell you, because you need 4 quarts in order to have a whole, cierto? So your Q1, because it's the first one, it's going to be 25% of your data. Upper quartile is going to be 75% of your data. Okay, and this I think is a lot friendlier to see in the box and whisker. That is why I drew it. So basically, from your minimum, and this is the key idea, okay, from the minimum to Q1, you have 25% of your data. From Q1 to Q2, you also have 25% of your data. From Q2 to Q3, you also have 25% of your data. And from Q3 to max, you also have 25% of your data. The point is the following. If you're looking at the upper quartile range, which is right here, well, in order to reach it, you need to have passed through this 25, this 25, this 25. You add all of those together, you get that 75%. Okay, so a lot of this has to do with sort of like proportions in terms of where you're standing in your data. Quartiles, think about them as percents. Okay, one quartile is going to be 25%. Depending on the quartile that we're talking about, it can be 25, it can be 50, it can be 75. Okay, so With that being said, and understanding the context a little bit better, we can now jump into part A. So, we have the intuition of the box and whisker, how it looks visually. We're going to employ the same idea over to the cumulative frequency graph. Okay, so down below, and this is the main difference, down below, okay, like the first student, the second student is somewhere in between in here. Okay, you're not sure where. You actually, it's hard to know. See, but you know that the first couple students are, I mean, yeah, the first couple students would be around here. See, if you put them in order, blah, 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 etc. In the cumulative frequency, it is much more detailed, okay? Because here, all you know is that the first 25% are there, but over here, you can actually count them one by one. The way cumulative frequency works is that it accumulates itself. That's why it's cumulative frequency. And so here, they say it's 200 students, right? And so where are the 200 students here? Right there. And so 200 students, as you can see, if you draw a straight line over there, you reach the end of your data. Ah, look at that. And so you can actually count each student. I mean, you can literally say, yo, student number 25, how much time did he take to solve this problem in a mathematics competition? And so student number 25, okay, notice the language I'm using. Student number 25 spent, how much time? They spent 25. Spent 25 seconds solving a problem in a mathematics competition. And this is very different, and this is the main idea. This is like the hard part I need you to catch, okay? This is student number 25. I'm sorry, this is student number 25, see? But what if I'm asking for this student at quartile 1, which is actually what they're asking for this part here, see? They want you to use the graph to find the lower quartile. In other words, they're trying to ask for the person standing at Q1, which is the person that is 25% through your data. Okay, 25% through your data, what is that? See, so the student at Q1 is the student which is in the first 25% of your data, but right on that 25%, see? And so if you have 200 students, well, what is 25% of 200? Essentially, all you have to do is take 200 and multiply by 25%. Now, it's kind of hard to multiply by a percent here, so what we do is that we pass from percent to decimal. And this is going to be 200 times 0.25, which will give me 50. So, with that information here, I can identify that the student at Q1, which is the student in the first 25% of your data, is student number 50. So at student number 50, we have our Q1 because student number 50 is on 25% of my data because 200 times 25% gives me that 50. Now, I might have gone a little bit quick there. Let me explain how the 0.25 appeared in the first place. You guys, when you are passing from percent to decimal, I feel like it's more intuitive. I put it with a couple examples. See, so I highly suggest you remember these three values: 100%, 50%, and 5%. If you remember how to pass these percents to a decimal, you're gonna catch like the pattern that goes behind it. See, so the first important thing is that 100% in decimals is going to be 1.00. 50% is going to be 0.50, while 5% is 0.05. So what I suggest is memorize like this small sort of table for passing from percent to decimal, and then you can use this for any example. See, if you're ever looking for, I don't know, 27%, you just follow the pattern of, okay, basically you just gotta put the decimal 2 points in front, see? So if here you have the decimal for 50%, you're gonna go 1, 2, and you end up there, see? So this would be 0.27. If you're ever looking for 0.2%, this is a little bit trickier, but eventually if you think about it for long enough, you will discover it's 0.0002. Let me just double check that real quick. Da, da, da. So that's 2%. Sorry, it would be, it's a little bit tricky, happens to all of us, 0.002. See? So basically, memorizing this table can really help you to understand how to pass from a percent to a decimal. The other thing I can tell you is that technically you just divide by 100. See, if you take any of these values, for example, the 100, and you divide by 100, you end up with 1. If you take the 50, and you divide by 100, there you end up with a decimal, 0.5, same as 0.50. If you take the 5% and divide by 100, there you end up with a 0.05 as a decimal. So here are the 3 examples of this table. You can also memorize that you divide by 100. Anyways, that was just a little bit of blah blah because I know some people probably are confused on how this happened. Now you know. And from here it should be smooth sailing because now that we identified how to understand these sort of percents and proportions, we know that 50 students is 25% of my data. So over here, and just to like, I guess, remember, I suppose, I can put that this is Q1, okay? So this is Q1, and Q1 is going to be 32. On the other hand, and because we need everything, I'm just going to fill it in, the median time is going to be my Q2, as I mentioned here, right? It's right the middle of my data. If I have 200 students, the student at the middle is student number 100. So over here, I have student number 100. Then I go down from there, and this will be my Q2, which is the same as the median. And the value of that is 38. And then Q3, well, let's find out. So Q3 would have to be 200 because I have 200 students times 75%, right? So 200 times 75% is the same as 200 converting to a decimal times 0.75. See? So that will give me 0.75, bada bing, bada boom, 150. All right, cool. So at 150, we have our boom. We have the value we needed. So here we have Q3. At 150 is going to be at 42. See? So using all of this, you can quickly answer that the median time has to be 38, my Q2. The lower quartile has to be 32. And the upper quartile has to be 42. Right? So this, like once you understand that, you can read any graph. Okay, so the main ideas which I think are important is on the one hand, be careful with your total. Here we had 200 students, and so for finding 25% of that, you got to do 200 times 25%. A lot of times, instead of 200 students, you have 100. So it's much easier because 25% of 100 is student number 25. It's very straightforward when you have 100 as a total. But when you have 200 as a total, 300, 400, or something that's not 100 basically, 25% of it gets a little bit trickier. Okay, so keep in mind the magic trick. Take that 200, multiply it by your percent, know how to pass from percents to decimals. All right? Bada bim, bada boom. So, that is for parts A, I, double I, and triple I. And for part A, single I with a single V, part A, part 4, we need the interquartile range. So, you guys, and here's another quick tip that I think would really help for your IB exam. So, the day of the test, and I know I say this a lot, but I just can't hammer it into your brain enough. The day of the test, you will be walking in with a brain, a pen, a pencil, 2 years of experience of this thing called IB, 2 hours of sleep, your graphing calculator, and da 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 da, Your formula booklet. You guys, the formula booklet is going to save you. I promise you it's going to save you. But do not make the mistake of saying, I have the formula booklet, I have all the formulas, I'm good to go. That is not good enough. Okay, you need to know what is inside the formula booklet. You need to be able to identify, and this is why I talk about all these buzzwords, all these keywords that are like the essential concepts of the exercises, and they might be in your formula booklet. For example, in this exercise, yes, we talked about cumulative frequency. That is not in your formula booklet. So sad. Yes, we talked about median time, lower quartile, and all these quartiles, but that is not in your formula booklet. So sad. But the interquartile range is in your formula booklet. And you might not know exactly what it is or how it works and this or that, but this is the kind of concept or thing that you should be able to read and say, I'm pretty sure that's in my formula booklet. I'm not entirely sure, but let's double check. See? So you should be able to read certain words and certain concepts and identify them as they exist in here. That is the kind of stuff and small detail that saves you a lot of time the day of the test. Because if you don't know what's inside your formula booklet, maybe you would have spent time trying to find the lower quartile. Maybe you would have spent time trying to find the upper quartile. Well, instead, you can know what's in it, know what's not, know when to use it, know when not to. And as I said, the interquartile range is essential for the outliers. So it's good to know it's in it. See? And also, it's a classic. It's absolutely a classic for them to ask for an outlier. Know how it works. See? So, in the formula booklet, it helps you for the interquartile range. It does not help you for the outlier. So, the interquartile range, before anything, let's talk about range. See? So, there's two types of like ranges you can have. So, you have the range, which is a classic in statistics. The range is just going to be max minus min, while the interquartile range, well, it's the range, but of the quartiles. So, the interquartile range is going to be the upper minus the lower. See? And this I know because I've done a lot of different videos and exercises involving something like this, but we can go to the formula booklet. Once we identify the buzzword of interquartile range, we can look for it. It will be in statistics and probability, page 9. So we go to page 9. Doop-de-doo. Lo and behold, it's the first one. Interquartile range, Q3 minus Q1. So if you ever forget it, it's in your formula booklet, but it is the sort of concept that you should read and should know. It's somewhere in there. See? So the interquartile range is just Q3 minus Q1. So you will be doing 42 minus 38. Oh, sorry. Q2 minus 32, my bad. So the IQR has to equal 10. See? Just so that we're on the same page, here are the answers. Looks pretty good to me. 38, 32, 42, 10. 38, 32, 42, 10. See? So, part A is complete. Then they tell us that our good old friend Cedric took 14 seconds to solve the problem. And we need to determine whether Cedric's time is an outlier. And notice, this is worth 3 points, and I would say that it's extremely easy 3 points. See? All you need to know for an outlier, and this is an introduction I will give you for now, all you need to know for an outlier is the interquartile range. So that's the first thing I need to explain for the procedure for an outlier. First, get the interquartile range. Secondly, we need to, depending on where the outlier is, apply the following formula. See? And the formula is extremely specific. See? You have an upper bound and a lower bound. Okay? Now, what I should have explained earlier, and I will do now, okay, is that an outlier, like what is an outlier? See, I should have gone through that first. Sorry. So, an outlier is something in your data that like is a little too far out. See? So imagine we go back to the coffee example. See? And one of my biggest values was like 8 coffees. But one of your partners, whatever, drinks 20 coffees per week. You know, we all know someone like that. So someone out there is drinking 20 coffees per week. Is that an outlier or not? Is that so far out that like it doesn't align with your data? Or also maybe someone that drinks 0 coffees per week. That can also be an outlier. And so that is why I put upper bound and lower bound. They are outliers as much as for students solving this problem way too fast and students taking way too long to solve this problem. See? So that is why outliers have upper bounds and lower bounds, whether they are like way above the expected or way below the expected. Okay? So our good old friend Cedric took 14 seconds. And so 14 seconds, as you can see, is right there. Remember that on the bottom is seconds. And so Cedric looks like I mean, this isn't the first student, but it's one of the first students, right? Solve the problem in 14 seconds. And so is this an outlier or not? A lot of people do the mistake, and I will show you now. See, a lot of people do the mistake, and here's Cedric, by the way. Yeah. A lot of people do the mistake that they say, but this point of information is within my data, so why would it be an outlier? Guys, that's the thing. Within your data, you can have outliers. You got to identify them in order to get rid of them, or at the very least, acknowledge them. Okay? So how do you identify which number is an outlier or not? Imagine I made this much easier for you. Write that on the bottom. We have time and seconds. See? Imagine I just invented as a rule. See? Imagine I just invented 20 or lower will be considered an outlier, and 50 or upper will also be identified as an outlier. See? Then it's very easy because you say, okay, so all of these guys are outliers, and all of these guys are outliers. It's much easier when you do that. See? Well, when you do that, you are using the lower bound, which is the guy you put right there, and the upper bound, which is the guy I put up here. See? I mean, more on the right, at 50 and at 20. Now, that was completely arbitrary. I just made it up on the spot. There is an argument for which one should be your lower bound and which one should be your upper bound, which is the formula that I'm about to show you. So how do you define the upper bound? How do you define the lower bound? What you actually do, and let me just double check because it is very specific. Exactly, you see. Yeah, we're good. Yeah, so basically, basically what you will be doing is that for the upper bound, see, you want to see if it's up and beyond. So you will be doing Q3 because it is for the upper bound, the upper quartile. You will be using Q3, upper, 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 Q3 plus 1.5 times the IQR. While for the lower bound, you will be using lower bound, lower quartile, the Q1, Q1, and because you're talking about below, you'll be doing Q1 minus 1.5 times IQR. So those are the two key formulas for identifying these lower and upper bounds. If I apply it up for the upper bound, you end up with 42 plus 1.5 times IQR, which we said was 10. So that ends up as 42 plus 15, if I'm not mistaken. Let me just check my work. Yeah, so the upper bound ends up as 57, while the lower bound will be Q1, which we said was 32, minus 1.5 times the IQR, which we said was 10. So it's going to be 32 minus 15. Let me just check my work anyways. Yeah, there you go, 17. See? So basically, these pink lines that I put for lower and upper bound, it was just to explain the idea, ¿cierto? But your argument for which one is your lower bound was using the formula. And so your lower and upper bound will be at, I'll put it in red. Actually, I'll put it in light green. So the upper bound is 57. So at 57, which is 57, 55, 56, 57. So at 57, which is right there. So here you have 57. This will be the upper bound, right? So anyone to the right of this is considered an outlier. So student number 200 is an outlier. Student number like 190 is also an outlier. Okay, makes sense. See? Well, for the lower bound, you have 17. So 17 over here is just around 19, 18, 17. So here I'm going to put 17, 19, 8, wait, 19, 18, 17. There is my lower bound. See? So anyone to the right of, anyone to the left of the lower bound is an outlier, while anyone to the right of the upper bound is an outlier. Visually, it makes sense. And so is Cedric to the left of my lower bound? Yes, he is. And so Cedric would be defined as an outlier. Now, careful. This is worth 3 points, so you gotta answer carefully. See? One of your points is given to you by using the formula. See? And so that is 1 point, right? Using the formula. The other point is going to be if you mention that Cedric's time is an outlier because they are below my lower bound. See? And then the last point is going to be actually using the mathematical argument, which is basically Cedric's time 14 is less than the lower bound 17. See? And if you look at the answer key over here, you can see that you have one method point, which is the one I mentioned by using the formula. Well, the other point I was mistaking is actually applying the formula. And then this right here, see, this is worth 1 point. So that is 1 point. This is another point, actually, this here, and this is another point. Okay, so those are your 3 points. I mentioned the points thing because it's important to understand how they evaluate you, of course. But more importantly, notice how many points these exercises are worth. That can be a hint of how much you should answer or not. Okay, because this is worth 3 points, one of the points is that you know the formula, the other one is actually using it well, and the last one is concluding. And this is essential for almost any exercise. See? For example, let me find like this is a good one. So here, we just state the conclusion of the test. Okay, it's a chi-squared test. See? And so because it's worth 2 points, I can assure you one of the points is your justification, and the other point is the conclusion. Because you might know the justification, but you might not understand the conclusion. See? So this is for exercise 6. This is just to explain like a test taking strategy. See? So over here, this is your justification, right? That is your justification, but you need to be able to interpret it. See? You need to be able to say, does this mean you reject? Or does it mean that you fail to reject, right? That is the sort of stuff that is important to know. That is the sort of stuff that they're testing you whenever you see that these exercises have more than 1 point behind it. See? So be very aware of that. It can be a big hint for how you should move forward with a lot of these exercises. So that is enough blah blah for me. A little bit of a longer video, but I think it was worth explaining some of this stuff. So take it easy. Just so you know, no one completes an exercise in 14 seconds unless it's a very simple one, so don't feel bad. Yeah, math is hard. See? Take it easy, guys. I'm here to help. I hope it helped. See you around. Alright, you guys. So for number 4, we have that at a running club, Sung Jin conducts a test to determine if there is any association between an athlete's age and their best time taken to run 100 meters. So, depending on their age, are they better or worse off for running 100 meters? 8 athletes are chosen at random and their details are shown below. So just so that we understand, for example, athlete A is 13 years old and ran 100 meters in 13.4 seconds. Athlete E is 19 years old and ran the 100 meters in 12.0 seconds. So that is what this table is telling me. And of course, because it's IB, they tell us that Sungjin decides to calculate probably the nastiest buzzword you are ever going to hear, decides to calculate the Spearman's rank correlation coefficient for his set of data. And we need to complete the table of ranks for part 8. So, before I jump into how to do it, this or that, etc., a little bit of context. Spearman's rank correlation coefficient is a way in which you calculate, there it says, correlation. And so what the heck is correlation in the first place? Correlation is used in the real world because it helps you understand how two variables interact with each other. So for example, let's say that down here on X, I have, I don't know, hours spent studying. And then on Y, I have your grades. Okay, and so clearly, if you spend more hours studying, and all these points are different students, okay, all the students in your class, the more you spend studying, the higher your grade is going to be. And so obviously the conclusion here is the more you study, the higher your grades are. Here, you have what we would call a positive correlation. It's a positive correlation because the more you spend studying, the higher your grade is. The higher X is, the higher your Y is going to be as well. That is a positive correlation. Okay, the higher your X, the higher your Y. There you have a positive correlation. Of course, you have the flip side, which is, you know, maybe the higher your X, the lower your Y. And so you can have an example where you have something like this, where clearly the higher your X, the lower your Y is going to be. And this would actually be a negative correlation. Okay, so correlation is really, it just establishes the relationship between two variables. It's very useful in statistics. And so over here, one of the ways in which you calculate correlation is using Spearman's rank correlation coefficient. Now this is a massive buzzword, and I know it looks nasty, but the most important word, you guys, the most important word is rank. So what you're going to be doing here for part A when you complete the table of ranks is that you will be ranking your data. Quite literally, you will be ranking your data in order. Okay, this is essential, in order. And this table right here, maybe they do it as a reminder, maybe not, already put the age rank of athlete C as 3. And so that means he is the third highest age. And for example, the time rank of athlete G is first. And so the highest time rank is athlete G, which makes sense because if you look up here, right, the equivalent, 17 seconds is the largest amount of seconds. Ah, that makes a little bit more sense, doesn't it? So Spearman's rank correlation coefficient helps you establish some sort of correlation. It might be positive, it might be negative. And in this case, we do it by ranking. So that's the key word, Spearman's rank correlation coefficient. You will be ranking your data in order. So let's go ahead and go piece by piece. Let's start with age. Okay, so with age, well, which athlete has the highest age? There's a 36 over here. It's pretty much a boomer. Just kidding, pretty much a boomer. This would be number 1. See? Which one is the most boomer? The one that's 36 years old. Who's the next boomer? Well, if you go down, or what's below 36, the next high will probably be one of the 20s. It's going to be the 25. So athlete F on 25 is going to be the second oldest. The third oldest is going to be this 22. Ah, I already put the third one right there. So following that logic, you know, you can finish filling in this table. Just to go quickly, the next highest after 22 will be 19. Then it looks like it's going to be 18, then 17, then probably the 13, right? Yeah, 7, and the 11, the 8. We make sure we filled in each square. All good over here. So that is for age. For time, something interesting happens, and it might have been why you clicked on this video. It might be something you're trying to solve yourself. So the highest time is 17 seconds right there. The second highest time follows the same logic as for age. So which one is the second highest after 17? We scan, we scan, we scan. It's going to be athlete B with 14. So here's going to be my second. But for the third one, you notice it's athlete A with 13.4, but also athlete C with 13.4. And so for now, you guys, I need you to understand that athlete A and C, it's not that they're both third, it's not that they're both fourth, it's like they're between the third and the fourth place, okay? And for now, I'm going to leave it like that. I'll come back to how you should actually write it. But now just logically think about it like this. Your highest time was 17 seconds. Your second highest was 14.6. And your third highest is between athlete A and athlete C. So they're both sort of fighting for the third place, the fourth place. So how do you leave it as? For now, let's leave it as between 3 and 4. So that means that the next number that comes along, because it would be the fifth square that I'm filling in, is going to be the fifth highest. So the fifth highest after 13.4 is athlete H with 13.1. So over here we put a 5. Okay, it's very important I do that parentheses because since athlete A and C are between 3 and 4, the next square you fill in has to be 5. The other way you can think about it is that here you filled in one square, here was another square, here was a third square and a fourth square, so the fifth square has to say 5. Okay, it's very important you do that. A lot of people put 4 here and then things don't work out. Okay, so follow that logic. This is the fifth square you fill in, so I'm going to put number 5. Okay, yeah. Let's finish establishing the rest of the table. So after 13.1, the next highest seems like it's athlete D. So I'm going to put a 6 here. Then it's athlete E with 12. Then it's athlete F with 11.8. Now, I can't leave it as between 3 and 4 because the calculator is not going to like that. Because as you can see for part B, you need to calculate Spearman's rank relation coefficient. And so if you plug in between 3 and 4 into your calculator, it's not going to like it. You can't leave it as an interval. So what is between 3 and 4? Between 3 and 4, you have, whoops, spoilers. Between 3 and 4, you have 3.5. And so instead of putting between 3 and 4, you will be simply putting 3.5. All right? So there we completed the table of ranks. Very important, you follow the logic. It will always be the same logic. See? So once you identify your ranking, your data, it's certainly much more friendly. The one thing I've seen that they try to catch you with is this 3.5 thing. Follow the logic. Bear in mind how many squares you filled in. Make sure you put a 5 instead of a 4 here, and you're good to go. Okay? Yeah, so that is for part A. For part B, as I was saying, we need to calculate the Spearman's rank relation coefficient. So, how the heck do you calculate the Spearman's rank correlation coefficient? Obviously, you have to use your calculator because no one knows how to do this by hand. You can, but why would I show you that? So, in your calculator, because we're talking about a statistics problem, you should have established that already, you're going to be pressing the stat button. And you are calculating something. You're not testing something, you are calculating something. So you should be pressing stat and then searching into your calc tab. You know, like which of these should I use? And after scrolling for a bit, hopefully you eventually remember you have to use line reg. Okay, line reg, I need you to associate it to correlation. So I'm actually going to put up here as well. For positive correlation, for negative correlation, I need you to associate it in your brain, associate it to line reg. Okay, line reg helps you find correlations. And so if I go ahead and press line reg, well, what does it ask for? It asks for an X list and it asks for a Y list. And so notice, when this guy online told me that when X goes up and Y goes up means I have a positive correlation, that is why in line reg, they actually ask for an X list and a Y list. It's the two variables that you're comparing to see if they have a positive or negative correlation. So apparently I need to put it into my lists. So where do I find lists? Well, lists is right above the stat button. So actually you can just press stat and then press edit. Here I put them already, but let me erase it and show you how to do it from 0. As you can see, L1 has to be your X. So we're just going to call this our L1. And our time will be our L2. Okay? So if I follow that logic, that age is L1 and time is L2, well, my L1 has to be 7, 6, 3, 5, 4, 4, 2, 8, 1. Okay? And then my line 2 is going to be the next row for the time rank. And so my line 2 is going to be 3.5, 2, 3.5, 6, 7, 8, 1, and 5. There's a very important detail here that we have to embark upon, which is the following. Notice how this 7 up here is associated to the 3.5. Notice how the 6 over there is associated to the 2. You have to be consistent. The 7 with the 3.5, the 6 with the 2, same with the 3 associated to the 3.5. That is essential, you guys. Spearman says rank correlation coefficient. You need to rank your data and then make sure that they are aligned. Okay? So just keep that in mind. It's very important. Yeah? So double check on that. Once you realize it's all good over there, you can go back to stat, go to calc, go to line reg, make sure you put list 1, list 2, and then what the heck is this? See? What is my calculator doing? Do not freak out. Sometimes you can scroll all the way down to calculate, which means you didn't need the stuff in between. If you can press calculate, you didn't need to fill in what's before. Now, just so you know, frequency list is if you ever had a frequency list associated to this table, and store reg EQ helps you store it into your y equals over here if you ever want to graph it. We will never want to graph it because it's a waste of time, with all due respect. I mean, for our interests and purposes, we just need the value of RS. So we're going to go ahead and press calculate. You press calculate, it calculates. That's what a calculator does. And here you have a bunch of stuff. So Spearman's rank correlation coefficient is going to be the R at the bottom. Okay. And before writing down my answer, some of you, I'm sure there's some of you watching this right now, telling themselves, my calculator's glitched. Maybe you already wrote a comment in the comment section, who knows? And you're saying, why doesn't my R value appear? Do I need to update my calculator? What's going on? What's wrong? Nothing's wrong. It's just that you missed a small detail. You have to press mode and make sure that stack diagnostics is on. If stack diagnostics is off and you follow the same procedure, you will come to realize that your R value does not appear. I'll be honest, I'm not sure why this is a thing. I think you should just always leave it on. The more information, the better. Am I not right? So make sure stack diagnostics is on. That should let you see the R value. Okay, so that just a small detail. I'm sure someone out there needed it. There you go. So the R value for part B, so RS, notice you have one that is squared and one that is not squared. Our answer is going to be the one that is not squared. Okay, so clearly it's going to be negative 0.670, 670. If you want to leave it as significant figures, you would be counting 1, 2, 3 after the 0. And this number, do you round it up or keep it the same? You round it up. And so significant figures, if you want, would be negative 0.671. Okay? So that is for part B. For part C, we now need to interpret the value of RS in the context of the question. And so this is a very easy 1 point. It's really like a context question. I mean, it's literally telling us that, see? And I already gave you the tools for it. Remember up here how I told you that a positive correlation is one that, well, it goes up like this, and a negative correlation is one that goes down like that. Well, quick pop quiz. The positive correlation, what slope does it have? You don't know the exact slope, but you know that the slope has to be positive. And the slope down here for negative correlation, what slope does it have? You're not sure, but you know that it has to be negative. Okay? So if you got an R value that is negative, then the slope is negative. Okay? Maybe the other thing that can help you understand this a little bit better is that technically, okay, you have two scenarios, right? Technically, this is x, this is y, this is x, this is y. So you have two scenarios. One scenario is a perfect positive correlation. And your other scenario is a perfect negative correlation. Okay? And in the perfect positive correlation, you have a line that goes like this. And your R value here actually equals 1. Okay? For every x value that you increase here, you increase one y value. So on and so forth. All of these increase by 1. So that would be a perfect positive correlation. For a perfect negative correlation, you can probably already guess it. It would go like this. So your R value, instead of being 1, is actually going to be -1. Okay? So that means my x values here, like for example, an x of 1 will give me a y of -1. An x of 2 will give me a y of -2. So on and so forth. So a perfect negative correlation is R equals -1, while a perfect correlation is R equals 1. So whenever people are wondering, should I call this a strong correlation or a weak correlation? It depends on how close you are to 1. But notice how close you are to +1 or -1. And so the essential thing that you have to mention here is if your correlation is positive or if it's negative. Whether it's weak or strong or etc. is like, it's not as important as mentioning whether it's positive or negative. Okay? So down here, back to reality for part C, interpreting the value of RS, we would be saying that it has a negative correlation, right? If you want to get fancy, you could say it has a relatively strong negative correlation because, well, it's negative. It's closer to -1 than it is to 0, so you can say relatively strong. Okay, fine. But the main point you're going to be getting is by saying it's negative correlation, right? Now, you're not done yet because this is a context question, so you have to connect it to the context of the problem. So in this case, you would actually say, let's remember the context of the problem. Sungjin, what was he doing in the first place? He was comparing athlete's age to the best time taken to run. So you can say that an athlete's age has a relatively strong negative correlation in respect to the time taken to run. Okay? So notice how I started off by writing the essentials. I started off by writing the essential negative correlation. Then just to secure the point, I got kind of fancy by saying the relatively strong part, see? And the other essential, which has to do with context, is that I connected the athlete age to the time taken to run. All right, so that is how you approach these problems. There's always a procedure that you can follow. If you learn all the procedures, you're gonna do just fine. Is that it? Yeah, so for part C, well, I put it up there, so whatever. That is for part C. And last but not least, we have the monster of a problem, part D, which says, suggest a mathematical reason. Damn. Suggest a mathematical reason for why Sungjin may have decided not to use what? Not to use Pearson's product moment correlation coefficient with his data from the original table. Guys, part D is awfully specific. Like, I'll be honest, this is the kind of thing that you either know or don't know, period. Okay? Let me give you a little bit of context. So remember back in the day where I told you what correlation was And I also told you that you associate it to line reg. The thing is, the way you calculate correlation comes in many different ways. There is more than one way to calculate correlation. So one of them is by ranking them in order. And the other one is basically like not ranking. Okay? I know that this is a very fancy buzzword. Pearson's is product moment correlation and Spearman's is rank correlation coefficient. I know this is stuff that is kind of hard to remember. Okay? So what I suggest is remember that for correlation, one of them is ranking in order, while the other one is simply not ranking. All right? And so that's the first thing we need to establish. There's more than one way to get correlation. One of them ranks your data, the other one doesn't. There's probably more tools out there in the statistics world, but for now, we will only focus on these two for our math level. One of them ranks them, the other one doesn't. So what could be a mathematical reason? Well, that's literally one of them, okay? My values have an ordinal sort of approach to them, maybe they don't. Now, there's a lot of reasons you can put here. This is worth only 1 point, and I'd rather just show you the answer key and like take the discussion from there, okay? But I do want to be insistent on the point, be organized in how you think about it, okay? We're talking about correlation. There's two ways to calculate it. One of them, in general, has a ranking associated to it, and the other one doesn't, okay? That's the main idea. Now, there's a couple of other differences that we will embark upon now. You remember it however you want to. These questions are usually worth 1 point, so you don't have to memorize everything I'm about to tell you, but you should memorize or learn one or two of them, okay? Make sure you get that point. It's a free point that you can actually answer without A, B, or C. Okay, A, B, or C are completely associated with each other, but part D is not. Okay, part D you can answer by itself. So it's a free point they can even answer if you're running low on time. That it? So, what are the reasons? Let's jump into it. Here is the answer key. And here it tells you. Okay? Now, for now, don't look here. Okay? Because I feel like it's a lot of information. It can come at you very strongly. I made a mini sort of summary down here. Maybe you want to write it down. Maybe you don't. Up top, I don't know why I put pink on both. Up top, we have Pearson's. Okay, so for Pearson's, these are the main connections, right? Pearson's is if your data is continuous. Spearman if your data is ordinal. So ordinal follows some sort of order. Pearson's if it's continuous. The other thing is that Pearson's is used if you have something that is normally distributed. Spearman's is if it's not normally distributed. And another difference is Pearson's is if you expect a linear relationship. Spearman's is if you have something that's not necessarily a linear relationship. And the biggest thing that I suggest you should remember is that Pearson's has no outliers, while Spearman's can have outliers, okay? Now, the no outliers thing is basically that Pearson's has a lot of troubles with outliers. Like, if you use Pearson's while you have outliers, your R value is going to be pretty flawed, okay? But using Spearman's when you have outliers, it's not as bad, okay? It doesn't affect your result as much. So, those are the main things you can compare. Pearson's is continuous, Spearman is ordinal. Pearson's is normally distributed, Spearman's is not necessarily. Pearson's has a linear relationship, Spearman's is not necessarily. Pearson's has no outliers, Spearman's can have outliers more comfortably. So it's four main differences. Technically, they're written up here. For me, it's a little bit harder to explain it from there. That's why I made the mini summary down below. But you will notice that they touch upon the same thing. Okay? For example, there are outliers or extreme data. So that is why Sungjin might have avoided Pearson's product moment correlation, because since you have outliers and extreme data, Spearman's is going to be better. Okay? Now, I could go through each of these, but I think I'm just going to confuse you. I feel like this is the kind of thing that you should write down over here, right? Or you can draw like a small table, like comparing the two, right? You can put maybe, I don't know, on the one side you have Pearson's, on the other side you can have Spearman's, and then you start writing all the differences. So for Pearson says you have continuous, then on the other side you have ordinal, over here you have normally distributed, on the other you have not normally distributed, etc. See? Linear relationship, not linear relationship, and no outlier, yes outlier. Okay? You can sort of define it however you want. You can remember it however you want. The main message I want to transmit to you is that you don't have to know all the differences. Usually knowing one or two for the day of the test is good enough, since it's usually just worth 1 point. So just giving one of these is good enough. Yeah? A little bit of a longer explanation at the end, but I'm sure it helped someone out there. So that was for you. Ladies and gentlemen, that is for number 4. Alright, you guys, number 5 is pretty easy. You just gotta know one formula, so let's get into it. We have that the following frequency distribution table shows the test grades for a group of students. Now notice, here we have a frequency distribution. Frequency is right here. We will understand that in a second. For this distribution, the mean grade is 4.5. So the mean is 4.5. And for part A, we need to write down the total number of students, so total number of students in terms of P. Now, fairly simple, but there are one or two things that we need to understand thoroughly. So, first things first, the frequency. What is the frequency doing? What is going on here? There are 7 grades, okay? And so how do you interpret this? Getting a grade of 1, okay, assume grades are from 1 to 7, see? So getting a 1 is like failing, getting a 7 is getting on 100%. See, that's like the idea I'm trying to give you. Or 7 points, you can think about it like that too. Got it? So the student that got 1 point or a grade of 1, how many students had a grade of 1? Only 1, because the frequency is 1. How many students had a grade of 2? 4 of them. How many students had a grade of 3? 7 of them. How many students had a grade of 4? 9. How many students had a grade of 5? P, who knows what that is. How many students had a grade of 6? 9. How many students had a grade of 7? 4. All right. So clearly down below, for frequency, it's also associated to number of students. And this, it makes sense, because imagine we had a different table, like a smaller one, and let's say this was, I don't know, coffees drank. And here we have frequency, see? And I tell you, I don't know, of the people that drank 1 coffee, we had 2, and of the people that drank 2 coffees, we had 3. How many people did I survey? Well, you add the ones that drank 1 coffee with the people that drank 2 coffees, so 2 plus 3, your total's 5. Makes sense, doesn't it? Well, up here, we have to follow the same sort of logic. So for part A, we need to write down the total number of students in terms of P. So the number of students has to be all the frequencies added up together. So you can have 1 plus 4 plus 7 plus 9 plus P plus 9 plus 4. Now you can do that with your brain, or you can use the graphing calculator because you should have it for the test. So why not? You do 1 plus 4 plus 7 plus 9 plus 9 plus 4. So here I added everything except for the P. So all of this combined together is going to give you 34 plus P. Okay, notice how I didn't add P onto my calculator because I can't. For part A, the total number of students in terms of P is 34 plus P. Now, the other small disclaimer I should be doing is that because it says in terms of P, well, what does that mean? Basically, it's asking you, write down the total number of students, and your equation has to, or your expression has to include P. Whenever it says in terms of P, your answer needs to have that P inside of it. If they tell you to write something in terms of X, your answer needs to have X inside of it. Write down something in terms of Y, your Y has to be inside of it.
That is what it means by in terms of this, in terms of that, in terms of P, your P gotta be in there. Not literally, but okay. For part A, it's gonna be 34 plus P. Yeah. For part B, we needed to calculate the value of P. And so here it's a little bit different, right? Now, what do you have to work with? On the one hand, you have the massive hint that sometimes in IB, more often than not, something from part B requires something from part A. So why would I need the total number of students for calculating the value of P? So on the one hand, you have, these are your two pieces of information. On the one hand, you have total number students. So that is one piece of information you have, that the total number of students is 34 plus P. The other piece of information that you have right now is that the mean grade, because they told us earlier, the mean grade is 4.5. So how can I, using these two things, try to find the value of P? Well, the obvious question we have to do is, how does the mean grade have to do with the total number of students? How are they associated? How are they not? Okay, we have the mean grade. What is the formula for mean? Now, I can show you from the formula booklet, and it's very useful to know because the day of the test, the formula booklet is something you will be using. Guys, the day of the test, you'll be walking in with a couple of things. You'll be walking in with a pen and pencil, a calculator, 2 years of experience of this thing called IB, 2 hours of sleep, and the formula booklet, okay? The formula booklet has a lot of formulas inside of it, of course, but it's no use to have it if you don't know what's in it. It's no use to have it if you're not quick with it. So you read mean, you're already opening up the calculator, the formula booklet, to find the statistics and probability page. Bada bing, bada boom, there it is. There is the formula for mean. Now, this formula for mean looks absolutely nasty, let's be honest. See? So let's break it down a little bit. On the one hand, for mean, this n down here is just going to be your total. So, whoops. So the total number of students right here, that's going to be the n in your equation, right? And then the mean, which is x with a little bit of a bar on top. So this is the mean, right? Like your result. Well, it's right here. So this is going to be your x with a bar on top. So all you're really missing is all this stuff up here. Now, what is this? This is I think you call it a summation in English. Una sumatoria. Whatever. Point is, that is like your data in essence. It's like your data. It's your raw data. You can think about it that way. Now, I think it makes much more sense if I just show you instead of me trying to explain what the summation thing does. The one thing I do need you to understand is that a summation, o una sumatoria, all it really does is it adds up all of your different f's with x's. Okay? So it's a long chain of addition. That will be your numerator. All right, but applying the formula that I have until now, I have the mean there on the left, and I have the total on the bottom. So for now, what I can, I keep showing the answer. So for now, what I can do, okay, is that I have the mean grade. I have the total on the bottom for your denominator, which is 34 plus P. And now I can start filling in the numerator up top. So for finding the mean here, all you really need to do is multiply the grade times the frequency and add, you have to add all of these multiplications, right? So you have to add 1 times 1 plus 2 times 4 plus 3 times 7 plus 4 times 9 plus 5 times P, etc., etc. How does it look on pen and paper? Here it is on your screen. So you have the first grade, which is going to be 1 times 1 plus 2 times 4 plus 3 times 7 plus 4 times 9 plus 5 times P plus 6 times 9, 69, plus 7 times 4. All right? So this helps you calculate the value of P. And I know some of you are already thinking, this guy on YouTube is crazy. this looks nasty. And I would say, I am crazy, and this does look nasty. But there is one thing you have to admit is very helpful to you. Although this formula looks absolutely terrifying, there's only one variable. You only have the variable p. Yes, you have it in two places, but it's the only variable you have. And so you know you can reach p equals something from here. It might take a couple of steps, but you're going to get there. Okay? So this formula does look nasty, but you only have p in it, so you can solve it. Okay? Yeah, the first thing I would suggest that you do is actually getting rid of this denominator. No one likes denominators, so how can you get rid of it? Well, this denominator is technically dividing, so what you can do is multiply both sides by 34 plus p. Because if you multiply both sides by 34 plus p, this goes away with this, and you end up with, well, obviously you need to do 34 times 4.5, because we are distributing like this, right? So I end up with 153 plus 4.5p. Has to equal all these different parentheses. Now, of course, I have the 5p over here that will remain unchanged. So I know I will have 5p somewhere in there, plus all the addition of all the other ones. So all the other ones, which I'm now marking in green, I will be putting into my calculator, adding each other. Okay? So putting all those guys in green, I end up with 1 times 1 plus 2 times 4 plus 3 times 7 plus 4 times 9 plus 6 times 9 plus 7 times 4. Let me double check. Looks okay. Boom. So 5p plus 148. Okay? Yeah. And so now we need to, well, combine what I can combine. I'm going to choose to have all p's on the right side. So I can do minus 4.5p minus 4.5p. I end up with 153 equals 0.5p plus 148. You want to get p alone, so you do minus 148 minus 148. That gives me 5 equals 0.5p. You divide by 0.5 onto both sides, and this should be giving me p equals 10. Let's see if my quick maths worked out well. It does give you 10. So p has to equal 10 in this context. Let me just double check with the answer key over here. But look at that, p equals 10. We followed the same formula. It's essentially you use the mean formula here. See? 34 for plus p. I'm just showing you the answers so that you trust this guy online. Not that you should trust guys online, but at least for this math problem you can. That's how you solve number 5. So the quick recap is keep in mind how the mean formula works, okay? And also acknowledge how I reached it. First, especially if there's a problem that you're kind of stuck on, write down what you know. And so what I knew was the total number of students and the mean grade. And I said, okay, is there a formula that connects the two? Well, the biggest buzzword here is mean. So let's look at the mean formula in the formula booklet. And through there, you quickly established, there's 3 things you need to fill in. See? You need to fill in, quite literally, the mean, then the n, which is the total, which are both of the things that I have over here, right? Here I have the mean, here I have the total. And last but not least, you need to plug in like your raw data, right? So that was the last step I had to do. I plugged in the raw data, much how it looks over there, ¿cierto? On top of the numerator. I suggest you put it in parentheses so that it's more easier to visualize or think about. But that's the whole procedure, see? I will also say this is a classic. I've seen it show up more than once. It tests 2 things. It tests if you understand the frequency distribution, and it also tests if you understand how to get a specific value within your table if you have the mean. Okay, I've seen it more than once that you use the formula for the mean to find something inside the table. So, enough has been said. That is for number 5. Alright, you guys, so for number 6, we have a chi-squared problem with a little bit of probability. So we have that a company that owns many restaurants wants to determine if there are differences in the quality of food. Okay, differences in the quality of food cooked for 3 different meals: breakfast, lunch, and dinner. The quality assurance team randomly selects 500 items of food to inspect, and the quality of this food is classified as perfect, satisfactory, or poor. The data is summarized in the following table. So just so that we're all on the same page, for example, there were 101 perfect breakfasts. There were 81 satisfactory lunches. There were 114 dinners, okay? And there were 204 perfect meals, okay? That is how you read this table. And keep in mind that these edges over here are totals, okay? These are totals. All right. So an item of food, for some reason, is chosen at random from these 500. And for part A, you need to find the probability that its quality is not perfect. Ah, look at this. Given that it is from breakfast. That right there is huge, okay? So there's 2 main things I have to explain here, okay? The first one is how this exercise would be if this was not written here at all. So if this was not written here at all, you're just trying to find the probability that its quality is not perfect. And so the item which has a quality that is not perfect is going to be, for example, all of these and all of these. So in other words, for the probability that its quality is not perfect, you would be saying, okay, so my total is 500 because you are picking from these 500, right? So you pick from those 500. So that's going to be where you're picking from. So it's going to be the number at the bottom, your total, right? And up top, you're going to be saying, okay, so those are not perfect are the satisfactory, 274, plus the poor ones. So for not perfect, it's either satisfactory or poor, okay? So you go ahead and do that, and you will be doing 296 divided by 500. Okay? So that is how you would solve it if this exercise would say, find the probability that its quality is simply not perfect. Okay? Here's the thing. The exercise puts in the word given. Okay? The word given, I need you to understand that the word given, okay, has to do with conditional probability. And so the main word that gets thrown at you is either given, or if you hear something like if. Okay? Now what's happening here? Notice in my original approach, I put the total on the bottom, right? And this is usually how probability goes. You put the total from the bottom where you're picking from, and up top, you put like your plausible cases. Plausible cases up top. See? Yeah, so up top, you put the plausible cases. Down in the bottom, you put your total. So, ladies and gentlemen, given that it is from breakfast, how does this change my total? And that's the other thing that I gave you the answer pretty much, but the main idea of conditional probability is that this, and write it down, changes your total. That's all that happens, okay? If initially, for the first version that I showed you, you were picking from any of these. Well, now what's happening is that given that it is from breakfast, you are only picking from breakfast. So suddenly, kapow, kapow, you don't care about this. Now what you're calculating, the only set of data that you actually care about is this rectangle that I'm putting now in pink. This is your new total. So that's the first thing I'm going to mention. That is your new total because you're finding the probability its quality is not perfect given that it is from breakfast. So given that it's from breakfast, you only care about breakfast. You don't care about lunch or dinner anymore. Bada bing, bada boom. So your new total is going to be, well, all of those that did breakfast, which, look at that. Conveniently, there's a total column right here. So on the one hand, your new total is 232. Okay? And up top, it's still going to be for plausible cases. So plausible cases is, okay, those that within breakfast are not perfect. And those that are within breakfast that are not perfect are this 124 and this 7 right here. So you go ahead and do some quick maths. You end up with 131, if I'm not mistaken, divided by 232. Let me double check that. Looks fine to me. See? So the big idea I need you to understand is that conditional probability, which comes through given or if, changes your total. There is a formula from the formula booklet for this, okay? And if I were to get very fancy, I would just tell you, oh yeah, for a given probability, it's like this. So that stick right there, it means given. Okay, so A given B is going to be P probability, sorry, of A and B. Remember that this right there is for and, okay? Divided by probability of B. So you can do it very rigorously. We could have applied this formula in this case up here and it would have worked out. But because we had the table here, I think it's very visually appealing to understand, yo, it changes your total. So once we're talking about just breakfast, because it is given that it is from breakfast, you don't care about lunch, you don't care about dinner, your table gets a lot smaller, and so does your total. That is the biggest idea I can share with you. Do not forget, the whole point of conditional probability is that it changes your total. That's why people use it in the first place. Be very aware of that. So there's my new calculation. So it's 131 divided by 232. I check over here. Whoops, that is a little bit of a spoiler, but we'll get to that in a second. 131 divided by 232. There it is, 0.56. We check the answer key, and it's right there. See, 131 divided by 232, 0.565. So for part A, make sure you leave your answer in either significant figures or as fraction, decimal, etc. I'm just going to leave it like this right here. Okay, so that would be for part A. All right, and now for the next part, it gets a little bit more juicy. So on the one hand, we have, or they tell us that a chi-squared test. See, this fancy x with the squared is just a chi-squared. Okay, don't get lost in the sauce with that. It's a chi-squared test. So a chi-squared test at the 5% significance level is carried out to determine if there's a significant evidence of a difference in the quality of the food cooked for the 3 meals, which is exactly what the company was trying to find out earlier, right? Are there differences in the quality of the food? Is the breakfast always perfect and is dinner always poor? We have to balance that out. Like that's what the company wants to figure out. See? If basically there's a big difference between the type of meal and the quality that it gets. So they also tell us that the critical value for this test is 9.488, and they give us the 2 hypotheses. See? The first thing I'm going to mention is that H0 will be your null, okay? And that H1 will be your alternative. So there's too many observations I can kind of try to do here, right? I know that a lot of times in the IB, you need to actually write the H0. You have to actually write the H1. And so a tip that I think a lot of people appreciate is that sometimes it works perfectly well that H1 is going to have the word not inside of it. I mean, if you see the difference between these 2 hypotheses, it's really just the word not. I mean, literally, everything else is word for word. The quality of the food and the type of meal are, and boom, if you're H1, you're putting the word not. If you're H0, you're not putting the word not. All right. So that's just a quick tip on how to get the hypotheses like correct. And notice for H0, it's that they are, quality of food and type of meal are independent. And so that's a little bit like there is no difference. See, well, for H1, if they're not independent, that means there is a difference. Okay, so notice that null is usually like no difference, So because they're independent, it's no difference. But if they're not independent, then there is a difference, okay? And how do you express that? Well, H1 has to have the word not, H0 doesn't. So those are the two main tips I can give you for creating hypotheses, because I know that happens sometimes. Now let's get into the action. So for part B, you need to find the chi-squared statistic. Now this is actually fairly simple. We just need to have really clear what my tools actually are, okay? So I'm not going to show you the tools and have you memorize them. I'd rather explain the thought process that I want you to go through, right? So the day of the test, you're going to encounter this problem, right? And then you're going to read all this stuff about significance level, critical value, etc. Maybe you don't remember it too well, but it's going to slowly come back to you. And one of the things that I need to have come back to you are the tools you have here, okay? So how do you identify the tools? Well, you need to find a chi-squared statistic. So what are your chi-squared tools? You have two main tools, okay? And you're not going to remember which ones they are because no one remembers them by memory, but you do know that, this is a test. So you're going to open up your graphing calculator. You're going to go ahead and press stat and go to the column of tests. And this is where you're going to look for your chi-squared tools, okay? So notice, I'm not saying that you read this exercise and you know immediately what to do, but you should be able to read this exercise, look at the word test, which is a big buzzword here, and say, yeah, so I'm testing something. I know there's a testing area somewhere in my calculator, find it, and look for your chi-squared. I assure you, you're going to find a bunch of stuff, see, that you don't need, probably have never used, and maybe never will use, but eventually you're going to find these two chi-squareds, see? So your chi-squared tools, we're going to call it just chi-squared, okay? And you also have chi-squared GOF, okay? I'm pretty sure GOF was for goodness of fit or something like that, but we're going to leave it even more intuitively than that, see? So you have the chi-squared one, and then you have the chi-squared GOF. So what's the difference here? What is going on, right? Well, again, you're not going to remember because no one has magical memory. So you're going to press one by one and see what they ask for. So depending on what they ask for, you're going to see, this is when I use this. That is when I use that. So if I press the chi-squared one, it asks for these big letters. If it asks for the big letters, then we're actually talking about a matrix. If you haven't seen this before, do not worry, I got you. So the normal one, the chi-squared by itself, is going to be a matrix, which for us, puny human individuals, we're going to remember it as a table. So whenever you have a table, you're going to be using the matrix, okay? On the other hand, if we go ahead and check the other test, which is chi-squared GOF, it asks for lists. And so this one's more apparent, right? It's asking for a list. So that's like L1, L2. The table for the matrix is literally something that looks like this. A encapsulated by a bracket that looks like that. B that looks like a bracket like this, okay? So right now we just established, okay, the two main tools are chi-squared and chi-squared GOF. Chi-squared GOF is asking for lists. Here I don't have a list. Here I have a table. I mean, and you might be thinking, but I can put 3 lists. You can only put 2. L1, L2. Okay? So that's the first thing I'm gonna establish. So here in this exercise, I will not be using GOF because I don't have lists. I have a matrix. So go ahead and put it into your matrix, right? Now, where the heck is the matrix? It's right below math, right on top of this button here, see? There's gonna be second, that button here, and you hit matrix. And well, I did do it earlier, but I'm going to show you again. Basically, you just have to edit the first one, right? You have to edit A. Now, you probably have something that looks like this. Whoops. You probably have something that looks like that. Okay, you probably have like a matrix that is smaller or maybe bigger. You need it to be aligned with what you have on the exercise. Yeah? And there's something very important that I need to establish. Okay? Although for calculating the chi-squared statistic, the total columns are super essential, your calculator does it for you. So actually what you need to plug in is only this right here. Do not plug in the total columns. It is not your job to go over that. So plug this in and only this in to your matrix on A. And so that matrix on A that I just put in pink, well, it's 3 rows and it's also 3 columns. So clearly it is a 3 by 3. So that's the first thing I'm going to do. Up top, I'm going to change it to a 3 by 3. And then I'm going to put in all the values. So the 101, and put it in order as well, important. 1, 2, 4, 7. You basically want a table that looks exactly the same like the one in your exercise. See? Yeah. So there, I plugged in just matrix A. See? Now, if I go back to the stat and the test and the chi-squared, notice, for my observed, I have matrix A. For my expected, I have matrix B. And you might already be thinking, don't I have to create an expected matrix for B? And I say, nuh-uh, your calculator is your best friend. And best friends sometimes do your homework. Just kidding, don't do that. When the calculator, when you put the observed matrix on A, it automatically calculates your expected matrix on B. Trust me on this, okay? You do not have to get into the details of calculating the expected values in a different matrix. All you have to do, okay, is plug in the observed and the expected will be calculated for you. So go ahead and press calculate. We don't care about drawing this time or ever probably. Just go ahead and press calculate, see? And there you go. You get 3 things, see? You get the chi-square statistic, which there's your answer for part B. So for part B, the chi-square statistic is 11.021. And might as well put a couple more numbers. 23361. 23361. So there is my chi-squared statistic. How do you show your process? You will literally have to like, I mean, if you show this, like visually, if you show this, you're gonna get full credit. See? So somewhere down here, right in your answer, you have to be very clear that this is the table that you put into your calculator and you put it into a matrix. How do they know that it's a matrix? Because you're writing the big letter A between these brackets like this. That is the language for matrices. Okay. So that is how you get the method point if there were to be one. For these exercises, usually there isn't a method point, so it doesn't really matter, but just so you know, okay? Yeah. That is for part B, all right? And the last part, which is actually when I'm going to start talking about what chi-squared even does in the first place, notice that everything else was just procedure, like what you have to know by heart, okay? Now I'm going to explain your procedure, maybe make it a little bit more friendly, maybe help us understand, okay, this is my chi-squared. What the heck do I do with it? See? So for part C, we need to state with justification the conclusion for this test. So this is going to be the more hardcore statistic mathematic part of the video. So buckle up and good luck. Yeah. Here's the main idea. So a chi-squared. Its purpose. Pass the butter. Its purpose is to I'm going to say compare. Yeah, so compare the differences between observed and expected values. Okay? So in the chi-squared test, you compare the differences between observed and expected values. If the difference is too big, then maybe H0 is wrong, right? Because let us remember that H0 usually has to do with like there is no difference, things are independent, everything's okay. H1 is usually like there's a problem, there's a difference, there is a statistical sort of like issue going on, right? So if the difference is too big, then maybe H0 is wrong, okay? And so just to hone in on that a little bit more, right? This company picked 500 different meals at random between breakfast, lunch, and dinner. They evaluated if it was perfect, satisfactory, or poor, and these are the numbers that came out. See? Now, just like throwing a dice, and you can throw a dice and get a 6 10 times in a row, see? You have to evaluate, okay, how likely is that? See? Because if the probability of that is extremely, extremely low, and some magician does it 5 times in a row, 5 times in a row, they get a 6 10 times in a row, well, that's kind of crazy. It's probably a loaded dice. You can start concluding stuff like that, see? Because it is a little too far out, and here's the main idea, from what you expect. And so the chi-square statistic, think about it this way, okay? The bigger the chi-squared statistic, the bigger the dispersion, maybe the difference. The bigger the difference between between observed and expected values. So maybe this is a bigger idea you can write down. The bigger the chi-square statistic, the bigger the difference between observed and expected values. Now the obvious question here is that at some point it gets too big, right? But how do you evaluate if it's too big or not? So for evaluating if it's too big or not, you would basically say, if the chi-squared is bigger than critical value, then it's too big, okay? That's basically it. If the chi-squared is bigger than your critical value, then it is too big. The other thing you do is that if the p-value, which we got over here in the calculator, right? If that p-value that came out here, right, is less than your significance level, right, then it's too unlikely. Okay, so these are two sort of things. Whoa, what the heck just happened? That's crazy. All right, this just glitched out really hard. Wow, that's new. All right, cool. Wow. Anyways, so there's two ways to conclude, okay? Two ways to conclude. If your chi-squared is bigger than your critical value, then it's too big. Now, what's too big? Then the difference between observed and expected is too big. The other way that you can conclude is using the probabilities, right? Because these values there are not probabilities. The p-value and the significance level is. So if the p-value is less than the significance level, which is a probability of 5%, then, god dang, then it is too unlikely. So you either say, okay, these values are way too far from my expected, or what I'm observing is far too unlikely, okay? So essentially, for concluding, you have your chi-squared, which we said was 11. Let's leave it at 11.0, okay? And you also have your critical value. So critical value, they told us, was 9.488, okay? So on the one hand, you can say that, okay, the chi-squared is clearly bigger than the critical value. And this, by the way, just so you know, is your justification. So if chi-squared is bigger than critical value, then the difference between observed and expected is too big. And so if the difference between observed and expected is too big, then the quality of food and type of meal are independent. Then you reject HO, right? You would have to reject HO. Just to check over here. Exactly. You reject HO. Okay? So that is one way you conclude. If the chi-squared is bigger than critical value, you reject HO. The other way you can sort of memorize it if you want is the alternative, which is if chi-squared is less than critical value, then you fail to reject. you can also think about it as you accept HO. See? In this case, we have the scenario that I'm putting now in red, because you only have to compare 11.0 being bigger than 9.44488. See? So clearly you reject HO. The other way you can conclude is using the p-value and the significance level. So make sure you're associating the right things with the right things. P-value with significance level, chi-squared with critical value. Okay? The other way you can say, the other thing you can say is, okay, so your p-value, right? So your p-value gave us 0.02. 63, right? While your significance level, they told us, was 5%. So 5% as a decimal is 0.05. See? So clearly the p-value is less than significance level. And so if the p-value is less than significance level, what I'm observing is too unlikely. And if what I'm observing is too unlikely, it's too crazy, then you have to reject HO. Which actually, again, putting it in red, is the current scenario. But just so that you can complete your notes, technically the alternative is that if your p-value is greater than a significance level, then once again you fail to reject HO. See? So again, have very clear, when you compare the p-value with the significance level, you are talking about probabilities. When you compare the chi-squared with the critical value, you are comparing like a benchmark or something like that. Like if it goes beyond this number, it's way too big. See? The visual aspect, and this will be the last minute of my video probably, the visual aspect of this is the following. So a chi-squared looks a little bit like a normal distribution, just that it's very skewed. See? So it looks something like this. Boom. Okay? And so your chi-squared is here on the bottom. Let's say that the critical value they told us was 9.488. See? So this is 9.488. So this is my critical value. And essentially, anything to the right of this is like a little too far out. Okay? It's not what you expect to observe. See? And one thing is that it's unlikely. Another thing is that it's like crazy. See? So for example, values that are over here could be very unlikely to observe, but it's not too crazy. While anything to the right of the critical value is not only unlikely, but it's also crazy to observe. See? It's like a little too far out, and that means that my HO is probably wrong. That's the whole point of the chi-squared statistic. See? Now, that's my critical value. This is a little bit like your benchmark. See, like anything beyond this, you have to really question yourself what is going on. And the chi-squared that we figured out was 11. 11. This was my chi-squared. So clearly, it's to the right of the critical value. It's to the right of the benchmark. So it's a little too far out. The difference between your expected and your observed is a little too much. So that is how you would interpret this. See? That is in the sense of like you're comparing like benchmarks and stuff like that. If you want to think about comparing probabilities, well, probability with a curve has to do with the area under the curve. See? So for example, this right here could maybe be like the 5%. See? And you got like a 2% that's over there. See? So anything that's below 5%, that's 5% or below, it's the same as saying that you're from the blue line to the right. Just that you're thinking in terms of area. So this is the 2%, ¿cierto? Clearly it's within the top 5%. It's a little too far out. It's too unlikely. H0 is probably wrong. See? So that is how you evaluate a chi-squared. Here is the visual aspect. See? And honestly, instead of remembering all this, because I know it can be a hassle, I know it can be hard, you can just kind of memorize what I'm going to put now in green. See? So if you memorize this and you memorize that, you're going to be good to go. See? It's not too much to memorize for getting easy 2 or 3 or 4 points. Okay? And remember, you're not going to know by memory when to use which chi-squared, but remember that you have a list of tools. Okay? Go one by one, discard them. You don't have to know all the tools by memory, but you do have to know roughly which ones you have. That's the main message I want to pass to you today. And yeah, I hope it helped. So that is for number 6. All right, you guys. So for number 7, we have that Annie owns 4 cafes. That's the dream, isn't it? Owns 4 cafes represented by the points A, B, C, and D. So all these different points that we're seeing on screen are different cafes that Annie owns. Annie wants to divide the area into delivery regions. So that means that, for example, B is going to be delivering all up here. C is going to be delivering all that's over there. And then A and D, clearly, we still need to complete the Voronoi diagram because, as it says here, we have an incomplete Voronoi diagram, right? So somewhere along this line, we will be splitting up between A and D and seeing who delivers which area, okay? That is our job. That is probably going to be your task, and that's what's going to show up later, right? Now, you probably clicked on this video because you have no idea what a Voronoi diagram is. First of all, at some point in my life, I also did not know what the heck a Voronoi diagram was, okay? So this is something that anyone can learn. Don't be scared. I know there's a lot of buzzwords we need to go over, but let's go piece by piece. There's 3 things you will learn this video, yes or yes. Okay, you will understand a little bit better what a Voronoi diagram is. You will understand a little bit better what we mean by perpendicular bisectors, which is probably the biggest buzzword you're ever gonna have, okay? And midpoints, right? These are the main things we need to go over. These are the main things we need to understand. So, a Voronoi diagram, the reason people use them is that it helps you split up areas evenly. It helps you split up areas / distances evenly. I mean, more than areas, I think it helps you split up distances more evenly. That's a better sort of explanation, see? Because what would make sense for Annie, right, is to plop into this graph all the different sort of locations of the cafes, right? And so it would make sense that the distance from here to here is the same as the distance from here to here. Okay? The distance from here to here is the same as the distance from here to here. The distance from here to here is the same as the distance from here to here. And so that is the main sort of intuition of the Voronoi diagram. First you put down your cafes, first you put down A, B, C, and D, and then you figure out where are those distances so you can split them up evenly. Okay, it has to be even. So if you take a good look at, for example, between B and C, right, you can tell that it fills up at least one square, it fills up at least one square, and then it fills up a little bit of the next, right? And then it fills up a little bit of the next. And so if you look at that, this distance right there is the same as this distance right here. And that's the whole point of the Voronoi diagram. That is why you use it in the first place. It helps you figure out how these distances work, yeah? Now, of course, this has a bunch of sort of information like and keywords aligned to it, okay? So the first thing I will tell you is that A, B, C, and D in the world of Voronoi diagrams is what we will call sites, okay? And the lines that I am now putting in red, okay, these are your perpendicular bisectors, okay? And that is a loaded word, perpendicular bisector. So there's 2 things happening here. On the one hand, coming back to the example between B and C, so you have a line that goes from B to C like this, right? So this line here, what that red line does, okay, the one that's remaining, the perpendicular bisector, well, following its name, it bisects it, okay? And bi, what comes to mind? Bisexual, so it's 2, okay? So bisexual for 2, bisect for 2. It's like you're cutting it in 2, right? So think about it that way. On the one hand, you're dividing it by 2. So this perpendicular bisector, what it's doing, the line that's in red, it's cutting the pink line in 2. So that means if this distance, I'm just going to make it up, yeah? But if this distance from here to here is 5, then the distance from here to here also has to be 5. Because you know that this red line that's drawn onto the Voronoi diagram is a perpendicular bisector. It's cutting the pink line in half. If this up here is 3, then the one on the bottom also has to be 3. Okay? Now what it actually is, if I do it by just eyeballing it, it looks like it's, well, I mean, this is 1, it might be like 1.5. Okay? So that's what it does. It bisects it on the one hand. On the other hand, here it says that it's perpendicular. Right? And perpendicular, you should be thinking in slope. There's 2 main types of slope that you will encounter. Okay? You have perpendicular slopes, perpendicular, and you have parallel. Okay? And the quick conclusion regarding both is that for perpendicular slopes, which is the harder one, you have that the slope of the first one times the slope of the second has to equal -1. This is also why you might have heard that for perpendicular slopes, it's the negative reciprocal of the other one. So when they say reciprocal, it's just a fancy way to say like 1 divided by that, right? And then negative, because of course there's a negative right here. See? So the hardcore mathy formula, it's either of these. You can remember it however you want. The other sort of cool piece of information is that because they're perpendicular, because they're sort of like perfect mirrors or something like that, you end up with a bunch of 90 degrees in here. Okay? That's not so relevant for us in this case. What really matters is this formula right here for perpendicular. All right? For parallel slopes, which is not the case, but I mention it because, well, if you read perpendicular, you should be thinking slope. If you're thinking slope, you should also know that parallel is a thing. So for parallel lines, you have that the slope of the first equals the slope of the second, quite literally. So parallel lines are lines that never touch. And why do they never touch? They never touch because they have the same slope. So they're always growing at the same sort of speed. And so if they grow at the same sort of speed, they're never going to touch. If one of them were to grow a little bit faster than the other, then eventually they would touch. But if they both grow at the same speed, then they are never going to touch. Okay? Think about 2 cars going at exactly the same speed. They're never going to pass each other. But if one of the cars is just going a little bit faster than the other one, then it will pass it. And it's not a parallel slope. It would be different slopes. See? So parallel slopes, they're equal to each other. This is the fancy formula you have to remember. Visually, I put it down there. For perpendicular slopes, usually you have something like this. They sort of cross each other. And the big detail, as I mentioned earlier, is that you have a bunch of 90 degrees within them. Okay? So that is the perpendicular bisector. In conclusion, if you draw lines between the sides, right, lines that I'm putting right now in pink, okay, the perpendicular bisectors are the one I'm putting in red. Okay? So the last buzzword I'm going to go over before even embarking upon the problem, but it's just such important buzzwords and vocabulary that you need to know. The last thing I'm going to talk about is that a midpoint, okay, following its name, is quite literally the middle of a point. Okay? So notice, why is this so relevant? The perpendicular bisector, as I said, the line in red, is cutting the line in pink in half. If it's cutting it in half, where does it cut it in half? Well, right at the middle. Ah, so here, where it's cutting it in half, you have the midpoint between B and C. You have to have the midpoint here because the perpendicular bisector is cutting right through there. Interesting. So now we have all the information we need. Now the monologue is over. Now let's go ahead and do the actual problem. The first piece of information that they give us is, look at that. The midpoint of CD is 5.5, 1.5. So the midpoint of BC, I'm following the colors, right? So I have this line in red, which would be the perpendicular bisector. And then I have this line connecting the 2 sides between C and D. Should look something like that, ¿cierto? This midpoint here, I'm just going to write it. So this is midpoint of CD, and midpoint CD, they just told us, is 5.5, 1.5. Okay? There we have all the information. I'm going to erase what I have up here because I used it just for explaining. Now we're talking about only what's relevant for the problem. And for the problem for part A, we have that we need to show that, which is already important that I acknowledge, show that the equation of the perpendicular bisector, we already know what that is, of CD, is this right here. Okay? So the perpendicular bisector of CD is the line in red that I have drawn right now. That is the equation that we need to find. All right? The other important thing that I have to mention is that here it says show that. Guys, whenever you have a show that exercise, it means that this is true. Why is this relevant? It's relevant because maybe for part B or for part C, it's very relevant that you have something from part A, right? And if this is show that, that means you can skip it and use this as true. Use this as factual information for you to be able to solve B or C. Now you might be telling me, why would you do that? This is worth 3 points. Why would I skip it? Well, you might have to do that if you're running low on time, if you tried to solve and you couldn't and you need to be time efficient. If it says show that, know that you have the option to skip it and use this information as factual as true. All right. The show that, I'm just showing you the mark scheme. The show that is reaching the same thing. It's no new information. Part A is giving information that might be important for B or C. Okay. So that's the first sort of test taking strategy. Whenever you have a show that exercise, you can use it as facts and maybe solve something down the line. Claw for points wherever you can. ¿Cierto? All right. So back to it. We need to show that the equation of this red line is this right here. Okay. Now, for arming the red line, on the one hand, we have the midpoint. See? Now, before delving into what we have, let's first understand what we need. So, right now for part A, technically, I am creating a line. Creating a line. Or an equation for a line, right? And through creating the equation, creating an equation of a line, we need to reach this guy here. So what are my tools, right? Well, the main tools that you have are in your formula booklet. So go to your formula booklet, get familiar with it. One thing is having it the day of the test, which you will, and another thing is knowing what's in it, okay? So once you establish that you need to create an equation of a line, you should be familiar enough with the formula booklet that you know that there's a part somewhere in here that you know that if you search you will find of how to create an equation of a straight line, okay? So guys, this is the level that I need you to reach. You need to be able to establish, what's the procedure here? I need to create the equation of a line. What are my tools for creating an equation of a line? I know that that's somewhere in my formula booklet. Let's look for it. You will find it and you will go from here, okay? That is the ideal procedure, you guys, okay? Establish the buzzwords, establish the procedure, and more likely than not, go straight to the formula booklet. Don't let your ego grow. Don't say like, I have the formula booklet, so I don't need to memorize it or whatever. No, you don't need to memorize it, but you do need to know what's in it, okay? It is an additional tool the day of the test. Use it. Here, for equations of a straight line, you have 3, okay? I'm not going to jump too much into it, but I will mention, and the biggest tip I can give here is that usually you will start here. Usually you will start here, and from there you can easily reach this, and you can also easily reach that. For creating the equation of a straight line, you usually start with what I have in red, right? What I have in red, you might have heard it as point slope formula. Why is it the point slope formula? Because following its name, you need a point and you need the slope. And that's all you need. For creating the equation of a straight line, once you have a point and once you have a slope, you can go ahead and plug it in. For example, this x1 here is the point that you found, and this y1 here is the point that you found. This m here is the slope, right? And this y and this x, you're going to leave it as it is because that is part of your answer, the y and the x. See? So all you need to plug in is just a point, just a slope, and you're good to go, right? So I'm going to write down here what I will be using. So for part A, I know I need to use the point slope formula. That it? So here's the point slope formula straight from the formula booklet. I know that I need one set of points, and I know that I need the slope. Okay, that's all I need. Now, this is for the line in red. So do you have a point for the line in red? Heck yeah, you do. Over here, they gave you the midpoint of CD, which is part of the line that's in red. So I already have a set of points, which I will be using 5.5, comma 1.5. Now all I need is a slope. So how can I get the slope of what's in red? Well, remember, and this is usually the procedure you have to do actually. See, remember the line in red is a perpendicular bisector. So if it's a perpendicular bisector, it has the perpendicular slope to the line that's in pink. So the next question is, can you get the slope of the line that's in pink? You can. So the procedure now is going to be slope of pink perpendicular stuff, or perpendicular formula, and that will give you slope of red. Okay? I know I'm saying this in a very ooga booga sort of thing, like slope of pink, perpendicular formula, slope of red. But it really is that simple. It's 3 steps. Find the slope of the pink, apply the perpendicular formula, find the slope of the red. All of this makes sense because you understand that you have a perpendicular bisector. You understand that the red line is perpendicular to the pink one. That is extremely important that you never forget. The Voronoi diagram is filled with perpendicular bisectors, and that helps you understand that you can get the slopes of all of these guys. See? Now you might be thinking, okay, so slope, how do you find slope? Go to the formula booklet, find slope. Here it is. You might be saying that's gradient, and I will tell you gradient equals slope. The first thing I'm going to mention is that I know it's taught in a lot of different schools and areas and whatever, okay, that slope is really what they call rise over run. Okay, how much you rise divided by how much you run. And I mentioned this because this equation suddenly makes a lot more sense. You have an XY coordinate plane, ¿cierto? So your X is clearly your horizontal, while your Y is clearly your vertical. And so if X is your horizontal, it's going to be how much you move side to side, it's how much you run. While your Y, which is your vertical going up or down, is how much you rise. So that is why it's rise over run, because your Y values are up top, while your X values are on the bottom. So that's just a small hint. That is why we call it rise over run, okay? Now, more importantly, how does this formula actually work? You have the little y, y1, y2, x1, x2. This is not y squared or x squared or anything like that. All this is really telling you is your first x with your first y and your second x with your second y, okay? So in terms of points, you have like x1, y1, x2, y2. All right, so which one is your first point? Which one is your second point? That's all that's really happening. Clearly, the first point of my line that's in pink is point D. And point C is going to be my second point, right? So what are the coordinates of C and D? This is so much easier than what you think. It's staring at you right now. Point D has x coordinate of 4 and of 1 over here. Point C has an x coordinate of 7 and a y coordinate of 2. So suddenly, now for the slope, right? Well, following this procedure that went up here, the 1, 2, 3 over there, the slope of the pink, right, is going to be following the formula, which is y2 minus y1 divided by x2 minus y1. Well, you can define your first point and second point however you wish. In this scenario, I'm going to call this my point 1 and this is my point 2. So if that's my point 1 and this is my point 2, that means this is x1, this is y1, this is x2, this is y2. So if I go ahead and plug in like that, the slope of the pink following step 1, ¿cierto? I have 2 minus 1 divided by 7 minus 4. So that gives me 1 divided by 3. So that is the slope of the pink one. I double check quickly. On the one hand, it's a positive value, so it makes sense because this is a line that's going up and it's not increasing too fast. 1 over 3 makes sense. And even more so, 1 over 3. So this is my rise up top with 1. This is my run on the bottom. I'm rising 1 square and I'm running 3. Checks out to me, doesn't it? So there's my rise over run. This is the slope of the line that's in pink. See? I apply the perpendicular formula, which I have down here, which actually, is it over here? Perpendicular gradient. I don't think it's up here. This might be the kind of thing that you have to memorize, see? Or learn thoroughly. So now you apply the perpendicular formula that's right there, see? So for the perpendicular formula, let's remember that we said that the slope of the first, if they're perpendicular, right? If they're perpendicular, the slope of the first times the slope of the second gives you -1. So the slope of the first, which we are calling 1 over 3, times m2, which is the line that's in red, has to equal -1. So to get m2 alone, clearly all I have to do is just times 3, right? Times 3 to both sides, so this goes away with this. I end up with m2, which is my line in red, right? And now it's step 3, giving me the slope of red. I end up with m2 equals -3. And m1 over here, so this is m1, right? So m1 is 1 over 3. Okay, I should have specified that earlier. m1, which is the line in pink, is 1 over 3. m2, which is the line in red, the perpendicular bisector, is -3. It makes sense. If this is rise over run, that means I have a rise of -3 and a run of 1. So rise of -3 go down 3, and I run over 1. Checks out. Makes sense. All right. That was a very long but complete explanation of how the slopes work. Now you establish the slope of your perpendicular bisector, which we said was -3. So from here, you can plug everything in. And the main objective, let's not forget, is reaching this right here. See? So on the one hand, first I plug in. So I'm going to plug in y minus y1, which we said was 1.5, equals m, which is -3, times x minus x1, which we said was 5.5. So just so that no one gets lost, this is x1, this is y1. Now, you need to reach what's this that's here. See? Now this that's here, take a close look. All that really matters is that y is alone. So as long as you search or make sure that you reach for y being alone down here, you should reach something similar to that, right? And this is no different than what I said earlier, that from here, you're going to pass to that, okay? Just make sure that y is alone in order to get the different sort of ways in which you can express a straight line, yeah? So from here, the first step that I like to do, okay, is that I distribute, see? So I end up with y minus 1.5 equals -3x plus -3 times that. Now -3 times that, I could do it by hand, but why would I? So here I pull up my fancy calculator and I can do -3 times -5.5. 16.5. So plus 16.5. I can do plus 1.5 to both sides. I end up with y equals -3x plus 18. I double check up here. It's exactly what I have. See? So for part A, it's fairly simple, but there is a lot of procedures and explanations that you need to understand why you're doing what you're doing. The lines of math are not that hard, but understanding, to my knowledge, or to my perception, understanding perpendicular bisector is the #1 thing for Voronoi diagrams. See? So once you understand that the line is in red, is your perpendicular bisector of the line that's in pink, everything becomes much more friendly. Also remember, oftentimes this is easier than what you think. If you have a Voronoi diagram that is giving you the different square distances and is giving you the 1, 2, 3, 4 down here, ¿cierto? You can probably find a lot of these points just by looking at it. See? I literally found the coordinates of D just by saying, okay, this is 4, this is 1, bada bing, bada boom, 4,1. Oftentimes it's easier than what you think. That's what I'm trying to tell you. See? Yeah, that is for part A. Pretty simple. For part B, we need to complete the Voronoi diagram shown above. So, notice, site B is split up from C with this perpendicular bisector. C is split up from D with this perpendicular bisector that we just found. B is split up from A with this perpendicular bisector, and B is split up from D with that perpendicular bisector. So which one do we still need to split up? We still need to split up A and D, okay? So let's talk a little bit about how we would do that. It's much simpler than what you think. It's much more straightforward than what you think. On the one hand, they're on the same sort of like Y level, okay? So because they're on the same sort of Y level, the approach is actually fairly simple. But let's still make it as rigorous as possible, see? So this is like the OG line between A and D, and I need to draw a red line somewhere here, okay? I'm not sure where, I'm not sure where the perpendicular bisector is, but you do know that the perpendicular bisector bisects it. It divides it by 2. So what is the distance that I have in pink? Well, clearly you're going from from 1 to 4. So from 1 to 4, you count how many times? 1, 2, 3, you count 3 times. So the distance from A to D is 3. So the perpendicular bisector has to be cutting where we have 1.5 on both. Okay. So where you have 1.5 on both, well, let's count it. Here you have 1, ¿cierto? So 1 plus 1.5, 1 plus 1.5, just so that you all trust me, is 2.5. So boom, your perpendicular bisector has to go on 2.5, like this. And there is my answer, okay? That is my perpendicular bisector, and it's perfectly vertical. Why is it perfectly vertical? Because A and D, the line that's connected in pink, is perfectly horizontal. So, complete the Voronoi diagram shown above. You can just draw like this. It's good enough. If you want to be more rigorous on your approach, you would say something like, I don't know, that A is 1,1, ¿cierto? And D is 4,1. So A is 1,1, D is 4,1. Maybe you would say midpoint, right? Midpoint has to be between the both. You can use the midpoint formula that's over here, if you like. That you can use this one here, but really visually you can just sort of tell the midpoint has to be at 5 divided by 2, so at 2.5, right? The same thing we concluded visually. So you can say that the midpoint is at 2.5, 1, right? And perfectly vertical, right? You can do the rigorous approach, which is doing all this stuff over here. You're going to reach the same conclusion, you guys. Okay, the equation of your perpendicular bisector ends up being x equals 2.5. This is the equation of your perpendicular bisector. And I really need you guys to understand that a little more thoroughly, okay? Whenever you graph, for example, x equals 2.5, all you're doing is that you're putting a line that goes straight up, and notice the x values. The x value doesn't change. The y value does, but the x value doesn't. So for putting a vertical line, you leave sort of like locked in an x value. And for putting a horizontal line, you leave locked in a y value, okay? So for this line that goes straight up, you just express it as x equals 2.5. That is how we completed the Voronoi diagram shown above. And last but not least, we know that Annie opens an office equidistant from 3 of the cafes, B, C, and D. So that's the other thing I need to mention. All these perpendicular lines that are in red, the perpendicular bisectors, they help you make everything equidistant. It is a fact of the Voronoi diagrams, okay? The equation of the perpendicular bisector of BC, all right, perfect. So of BC, so this guy here. So just the line in red that I'm leaving now, the equation of that red line is this, okay? And through there, we need to find the coordinates of the office. Now, because Annie opens an office that is equidistant from the 3 of the cafes, that means it has to be where the perpendicular bisectors are meeting, because the perpendicular bisectors is exactly what helps you split up distances evenly. So if it's between B, C, and D, well, what is the what are the perpendicular bisectors between B, C, and D? It's that one, it's this one, it's this one. So the cafe that Annie is opening has to be this point right there. That it? Now, what information do you have? They just gave you the equation of this line up here, which I'm going to put in orange. They just gave you that this is that. 3y equals 2x minus 1.5. And you have from part A that this equation here, right, is this guy right there, is y equals negative 3x plus 18. And guys, this is much simpler than what you imagine, right? So because you need to find this point right there, and you know the formula of these two equations, well, these two equations, what do? They intersect right there. And so if they intersect right there, that means they are touching. If they are touching and intersecting, they are equal to each other. So the big idea I need to share for part C is that if they intersect, then they are equal to each other right at that point. So if two lines intersect, then they are equal to each other right at that point. So my first equation, as I mentioned, was y equals 3y equals 2x minus 1.5. So 3y equals 2x minus 1.5. This was your first equation. And your second equation from part A is y equals negative 3x plus 18. So if you find the intersect between these two lines, then that's going to be where the two lines meet. That will be exactly the equidistant location that Annie wants to open this office at. Okay? So how do you find the intersect between these both? Well, here you actually have a system of equations. Okay? Notice, the annoying part of looking at both of these individually is that they both have two variables. So as much as the first one as the second one, currently they both have x and y within both of them, right? So it's hard to solve them individually, but solving them together will help. It's going to make more sense in a second, yeah? Here you have two main tools. You have substitution and you have elimination, okay? I suggest you learn one of them like thoroughly, deeply, and then forget about the other one. In this case, I will use substitution, see? So substitution is, for example, reaching y equals blah, blah, blah in terms of x, plugging that into the other one, so you end up with only one variable. Now, I know that's a lot of blah, blah, so let's see it in action, see? For example, equation 2 is already written as y equals something with an x inside of it, right? So if you take equation 2 and you plug it into equation 1, see what happens. So now you're telling me that y equals this. And you're going to be applying that for the first equation. So if you plug in the value of y into the first equation, you end up with 3 times my new value for y, which is negative 3x plus 18 equals 2x minus 1.5. Just so that no one gets confused, all that's happening here is that this got plugged in here. That's what happened. That's all that happened, okay? And notice, yes, this looks absolutely horrifying and nasty and everything, but you passed from having two variables to having only one. Yes, you have an x there and an x there, but you only have x's. Before you had x and y, now you have only x. So that means you can reach x equals an actual number, which is what we want to do. Ah, look at that. So from here, I only have one variable, I only have x. And that's the magic of system of equations. Through substitution and through elimination, you go eliminating variables. In this case, I eliminated y. And I used substitution. See? So, enough blah blah, let's get into it. From here, you can go ahead and distribute, ¿cierto? So you can do with 3 times negative 3 gives you negative 9x, plus 18 times 3 should be 30, 54, equals 2x minus 1.5. Okay? Seems good to me. Yeah. From here, I like to keep my x values positive, so I'm going to do plus 9x. Plus 9x, 54 equals 11x minus 1.5 plus 1.5 to both sides. 11x will have to equal 55.5. So here I just flipped it at the very end. I like having x on the left side. Here you can divide by 11 to both sides, and x has to equal, I'm pretty sure that's just 5.5, but let's double check. There's no reason not to. Yeah, 5.045. And checking the Voronoi diagram, it actually kind of makes sense, because if you look, 5 is right here, and where they intersect is a little bit to the right of that. So it makes sense that it's going to be 5.0 something. See? So your x value ends up being 5.045, right? If you want to do significant figures or values or whatever, you count 1, 2, 3, round it up or keep it the same, you round it up. So I'm going to leave my x value as 5.05. That it? And with 5.05 for your value of x, now you can just plug it in anywhere up there, either to the first or second. I'm going to choose to plug it into whatever the second one, see? So I'm going to plug into the second one, the value of x. I end up with y equals -3 times my value of x, which is 5.05, ¿cierto? Yes. Plus 18. So y has to equal whatever that is. So let's find out. -3 times 5.05. Yeah, -15.15 plus 18. So your value for y ends up being 2.85, probably. Quick maths, there is 2.85. Just double checking. So boom, this is the x value, this is the y value of this coordinate right there. See, so if I get really, really fancy, I would be saying that this is 5.05 and that is 2.85. Okay, so the coordinates of this office combining the x and the y is going to end up as 5.05 comma 2.85. I check visually with the graph, it makes sense. That would be for number 7, you guys. All right, just to show you the answer key, well, I always put it down in the videos, but anyways, here is the show that for part A. Here is completing the perpendicular bisector of AD, a vertical line with x-intercept 2.5, ¿cierto? And for C, there are my 2 solutions, okay? Technically, I guess I could have, rounded it up a little bit, this or that. I ended up with 2.85, ¿cierto? For using significant figures. Okay, so don't freak out. I know it's different than the 2.86, but that's because I'm using significant figures for this calculation, okay? It says to accept it, so don't worry. All is good over here. Ladies and gentlemen, that is for number 7. That is for Voronoi diagrams. I hope it helped, and I'll see you around. All right, you nerds. So check it out. We got that Ruhi, good old friend Ruhi, bites a scoop of ice cream in the shape of a sphere, and Ruhi has a very good eyesight, and so he tells you, yo, did you notice that this ice cream has a shape of a sphere with a radius of 3.4 centimeters? And he shows you that the ice cream is served in a cone, okay, and it may be assumed that 1/5 of the volume, okay, that looks kind of ugly, so let me go like this, 1/5 of the volume, okay, 1/5 of the volume of the ice cream is inside the cone. This is shown in the following diagram. So, first things first, what 1/5 is our good old friend Ruhi talking about? They are talking about the 1/5 of volume, which is hidden right over here, right? Like if you were to finish the sphere, it would look something like this, right? And then there's this 1/5 right there that is inside of the cone. That is what I mean by it. That is what it means by it, right? And so the remaining 4/5, which is everything that's kind of like in white, so everything that's kind of like in white is 4/5 of the volume of the ice cream. So that is what's happening when they're talking about the 1/5 volume of the ice cream that is inside of the cone. And so for part A, doop-de-doo, we need to calculate the volume of what thing? Of the ice cream that is not inside the cone. So, fairly simple, but you do have to take a very rigorous approach. So, of the things I highlighted, and this is a quick sort of reminder of the approach that I like to suggest, first identify buzzwords or important words, okay? After that, this is going to lead you, usually, right? This is going to lead you to the correct formula, and this will lead you to the correct procedure, okay? So, once you identify the buzzword and important sort of key concepts of the exercise that I highlighted here, that leads you to a formula, and from that formula, you embark upon the procedure, and it tends to be pretty obvious. Now, formula. I know you've heard that before. You've heard it in the formula booklet. Ladies and gentlemen, the day of the test, you're walking in with a couple of things. You're walking on with a pen, with a pencil, with, 2 years of experience of this thing called IB. Probably a lot of coffee, right? 2 years of experience, 2 hours of sleep, a whole lot of motivation to do well, and your graphing calculator and your formula booklet. Guys, the formula booklet, a very common mistake that people do is that they say, the day of the test I have all the formulas, like, I'm good to go. That's not good enough. You need to know what is in it, okay? Why is that important? Because once you start identifying these buzzwords and these important words like cone and sphere, you remember, I know I've seen that in the formula booklet somewhere. And so you're going to open up the formula booklet, look for sphere, look for cone, look for volume, okay? And eventually, you're going to find it around there, see? So here, for example, you have Actually, that is not very useful right now, but I know it's somewhere here. So volume, here it is. So boom, there you have the volume of a sphere, see? And so suddenly, this is the kind of thing that starts giving you the approach that you need, right? So it's not good enough to have the formula booklet. It's very important that you know what's in it. You identify some of these buzzwords like, I've seen that before. I'm pretty sure it's in the formula booklet. See? That is the level I need you to reach. And once you do that, you're going to be just fine. Got it? So again, back to reality, part A, calculate the volume of the ice cream, right? Now they did tell us that the ice cream is in the shape of a sphere. So really, this is calculate the volume of the sphere. Now, the volume for sphere, okay, we checked in the formula booklet, and it's this right there. It's 4/3 pi radius cubed. And they tell us that, I said it out loud, but r is the radius, see? Remember that this fancy symbol here is just pi, it's just a number, and you have it in your calculator. So pi is actually right below the clear button, right? So you can push second, and then this little sort of arrow. There you have pi. See, pi is an actual number. Don't worry about that. You can leave your answer in terms of pi, by the way. Just so you know, this would be for number 8, right? So for number 8, you can see that you can leave your answer in terms of pi. See? Oh, well, back in my day, you could leave your answer in terms of pi. Maybe not anymore. Maybe times have changed. Times will always change. Anyways, enough blah blah. We identified the formula. This is what we gotta do. All you need to plug in, the only thing you're missing is r for radius. And so what is the radius here? They literally tell you the radius is 3.4 centimeters. So from here, the volume of the sphere, you plug in an r equals 3.4. All right. And so if you put all of that into your calculator, or just to show the procedure, I suppose. So volume of sphere is 4/3 times pi times 3.4 cubed. See? Now you want to plug in carefully. So plugging in with parentheses tends to help with that. Put all of this into your calculator. So it ends up as, for the fraction, you can use alpha y equals. Press the first one. 4 divided by 3 times pi times 3.4 cubed. So bada bim, bada boom. The volume of the sphere, okay, is sphere. Dude, I cannot English today. Volume of a sphere equals 164.636. Guys, I'm going to say this right away. a common mistake is for you to say, here's the volume of the sphere, here's the volume of the ice cream. I'm just going to box in my answer, be done with it. There's a small mistake here. The small mistake here is that, yes, we found the volume of the sphere, which is the same as the volume of the ice cream, but they're looking for the volume of the sphere or the ice cream that is not inside the cone. And so remember, if 1/5, as we mentioned earlier, if 1/5 is what's inside the cone, right? So this is 1/5. Then everything else, which I'm putting now in, I don't know, pink, right? Then everything else has to be 4/5. I mean, makes sense, right? If you still don't trust me, you can do 1 minus 4 divided by 5. Or, sorry, 1 divided by 5, right? You end up with 4 divided by 5, right? It's the remaining part of the ice cream. All right, enough blah, blah. Let's get into it. So this is, you can think about it as the total volume of the sphere. If you want to find the volume of the sphere that is not inside the cone, then we're talking about not inside the cone, what I put earlier in pink. So it's, if it's 4/5, then for finding 4/5 of it, right? So 4/5 volume of the sphere, all you have to do is take your answer from before and find out what is 4/5 of it, quite literally. So you take your answer and you're going to multiply it by 4/5. Bada bam, bada boom, for 4/5 of volume of the sphere. Or also, if you want to, maybe get more fancy, you say volume ice cream outside cone. Your final answer has to be 131.7089682. And if you were to consider significant figures because you're a cool kid, you count 1, 2, 3. Round it up or keep it the same, you round it up. Do not forget your units. These are in centimeters, so you would call this centimeters cubed. All right? Checking your answer just so that you believe this guy on the internet. If you do significant figures, it's 132 like it shows there. There are the units, centimeters cubed, and the long answer is 131.708. There's the 0.708. See? Anyways, enough blah blah. Part A is pretty simple, just gotta be organized. And I think it's a good opportunity to explain the procedure that I like to suggest. Identify the buzzwords, go to the formula booklet, or think of a formula, and that is going to be the biggest hint for your procedure. Okay? That's for part A. Then, our good old friend Ruhi takes another good look at the ice cream and say, wow, did you realize that the cone has a slant height of 11 and the radius of 3? And that the outside of the cone is covered with chocolate? Man, it would be excellent if the IB, Ruhi says, would ask us to calculate the surface area of the cone that is covered with chocolate and give her an answer correct to the nearest centimeters squared. This is fairly simple, but we do have to once again be rigorous in our approach. The first thing I suggest is that if you get new information, put it into your diagram, okay? Make it visually appealing. It's going to help you. So here they talk about a slant height. Okay, so it's the part of the height which is slanted. It has like a little bit of an angle. So this right here we're going to call L, which is the slant height, is 11. And they also tell us that the radius, which I will be putting in, I don't know, whatever, in blue, this radius is 3 centimeters. So of this cone, which is just this figure here, ¿cierto? So this is the figure of the cone. The radius of that guy is right here. Okay? Now, there are two main things they can ask you in terms of geometry or whatever. See? There's usually two types of exercises. It's either like a volume exercise or a surface area exercise. Right? Volume is pretty straightforward. You can think about like filling up your shape with water. That is the big question of how much volume. Okay? for the surface area, the example that I like to give, which is actually the same one as this exercise, is dip it in chocolate. How much is covered? How much is covered is exactly what they mean by surface area. It's the area of your surface. How much of it gets covered by chocolate? Now, in this case, there's a small observation we have to do. See? They tell you that the outside of the cone is covered with chocolate. Okay? This could have been a cone where it's covered on the outside and also on the inside. See? But in this case, they tell you that only the outside of the cone is covered with chocolate. Okay? So, we need to find the surface area of the part of the cone that is covered with chocolate, which is like the curved part of the cone. See? Remember, a cone looks like this. Right? Actually, let me make a little bit of a better drawing. A cone looks like that. See? It's just that in this case, it's, well, flipped upside down, but a cone looks something like that. Okay? So, a cone has two components. Technically, it has like three. On the one hand, it has this circle down here. See? Which also has a radius, this or that, right? The second thing, yeah? So the second thing is going to be that it has a height. And the third thing is that it has a slant height. Okay, just so that we understand what we're talking about here, it has the slant height right there, which is the same slant height as right here, actually. See? So one thing is the height, the other thing is the slant height, and it has a circle. Yeah, why does this help? It actually doesn't help for much. I'm just telling you what a cone is. Some people don't have it clear, so I'd rather clarify it. See, this is a cone. This is a right-angled cone because it goes all the way up. See, with a right angle. Yeah. So, by now, you should have heard the word cone like a million times. See, so the biggest buzzwords here are cone and surface area. So, go to your formula booklet and find anything you can related to a cone. You're going to find two things. Look at that. You have two formulas. You have one formula which is for volume of this famous cone, and another one that is for, look at that, the area of the curved surface of the cone. So let me write this somewhere around maybe here. See, so area of curved surface of the cone is big A, right? Because that is how they express it. Big A equals pi RL equals pi RL. I'm going to put a big L here just so that we understand that it's an L, okay? Yeah, so area of the curved surface of the cone is pi times R times L. Do you have, what do you need? You already have pi because it's in your calculator. Do you have R? So pi we have, right? R, they tell us earlier, is 3. And L, which is for the slant height, ¿cierto? L for the slant height is right there, 11. So, this isn't hard at all. So the area, the surface area, I should say, the area of the curved surface of the cone, so the surface area of that outside part is just going to be this formula here. It's going to be area equals pi times R times slant height L. That's literally it, you guys. See? So for part B, you're going to plug that in. Clearly, you end up with 33 pi, ¿cierto? And what is 33 pi? 103.672. So, again, another small mistake some people can do. They say, so my answer for B is 103.672 centimeters squared because we're talking about surface area. Easy peasy, good to go. Yeah? The small mistake here is that you should always need to read carefully what they're actually asking for. So yes, they want the surface area of the cone that is covered with chocolate, but they also want it to the nearest centimeter squared. So all you have to do here is evaluate this number, which is to the left of the decimal, and ask yourself, do I round it up or keep it the same? You round it up. So your final answer has to be 104 centimeters squared. A little bit of a longer explanation, but I did want to be very specific on what the procedure is and how you reach it. Okay? So the final answer, I'm just showing you over here, is clearly 104 centimeters squared. Ladies and gentlemen, an exercise that is not that hard, but you do need to visualize it a little bit and just be organized. See? It was extremely easy. You literally just had to plug in over here, right? The only but that I would mention is that maybe some people get lost with like, oh, dude, I have no idea how to calculate the surface area of a cone. Well, that is why buzzwords are important. Knowing what's in your formula booklet is important. It's a very easy exercise once you realize, dude, it's in your formula booklet. You just have to plug it in and that's it. See? So guys, keep it in mind, a lot of these exercises become much easier once you start using the formula booklet more. So use the formula booklet, study with it. Okay? That's the biggest tip I can give you. Ladies and gentlemen, that is for number 8. All right, guys, number 9 is a normal distribution problem. Now, I'm going to say right away, these exercises tend to be very easy. It's just that people freak out on the different tools that they have, okay? Once you understand the tools that you have, which are mainly 3, or actually, in my experience, it tends to be 2, okay? Then you're pretty much good to go, okay? So, what is a normal distribution? What are my tools? What's happening? Yeah? So before even reading the exercise, we need to understand what are the tools for the normal distribution. The tools for the normal distribution have to do with, well, understanding how it actually works, like in a graphical sense. And then we have this thing called normal CDF. And then we have this thing called inventory normal. Okay, that's pretty much it. All right. I'm yet to see normal PDF be used, so I think I'm not even going to mention it for this video. Okay. So where do you find those in your calculator? In your calculator, because we're talking about a distribution, then you need to go ahead and press that distr button that's in blue on top of vars. So you're going to be hitting second and vars in order to press distribution. And these number 2 and number 3 are for the normal distribution. Okay, down here you have for the chi-squared distribution, for the t distribution, there's a bunch of different stuff. For us, we will only be caring for now about the normal distribution tools. Okay, I guess I'll mention PDF just because it's here, but the intuition is the following. I am yet to see normal PDF be used, so I'm going to mention it just to mention it, but really most of the time you're not going to use it, in my experience. ¿Vale? So the 3 main tools, and I suggest you write this down somewhere, okay? Normal PDF is like probability of exactly this x. Okay, and if I were to draw something maybe more visually, it would be a normal distribution, and you're finding the probability of landing exactly right here. Okay, for normal CDF, it's very similar, but it's probability between this. And so this one's a little bit different graphically. Okay, it looks something like this. You have your normal distribution, and you're saying if I have an x value here and an x value there, what's the probability of landing this? Okay, so maybe it's like, I don't know, this is for mango trees, right? So you have a mango that weighs 2, you have a mango that weighs 3. What's the probability of picking a mango that weighs between 2 and 3? Okay, that's a sort of thing that you use for normal CDF. Notice, normal CDF and normal PDF, both of you, what do they give you? They give you a probability. So normal CDF and PDF are giving you a probability when you give it an x value. So that's very important to acknowledge. For normal CDF and normal PDF, you're given x. So give x, get probability. Okay, and when I say x, it's literally something down here. Okay, so you give an x, you get a probability. For inventory normal, or inverse normal, I don't know why I say inventory, to be honest. I'm pretty sure it's inverse normal. What happens here is actually that you give x, sorry, you give probability, you get x. So this is actually a little bit different. So if I were to show this kind of visually, what's happening is that you're telling it, yo, like what is my lowest 30%? You can think about it that way. See, so you can say, okay, this right here gives me 30%. What is my x value there? Okay, so you know what's in green. You know that this is, I don't know, 30%. And you're trying to find the x value where it ends at. See? Once we understand these three tools, everything turns out to be much, much more easy to like go over. See? So keep in mind, for the normal CDFs, you give an x, you get a probability. For the inverse normal, it's a little bit different. You give a probability and you get an x. All right? So now that we understand the tools and also just the intuition of a normal distribution, that's the last thing I forgot to mention. Guys, a normal distribution, there's two main things you have to acknowledge, okay? The first one is that right down the middle, you have your mean, okay? You have your mean, you also have your median, you have your mode, you have everything here. But for us, focus on that you have the mean. And the second thing you have to establish is that from the middle to the left, you have 50% of your data. And from the mid, actually this is a very small drawing. So here's your mean, ¿cierto? And from here to the left, so all of this over here, right, is 50% of your data. And from here to the right is your 50% of your data as well. See? So the main thing we have to catch from that is that it's symmetrical. Okay? It's symmetrical. And that's going to come into play down the road. Yeah? So that is the general overview of normal distribution. Once we understand that, solving this becomes much more easy. Yeah? So now and only now I will start talking about number 9. Number 9, we have that the lengths of the seeds from a particular mango tree are approximated by a normal distribution with a mean of 4 centimeters and a standard deviation of 0.25. A seed from this mango tree is chosen at random, and for part A, we need to calculate the probability that the length of the seed is less than 3.7 centimeters. And so the first thing you need to establish for these kind of exercises are, notice up here, you either give x and get a probability, or you give a probability and get an x. So which of the two scenarios are we in? We're in the scenario where we need to calculate the probability. So clearly, I need to give x, get probability. So which are my tools that give x and get probability? We have normal CDF, and we have normal PDF. Now, normal PDF is for exactly one value of x. Yeah, and normal CDF is for between two values of x, right? Here, it's saying you need to find the probability of the length of a seed that is less than 3.7 centimeters. So it's 3.7 centimeters and everything below that, right? So it's not exactly 3.7 centimeters, it's 3.7 centimeters or below. So it has to be normal CDF, okay? Now, guys, I know that a lot of you are probably thinking right now, dude, you cannot expect me to memorize all of this, much less for the test that I have tomorrow. See? So I will tell you the following. Guys, it isn't about knowing all of this by memory. It's about sort of remembering it. See? So the day of the test, you should first look at this problem and say, okay, it's a normal distribution problem. I know I have these tools and I know where to find them. Okay? Maybe you don't remember exactly what they do, but that is why you need to go piece by piece. So you know they're in your calculator, you know they're in the distribution section, and you know that it's the first three. Got it? Maybe you don't remember which one is for a range of x values, which is for an exact amount of x values, but that is why you go piece by piece. Press each of them and go remembering, okay? For example, normal PDF, if you press it, well, what does it ask for? It asks for one x value, okay? And then it asks for the mean and the standard deviation. Okay, that's another thing. This is the mean, and this is the standard deviation. Okay, so that's all you need. You plug in one x value. So normal PDF is for the probability. I give 1x, and I get the probability of landing that 1x. Okay, go ahead and press normal CDF. Here you have a lower and an upper. So this is my lower x, this is my upper x, and again it asks for mean, again it asks for standard deviation. This is for a range of values. And last but not least, for inverse normal, you can see you plug in an area, and this guy online told me, if I plug in a probability, I get an x. Well, this probability here that I'm writing, ¿cierto? It's the area under the curve. The area under the curve is probability. Okay, that's another thing I should have mentioned. In this context, area is going to be probability. Okay? Yeah, so clearly I need to use normal CDF. So I go ahead and I go back to our normal CDF. Notice how a lot of this is really just understanding the tools, you guys. Yeah. So I go to normal CDF. Here I have lower and upper. On the one hand, most calculators will put for your lower something that looks like that. Now, what is it doing? What is happening? Really, this is like -1 to the power of like a lot. ¿Cierto? So what's happening? It's a this is the thing. That number right there is a very big negative number. Okay? Why would we want to put a very big negative number? Because right now, this is my context for part A. ¿Vale? Right now, you know that the mean is 4. Okay? And they're asking, what is the probability of picking the length of a seed that is less than 3.7? So 3.7 you know is a little bit to the left of your 4, ¿cierto? And you need to find the probability of landing, or picking, I mean, a seed that is right here. So clearly your approach has to be, okay, so your upper x clearly has to be 3.7, but what do you put for your lower, right? Oftentimes this plays off of context, see? So for your lower, because we're talking about the length of seeds, you can't have a negative length, so you can just put 0, yeah? But what I also suggest that you do is that, well, if you put the lower as 0, or you put it as -1, it's still going to work, because it's still going to scan where it needs to scan, ¿cierto? So that is why a lot of people, for this sort of exercise, they put lower -100, just to make sure that you're capturing the area that's in green. See? Now, given the context, you can just put it as 0 and it's going to work. Yeah, because there aren't any negative distances for seeds. Like, that doesn't make sense. Yeah? But just so that we all feel a little bit safer, for your lower, just put a very big negative value. Okay? For the upper, we're going to put 3.7. The mean we know is 4. The standard deviation we know is 0.25. Go ahead and paste. This is giving me the area that's in green. Yeah? Just in case you don't trust me, because you shouldn't trust people on the internet, let's be honest, you can change this to 0. That it? And look at that, you end up with the same answer. And that's because it doesn't matter if you tell the calculator, yo, here's the 0, or yo, here's the -99999. It's still going to do the same procedure, which is, yo, let's take this lower bound, let's take this upper bound, and scan the area that's in green. It's still going to capture the same area, okay? So whatever floats your boat, whatever makes you feel safer, put a very big negative value, or given the context, you can just put 0, okay? Do whatever floats your boat. I'm not going to stop you. You end up with the same answer, yeah? So the area that's in green that I just found out here is going to be 0.1150, right? 69. If you count significant figures, you would be counting from this guy right here. Do you round it up or keep it the same? Keep it the same. If you want to turn it to a percent, it would be 11.5%. Okay, so clearly my diagram's not drawn to scale, but the idea is what matters here. See, so for part A, that would be my answer. So the probability of capturing a seed less than 3.7 centimeters, I use normal CDF. There it is, 11.5. Yeah. If you're worried about showing your procedure, all you really need to do, which is what I did the day of the test, and I got full credit, so no worries there. Literally write normal CDF. Actually, if you write this right here, you're going to be fine, because that is showing your procedure. If you write your answer as normal CDF 0, 3, 3.7, sorry, 4, and 0.25, whoever is evaluating you knows, okay, that means this is the lower they put, this is the upper they put, this is the mean they put, and this is the standard deviation they put. They're going to understand it. They're going to understand it better than you do, okay? I'm just saying it's important you write this out so that you get a method point. The answer key usually has method points established somewhere. In this case, it's you need to show that you understand you're dealing with a normal distribution. See, there's a lot of different ways to sort of express this, and I assure you that putting it like this will give you the point. Putting a diagram is even better, okay? Yeah, you guys, that's just so you get full credit, that's all, yeah? Then they tell us that it is known that 30% of the seeds have a length greater than k centimeters, and to find the value of k. So part B is a little bit more creative, okay? So you should already be thinking, I'm getting a probability, I need to get an x value, okay? The thing here is that you need to think about it before you do it, okay? Because a lot of people would go straight to inventory normal and straight to plugging in 30 and just putting out the answer, see? It's not so much like that. See, first visualize it. I highly suggest you draw diagrams for this, okay? So, here you have your diagram. Here you have 4. And as I mentioned earlier, half and half is 50%. So, if it is known that 30% of the seeds have a length greater than k centimeters, because we're talking about greater than, then we're talking about the top 30%. So if we're talking about the top 30%, we're talking about, boom, this k value right there. So from here to the right is going to be 30%. Now the issue is the following. Inverse normal, depending on the calculator, but at least for our calculator, most calculators, inverse normal works from left to right. So let's understand this for a second. A very common mistake is that people go to inverse normal from here. They put the area, which is 30%. And I'm actually going to show 2 common mistakes here. So the first one is putting area as 30, putting the mean, putting the standard deviation. This is the first common mistake. People press enter, and it says error domain. What's happening here? What's happening here is that when you put area of 30, okay? When you put area of 30, well, this is technically like in percents and stuff like that. So area of 30 means that you're asking for 30,000%. So really what you should be doing is asking for 30%. Okay, so that's a common mistake. See? So that's common mistake number 1. Common mistake number 2 is actually interpreting it as like thinking in 30%. See? The thing is, if you go ahead and paste this, okay, now we just trolled because there's 2 equations up there. See? If you plug it in like this, your k value is 3.86. Like what I just found. And this is incorrect. Because clearly, since I'm talking about greater than, or in other words, the top 30%, well, why is my k value to the left? What's happening here? And so what happened here is that, inventory normal works from left to right. So that means that it found, or it counted, you can think about it, it counted up to 30% and gave you that k value. For the k value that's in the top 30%, then it has to count all the way until reaching here. And so we're talking about the top 30%, because the normal distribution is perfectly symmetrical, then that means that actually what I need to plug in, because it reads from left to right, I need to plug in the 50 right here and the 20 right there. Because if all of this is 100%, I need to do 50 plus 20 in order to reach that 30. So actually for inverse normal in this case, you need to be plugging in 70%. That makes a little bit more sense. That is where the IB catches you. See, the tools are not that hard to acknowledge, to understand, to use. I mean, with this little summary, you're good to go. But they do try to catch you with these small sort of details, okay? So again, drawing a diagram is usually the ideal here. Clearly, my value for k has to be 4.1311. And if you count significant figures, you count 1, 2, 3 to round it up or keep it the same. You keep it the same. So k has to equal 4.13. Don't forget the units. We are talking about centimeters. All right. So that is a small sort of twist that they might give you for inverse normal. All right. Get familiar with the tools. Get familiar with its different sort of ways in which they try to catch you. drawing diagrams is going to help a lot. See? Notice that your compass for most of these problems, like where you should not get lost, is boom, from your mean. The mean is 4, that's the middle. So the moment I saw k of 3.8, like I saw earlier, I said, that's definitely not the top 30%. That's the lower 30%. So careful, okay? Your compass is usually going to be your mean. That's going to help you interpret whether your answers are correct or not. Keep it in mind. I highly suggest it. For part C, they tell us that for a seed of length d chosen at random, this is true. And I'll help you interpret that in a second. See? Find the value of m. So, what the heck is this even asking for? See? This is very similar to normal CDF. Okay, it's just written in an extremely fancy way. So normal, it's telling you that if you put a lower of 4 minus m and you put an upper of 4 plus m, you're going to end up with a probability of 0.6. And so the hard part here is identifying, okay, how much should I move to the left? How much should I move to the right in order to get that 0.6? Now notice, you're doing minus m and plus m to both sides. And this has to equal 0.6 or 60%. So visually, and this is what I mean by drawing diagrams is going to get you very far with stuff like this. See? So you have the middle with 4, ¿cierto? You know that on both ends, it's perfectly symmetrical. So this is 50% and this is 50%. Yeah, we know that already. What's happening here is that basically, because you're starting from this 4 on both ends, ¿cierto? So you're going a little bit to the left with m and a little bit to the right with m, shifting the lower and the upper. That means that at some point, you move it enough so that this is 60%. And that is the big hint you have to understand. You do 4 minus m, you do 4 plus m, and the lower that comes from here and the upper that comes from there, the area that you end up with is 0.6. It's 60%. And visually it looks like this. So, okay. Clearly if I try to plug in some area or some probability, this might work. So think about it. If this right here on the middle in pink is 60%, how much percent should be over there? If you said 40%, there's a small mistake with that. What's the small mistake? If you say that that area that I'm putting in sort of purple has to be 40%, well then how much is this in red? Are you going to tell me this is 0%? Nuh-uh. Clearly what you end up with is actually that because in the middle you have 60 and in its entirety you have 100, well, if you do 100 minus that 60, you end up with 40. So that means that both ends have to equal to 40, and because normal distributions are symmetrical, like I mentioned earlier, boom, that means that both of them have to be exactly 20% and 20%. Because of this 40 that's remaining, you divide it by 2, 20% on both ends. So that's the big hint that's happening here. See, because the middle is 60%, the left and the right has to be 20%. All right, but mister, how the heck does this help me find m? Well, if now you know that that 4 minus m, this is the thing. 4 minus m is right at the lower 20%. And inverse normal reads from left to right. Kapow! So now you can plug in inverse normal with an area of 20%. 0.20. So boom. That means that 4 minus m has to be 3.789. 59, right? 59, the whole number, 594692. So 4 minus m has to be this. So if 4 minus m equals 3.789594692, that means that you can do plus m to to both sides. So 4 equals 3.7895946992 plus m. You want to get m alone, so minus 3.7895946992 to both sides. You probably know where this is going for by now, but you end up with m equals basically 4 minus this. And that has to be your value for m. So m has to equal 0.210 40 5308. If you think in terms of significant values, you count 1, 2, 3, round it up or keep it the same, you keep it the same. So m has to equal 0.21. Now they're asking for only the value of m, so we're good to go, but maybe some other day they ask for the actual bound. So your lower bound would be this, and your upper bound would have to be 4 plus this number right here. All right? It's not what they're asking for in this exercise, but maybe for tomorrow's test that you're studying for at the last minute, it might be. Okay? So just so you know, that is the general intuition that I can share with you for the normal distribution. Guys, I think this is an excellent sort of exercise to study from. All they're really ever going to do is ask variations of normal CDF and variations of inverse normal. I think I've seen it like maybe once normal PDF. They don't usually ask that, okay? They get a little more creative than that. So, you guys, that is for number 9. The tools are not that many. You do need to be familiar with them. And not only the tools, but also how the normal distribution works. I highly suggest that you think about this in terms of diagrams. It makes everything easier, especially for part C, okay? So here's the answer key. I always put at the end of the video anyways, but just so that you trust this guy online, there's your value for K, 4.13. Here's your value for M, see? So, ladies and gentlemen, and here's the value for A, see? Ladies and gentlemen, that is number 9. I hope it helped, and I'll see you around. Take it easy. All right, so number 10 is pretty much a quadratics problem, which is fairly easy in my opinion, but context-wise, it can get a little bit confusing, like what they're actually asking for. So, for number 10, we have that a player throws a basketball, and the height of the basketball is modeled by this right here, where h is the height of the basketball above the ground in meters. Units are important for our answers, and t is in time in seconds. So h for height and t for time. For part A, we need to find how long it takes for the basketball to reach its maximum height. So the big buzzword here is the word maximum. So essentially, I did mention this is a quadratics problem, but let's also talk about how I know that it's a quadratics problem. And this first step is very important to acknowledge. So a quadratic, its general sort of function is ax squared plus bx plus c. Whenever you have something like this, you have what we call a quadratic. Now guys, a quadratic, you might have also heard it as a parabola. And the cool thing about the quadratic or the parabola is that it can look like this, or it can look like this. Okay? So it's either like a U facing up or a U facing down. The other way that some people memorize it is that it's either like a smiley face or it's either like a sad face. Okay? So there you have a quadratic. And in this case, there's a lot of different stuff you can learn about a quadratic, and that we're kind of gonna do it on the fly. See? So depending on the values of A, B, and C, you can identify a bunch of different stuff about this quadratic. The first thing I will explain is that the value of A, if it's positive, you have a smiley face like this guy here. If A is negative, then you have a sad face like this one here. And so for part A, it makes sense that they're asking for maximum height because my value for A is negative. My value for A is negative 4.75, which is something that is less than 0. And so because it's negative, then you have a sad face. And if you have a sad face, notice you have a maximum. If you have a happy face, you have a minimum. So that's the first observation I'm going to make. It makes sense that we're looking for a maximum because our parabola looks something like this. Okay? The second thing I will mention is that a parabola, the other cool sort of function that it has, okay, is that no matter how it looks or how it's drawn, it has this thing called the axis of symmetry. And so when something is symmetrical, that means it is equal like on both ends. Okay? So for example, the axis of symmetry runs right down the middle. And it's no different than like you have, imagine your own face, see? And imagine you draw a dotted line that runs through your forehead, through your nose, through your mouth, all the way down. You have an axis of symmetry. Like the distance of your eye to the left is the same as the distance from that axis of symmetry to the eye on your right. And quadratics are no different. Like the distance from here to here, I know it's not drawn to scale, but the distance from here to here is equal. Like say maybe they're both 2. From here to here, maybe they're both 3. From here to here, maybe they're both 4. And the awesome thing about this, or why I'm mentioning it in the first place, is that the axis of symmetry, I don't know why I put symmetrical. Parabolas are symmetrical. Right now I'm talking about the axis of symmetry. Okay? So in an axis of symmetry, the cool thing about it is that it has to run through the max or min. The other thing you might have heard of in class is that it's the vertex. So the axis of symmetry goes to the vertex, and the vertex is either a maximum or a minimum, right? So you can have a parabola that goes like this, or a parabola that goes like that, and the axis of symmetry on both is going to be right there. And it's going to give you information of where the vertex is. So here you have, for example, vertex 1, and here you have vertex 2. And the cool thing about vertex 1 is that it's a minimum, and the cool thing about vertex 2 is that it's a maximum. So, in conclusion, a vertex can be either a maximum or a minimum. You know whether it's a maximum or minimum either visually or by seeing the value of a. So if a is negative, you have a maximum. If a is positive, you have a minimum. And yes or yes, the axis of symmetry cuts through that maximum or minimum. So the axis of symmetry is going to help us for finding the maximum height. So in conclusion, or conclusion number 2 maybe, when you read maximum height or minimum height, you have to be thinking axis of symmetry will give me the x value of vertex, and the x value of the vertex will help you get the y value of vertex. Okay, that is like the procedure we will go for. Once you find the x value of the vertex, you use that to plug it in back into your function and get the y value of the vertex. So let me make a little bit of space. It was a little bit of a long introduction, but also a very necessary introduction. So our game plan is finding the x value of the axis of symmetry is the same as the x value of the vertex. And through that, I get the y value of the vertex, which helps me find the maximum height. Now, for axis of symmetry, okay, so AOS will be for axis of symmetry. For the axis of symmetry, there's actually an equation. So the equation for axis of symmetry, which is, I don't think it's in your formal booklet. I'm pretty sure it's not. So for quadratic, we have 2 equations. Look at that. So in your formal booklet, you will find out that for the axis of symmetry, the equation is negative b over 2a. So the axis of symmetry, which is just an x value, will be negative b over 2a. And in this context, what is a, what is b, what is c? Well, let's take a closer look. A clearly has to be negative 4.75. B clearly has to be 8.75. And c clearly has to be 1.5. Guys, a classic example is that people say a is negative 4.75 t squared, or that b is 8.75 t. And there's a small mistake here. It's a common one, but it's a small mistake because your a, b, and c is simply what is defined by what is next to it. So your a is whatever is next to x squared. Your b is whatever is next to x. And I can mention the same thing here. So whatever is next to t squared is your a, whatever is next to t to the power of 1 is your b. So here are my values for a, b, and c. And so if I go ahead and plug into negative b over 2a, I end up with x equals negative 8.75 divided by 2 times negative 4.75. And so, well, really I can just plug this into my calculator and see what happens. Because I'm plugging into a fraction, just to make it more organized, I suggest you press alpha, y equals, and then the first one. Okay, this helps you for putting in fractions. And so the first one, voila, looks like this. Plug in carefully, don't mess it up. These are easy points. Always use parentheses for plugging in multiplications. That's my suggestion. Bada bim, bada boom, there is my value of x. So my axis of symmetry is an x value, right? Which is also the x value, as I mentioned earlier, of the vertex. So that is also another thing I should maybe clarify. Whenever you use this equation for the axis of symmetry, you can also think about it as the x value of the vertex. Okay, it's the same thing. The axis of symmetry is the x value of the vertex. Once you establish that, this becomes so much more easy. So the axis of symmetry is the x value of the vertex, which gave me 0.921, 0526, 0526. If I were to do 3 significant figures, I would count 1, 2, 3. This one, do I round it up or keep it the same? I keep it the same. So significant figures, you can put the whole number, but for now I'll put significant figures is 0.921. And so the procedure that I showed you was find the axis of symmetry. This is the x value of the vertex. Use this for the y value of the vertex. And this next step is actually very simple. It's just very common for us to get confused what we're doing, why we're doing it. So right now, you have some x value, see? And if I were to plug in, so the equation of the parabola is negative 4.75t squared plus 8.75t plus 1.5. So if right now I were to plug in the x value of the vertex, so 0.921, that means I end up with an equation that looks like this. For each t value, I'll be putting that 0.921. All right? Now, this probably makes sense to a lot of you. You've probably seen it in class, but I will be in charge of explaining why. So, the big thing you're asking your function when you do this is, when x equals 0.921, what is my y? Okay, don't get lost in the sauce. This is the procedure. When x equals 0.921, what is my y? And in this context it's basically like when, or better said, if my x value of the vertex is 0.921, what is its y value? Okay, these two sentences are pretty much equivalent to each other, see? But I do need you to understand the procedure that is going on behind it. Enough blah blah, let's go ahead and plug in. So, if I plug in, I end up with negative 4.75 times the parentheses that I told you earlier, plus this. I'm just plugging in what's here, guys. Okay, don't get lost. Plus 1.5. Aha. So the y value now, or better said, when for my function of h, right, when I plug in 0.921, I end up with 5.5296. 0.5, right? And if I were to do significant figures here, I count 1, 2, 3. Do I round it up or keep it the same? Clearly, I round it up, so I'm going to leave it as 5.53. So this right here is now going to be y value of my vertex. So, look at that. I just identified let me use a brighter color for this. So I just identified the x value of the vertex, which is 0.921. And I also just found out the y value of the vertex, which is 5.53. So my vertex basically has to be at 0.921, comma 5.53. And I know that because my a value is negative, right? Because a is negative, that means I'm dealing with a maximum, right? If you have trouble remembering that, remember that if it's negative, it's going to be a sad face, okay? So it's clearly a sad face has that maximum right there, see? So instead of vertex, I'm actually going to rename it as maximum, okay? Now, context. What is my x? What is my y? Because I have it as h of t, let's remember that the original version is f of x. So whatever is inside the parentheses is x, whatever is outside is y. So clearly x is going to be time, y is going to be height. So for the maximum height, it's just the y value of my vertex. So for the maximum height for part A, I would be saying 5.53. Do not forget your units, meters. All right, so that is for part A. Pretty straightforward. Quadratics are exciting. Yeah. Then for part B, we have that assuming that no player catches the basketball, find how long it would take for the basketball to hit the ground. All right, this one also gets interesting. And I think it might make more sense if I actually explain it through Desmos. So let me go ahead and plug this into Desmos just so that we can all see it a little more, friendly. So if I go ahead and plug in my function into Desmos, and I know you might be thinking, dude, the day of the test, I can't use Desmos, but I'm trying to explain an idea here. See? So x is time, y is height. And for part B, they're asking, assuming that no player catches the basketball, find how long it will take for the basketball to hit what thing? To hit the ground. And so where is the ground in terms of height? Is the ground, up there? Is the ground here? Is the ground there? No, my dude. The ground is obviously wherever the height is 0. Wherever the height is 0 meters is going to be the height. So, assuming no one catches the basketball, the player threw it up here like this. And then where does it touch the ground? It touches the ground right there. And yes, I'm showing you the answer, but now we're going to figure out how to actually do it. See? So the one hand, I need you to really visualize and conceptualize this. For part B, if you're talking about hitting the ground and your height is your y, then all you're really finding is what we call the x-intercepts, or the zeros. Okay, it's the same thing. It's important for me to introduce the idea like this because quadratics are not that hard. I mean, for quadratics, usually what I see, okay, is that they're asking stuff like the max or the min. Okay, they're asking stuff like the zeros or the x-intercepts. Okay, they're asking stuff like the y-intercept. The tough part is that the IB loves to disguise this. When they're talking about, when they ask about maximum height, that one's pretty obvious. But when they're talking about hitting the ground, it's disguised as x-intercept. See? And so that's the kind of stuff we need to start catching on to. That's why I'm presenting it to you in this way. So for part B, how do you find the zeros of this guy here? So let me rewrite my equation right there. H of t equals negative 4.75 t squared plus 8.75t plus 1.5. So the three main tools that you have, okay, is technically on the one hand, okay, you can do factoring. All right, it's just that factoring here is a little bit hard. The other tool you can do, that's actually in your formula booklet, which is the other formula for quadratic, is this right here. Solutions of a quadratic equation really just makes reference to the zeros, okay? Notice how this equals 0. Why would it equal 0? Why would I make this equal 0? Because if that equals 0, then you're basically asking your function, when y equals 0, what is x? it's a little bit backwards to what we did earlier where we gave an x and found a y. Here, if you equal your quadratic to 0, you're saying when y is 0, what is x? And so you will be finding the x-intercepts when you do that, okay? All you're really plugging in is some x, you're going to find some x when y is 0. Okay, that's what you're doing. That's all that's happening here, okay? Anyways, back to the tools. You have the factoring. You have this thing here, which is I think we just called it quadratic formula, okay? So we can use the quadratic formula, or we can use graphing, okay? I think most people use quadratic formula. It's what I show in most of my videos. Today I'm going to show how to do the graphing, see? Feeling a little bit spicy, let's see what happens. So you know you don't have decimals, you do have your graphing calculator. So how do you solve it by graphing? Well, go to y equals and plug in your equation. So if you go ahead and plug in your equation, you might be thinking, I don't have t. Okay, but t in this context is really just an x, ¿cierto? So that means you can put it as negative 4.75x squared plus 8.75x plus 1.5. And from here I press graph, and it's pretty likely that it's not going to show up just because your window is not aligned. In this case, my window is aligned, but I'd be willing to bet that half of the world watching this did not have a nice window. So I'm going to give you tips and tricks on how to get a good window. See? The main tip is that you can go to zoom, scroll all the way down, and do zoom fit. Okay? Zoom fit usually helps you see like the key points and stuff like that. And so in this case, the key point that it seems to be trying to show me are the x-intercepts. And so this by itself, although it might look kind of nasty, it is a very good starting point, believe it or not. So on the one hand, clearly I need to put more y values so that this is easier to see. And all these negative y values is useless information. The other thing that might be relevant is that given the context of the problem, you only care about when the player catches the basketball, which is going forward in time, not backwards in time. So with all of that, because I'm going forward in time and not backwards in time, I can make my x minimum be 0. I don't care about negative values in this case. My y value does not have to be negative because I don't care about negative heights. So I'm actually going to put y min of maybe -2 just to see it better. My y max, well, because of zoom fit, I was able to see the maximum. I also know that the maximum is at 553, right? So I'm going to put a y max of, I don't know, 7 just to see it a little bit better. See? So it's that kind of stuff that helps you regulate how your window should be. The zoom fit was an excellent starting point, but the information that you already have from the problem helps you out. See? So from there, instead of pressing enter, you actually just press graph. Okay? And yes, there are useless x values here, but for our intents and purposes, this is good enough. What is good enough? Being able to see the x-intercept, which I clearly do. So that right there is when I need to find the zeros. See? So you can actually do second and then hit trace in order to press calc. So with that, you have a bunch of different stuff that helps for the quadratic, including the max or min actually. I could have showed you how to solve it with that as well. In this case, I press 0. See? Now notice what it asks for. It is asking for a left bound, and later on it's going to ask for right bound. So let me explain that for a second. This quadratic right here that you see on screen technically has 2 zeros. It has this one and this one, right? And so if I were, this is the main idea. If I were to plug in a left bound of -3, which is this green one, and a right bound of x equals, I don't know, 3 as well, what your calculator is going to do, okay, is that it's going to basically scan between the green and the purple for any zeros, for any x-intercept. Clearly, it's going to find 2 of them, right? And so you need to be able to specify which one you actually want, which is why at the end of the process, it asks you to guess. But for us, just to keep it a little bit more friendly, we're going to keep our x or our left bound maybe right here, maybe at 1, right? And then we're going to, at 3 is fine. See, so now we're going to scan only this x-intercept. It's the only one we actually care about. So the left bound, we're going to put it anywhere to the left of my 0, so that's this is probably fine. And my right bound is going to be somewhere to the right of my 0. That's probably fine. And then guess. See? Guess is not that your calculator is dumb and needs to know. Guess is that you are specifying which 0 you want. Okay? So that's what I meant. I suggest just keeping the bounds to the 0 you actually want. But the guess function, that's its role. You're specifying which one you actually want. See? So I press it over here. That is my 0. 2, 0. So over here, got a little bit messy, but for part B, basically, I found that my 0 was 2, 0. See? And so if my 0, my x-intercept, is 2, 0 for part B, I can say, how long would it take for the basketball to hit the ground? It would take 2 seconds. Because if my x-intercept is 2, 0, the 0 is the height. As I mentioned earlier, y is height. And the x is going to be the time. So 2, follow the units. Units is seconds, so 2 seconds. See, that is for part B. Later on, they tell us that another player catches the basketball when it is at a height of 1.2 meters. And so for part C, we need to find the value of t when this player catches the basketball. Now, another pretty easy problem. We just need to really understand what is happening here. So the first question I will ask you is, they're giving me a height of 1.2 meters, correct? What are they asking for? They are asking for when this player catches the ball. So, two very important things to point out. They're asking when they catch the ball, and they're telling me that we have a height of 1.2. As I just mentioned a second ago, x is time, y is height. So basically, they're giving me a y of 1.2, and they're asking what is my x when y is 2. So when y equals 1.2, what is x? That's all they're asking for. It's not that hard. The thing is, it's kind of disguised because it's like, in terms of context, it's saying when the height is 1.2 meters, what is, when is the ball caught? And so this is a very tricky way that the IB tries to ask you, quite basically, when y equals 1.2, what is x? See? So if y equals 1.2, that means this whole thing is 1.2, and x is what you're trying to find. See? So this that I'm putting now in pink is what I need to solve. See? So not that complicated. I can start off by doing minus 1.2, minus 1.2. 0 equals negative 4.75 t squared plus 8.75 t plus 0.3. Now notice this procedure that's happening right here is actually the same procedure that I did for part B. Because notice, I equaled it to 0 for part B. And up here, I'm also equaling it to 0. And the only difference is that my C value, instead of being 1.5, is 0.3. But all I really need to do now is go back to y equals. I can probably just change this to 0.3. That'll work. And then graph it. See? So when does this happen? We'll find the 0, of course. So find the new 0, and in this context, it will be (1.875). 3 significant figures would be 1.88. So for part C, just following pretty much the same procedure, we ended up with, it will happen at 1.88 seconds. Okay? So that is one way to solve it. You sort of approach it by asking yourself this. See? And now that I think about it, there's one more way to approach it, which actually might be a little more exciting or maybe more intuitive. See? So I'm going to go ahead and put back the original sort of like equation. And for my, I'm going to add another line. So this other line that I'm adding, because it's going to be a y value, it's going to be for the height of 1.2. So basically, I'm having this equation here. And if I go ahead and put a y equals of 1.2, I just need to find this point right there. And so if I find this point right there, this intersection, okay, this will be when the player catches it. So notice that 1.2 is going to be the height, and that 1.875, which is rounds up to 1.88, is the moment it is caught. So that's two ways to solve it. The second way for me is actually a little more intuitive. So here I put 1.2 for the height of the player. Both lines are going to show up now. Same as decimals, both lines show up. And now I just need to find their intersect. So I can do second, trace, hit calc, go to intersect, pick your first curve. Usually it nails it right away, but just to check, there's my first curve, and the second curve is this red one, right? Guess is just for picking the intersect. This is my only one. Boom, there's the answer. I got the same 1.875. We rounded up to 1.88, okay? So, two ways to solve for part C. Whichever one is more intuitive for you, go for it. I think most people would appreciate this one more, but this other aspect has a very visually appealing approach. Whatever floats your boat, see? There's a lot of people out there. Everyone does whatever is best for them, right? And last but not least, we have the exciting question, part D. Write down two limitations of using h of t to model the height of the basketball. And so two limitations, notice 2 points. Now, although this might be case specific for the context, there is something I can mention here. First of all, this is a classic IB question. They love to ask questions about what are limitations of your model, right? What are things that your model would maybe not be good for or good at or etc. See? So on the one hand, what comes to mind is like maybe this model, I mean, notice it has a bunch of negative values down here. See, so you can say that maybe this model is good, but not always. Like, what if you have someone that's really strong? The ball would probably go a lot farther, right? And so there's all these different kind of limitations that can sort of come to mind. And I'd rather take this discussion to the answer key. Okay, it'll probably make a lot more sense if we approach it from the answer key. So in the answer key, notice, usually you just have to criticize your model as much as you can, right? So on the one hand, the model is not a physics model, it's a math model. See, if it were a physics model, it would have to take into consideration a bunch of stuff. So really, the cool thing about these exercises is that there's a lot you can sort of like, it's not that you invent it, but like you can go with your gut on this kind of stuff. See? So like you think about it, a basketball, you're trying to measure it. There could be wind, there could be rain, there could be this, there could be that. There's like a lot you can sort of say, so just go with it. The other good thing about this kind of context question is that it doesn't use anything from part A, B, or C. Nothing at all. Nada. You can go straight to part D. Why would you ever want to go straight to part D? If you're running low on time, if you want to get some free points, identify the questions that are context questions. Okay? Once you realize that part D is a context question, maybe if you're running low on time and you want some free points, just do part D. Don't do anything else, right? Or maybe you did part A, got stuck on part B, noticed that part D was a context question. You have 5 minutes left in your test. You're going to do part D, right? After all, these are all worth 2 points. Keep that in mind. Enough blah blah, back to the discussion. There's a lot of stuff you can say here. You can say it ignores wind resistance. It treats the ball as a point. It assumes that gravity is constant. Maybe there's like a little bit of height on the ground. Maybe there's not. I don't know. There's a lot of stuff. See? It assumes the ball continues to follow the trajectory even after hitting the ground. That's another good point. That's what I meant about there's a bunch of negative values here, right? Doesn't account for that. Like an actual model would probably have more bounces from the basketball, right? And the model ignores the bouncing ball, just as I said, back of the ball after hitting the ground. See? So, as long as you don't keep it as something generic, you're going to be okay, right? Don't say that there are assumptions being made. Mention one. Mention one, okay? Don't say that models are never accurate. Say why. Right? So mention something, the main idea I need you to get from this is that you need to be specific. As long as you're specific and you just kind of like say some stuff, you're gonna get the marks. See? Ladies and gentlemen, that was a quadratic problem. I like quadratic problems. They're exciting. There's usually only a couple of stuff they can say. Max or min, zeros, x or intercept, and y intercept. The thing is they disguise it through the context. So watch out for that. But keep in mind, there's not too much they can ask from you, and there's not too many tools here either. Okay? So as long as you have them clear, this is a sort of exercise that, yes, there's a couple procedures, yes, it's some writing, but it's solid points. So quadratic functions should be solid points for you. And there it is. I hope it helped. I'll see you around. And take it easy. Alright, you guys, so for number 11, it's a fairly simple sort of graphing problem. So we need to consider this equation right here, which does look a little bit nasty. The first thing that I will proceed to explain is that they tell us that x cannot equal, whoops, let me try that again. We all deserve a second chance. That x does not equal 0. Now, why would x not be able to equal 0? Take a closer look at what you have here. So, you have an equation that says f of x equals 3x squared minus 5 divided by x. And they tell us that x cannot equal 0. So, oftentimes, depending on how our equation is written, there are certain values that we can never take. For example, if I were to have something like f of x equals square root of x, okay, then I would also have to say that x has to be greater than or equal to 0. Because if you go to your graphing calculator and you try to do square roots of, I don't know, -4, you get a mistake. Actually, there are answers to this, but they aren't real answers. They are imaginary numbers. All right. And so if you were actually to graph this, for example, in decimals, what you're actually going to find is f of x equaling square root. Actually, can I do square root like this? F of x equals this. Notice you don't have any negative values, only positive ones. And so there's certain things you have to watch out for which help you define your domain or your range. All this is helping you is defining your domain. Domain, let's remember, are your possible x values. Okay, so here they are telling you that x cannot equal 0 because of something that's here. And the special thing here is not a square root like I showed you down there, but it is the fact that x is in a denominator. And so notice, x cannot equal 0 because if x were equal to 0, well, what would happen? You would have 3 times 0 squared, which is just going to go to 0, minus 5 divided by 0. And what is 5 divided by 0? Well, if you ever forget, check with your calculator. Your calculator explodes. You cannot divide by 0. This is what we call undefined. Okay? So x cannot equal 0 because in the denominator you have an x, and the thing on the bottom cannot equal 0, right? And so if the thing on the bottom cannot equal 0, then x cannot equal 0. See? So that's the first thing I'm going to mention. That's why that appears. See? And believe it or not, it's actually very relevant for part C, but we will talk about that in a second. See? So for now, that is the context. They give us a little bit of the domain, and they tell us that the graph of f, so basically just our equation, is graphed for our values between 0 and 5. Okay, so all of this clearly has already been graphed, but it hasn't been graphed yet on the left side, which is actually what they ask us to do. So for part AI, we need to sketch the graph for the negative values of x. Right now we have the sketch for the positive values of x. Now we need to sketch for the negative values of x. Okay? Now, there's a couple different things you can do here. See? Because you need to sketch for the negative values, technically you can go ahead and find out what is y when x is -1, when x is -2, when x is -3, when x is -4, and when x is -5. Like that can be good enough for sketching your graph. So basically you would find 5 different points and see what happens from there. Okay, now of course, let's think about the most efficient way to do this, and of course, we will be using the graphing calculator. So the two main approaches that I suggest is, well, first of all, yes or yes, use your graphing calculator, and for that, because we need to sketch it, you might as well graph it. Okay, so go to your y equals, and in your y equals, you're going to be plugging in this. Actually, sorry, you're going to be plugging in this as your y1. Okay, so if you go ahead and plug in that as your y1 up here, you end up with 3x squared minus this fraction. So for the fraction, to plug it in more easily, you can do alpha y equals and press the first one. Boom, you're putting in a fraction. Yeah, so you can go ahead and graph this, right? Now, the friendliest way to approach it is literally graphing and putting in the window. But before that, I'm going to show you finding these specific points, okay? So a quick way to solve this, you might already be thinking, is that you plug in one by one, right? Like technically you can do it like this. 3 times negative 1 squared minus 5, right? Divided by negative 1. And you can do this a bunch of times and change the negative 1 each time, right? And you're going to get the answer, like you're going to get there. But a slightly quicker way, okay, is once you have it on y equals, you can actually pop up a table. So instead of pressing graph, you put second graph to hit table. And from here, you can see, here are the values of x. So when x is 1, y is negative 2. Makes sense. When x is 1, when x is 1, y is negative 2. That would be like right there. See? Makes sense. When x is, for example, I don't know, 5, ¿cierto? Y is 74. Makes sense. When y is 5, y is around 74. Checks out, ¿cierto? So you can do the same for the negative values. You just got to scroll up. And from here, you can graph, right? It's in fractions, so you might have to simplify it or eyeball it a little bit. But eventually, you're going to find out. See, for example, if negative 1 is around 8, so negative 1 is around 8, that would be like here. And you also know that negative 2 is 29 divided by 2, so that's around 15. So negative 2 is around 15, that would be like there, ¿cierto? Negative 3 is 86 divided by 3, that would be like a little less than 30, so a little less than 30, maybe there. Negative 4 is 197 divided by 4, that's around 50, ¿cierto? So, around 50, I guess you could leave it like here. And then negative 5, okay, is 76. So negative 5 would be, boom, all the way up here, right? And you can already notice that there is sort of a curve happening here. Like it does seem to slow down a little bit there, ¿cierto? So on the one hand, you have that going on, right? So that it has some sort of curve. But the other thing, because you're sketching, and really this is probably the best way to approach it, I'm just showing you all the tools you can do, is literally just graph it. That it. Now the small issue that you're going to encounter is that if you literally just graph it, you do have to play around with your window. The challenge of graphing is that a lot of people have trouble with the window. See? Now how does the window work? The window, the main thing you need to be focusing on is x min, x max, and y min, y max. You should not be changing anything else because you don't have to change anything else. And so take a good look here. It's very apparent what I have to do. This is going to be your x min because it's your smallest x value. This is going to be your x max because it's your largest x value. This is going to be your y min because it's your smallest y value. And this is going to be your y max because it's your largest y value. So once you establish that, it's suddenly very easy. So y min is negative 5. Y max is going to be 5. Y min is going to be negative 60. And y max is going to be 80. So graphing from here, doop-de-doo, is suddenly a lot more simple. So clearly, the pink dots that I put here are like good enough, but I do need to acknowledge that it goes all the way up like that. See? If you want your window to be 100% accurate, notice that each of these squares, it's jumping by 1, right? And each of the squares on the y-axis is jumping by 20. So if you want to make it like super duper mega accurate, you could change your YSCL to 20. The SCL is the scale, like each square is going to be 20, right? For the X, each square is going to be 1. So now you can graph, and now you end up with something literally like the diagram showing. See? So a lot of blah blah, a lot of window context. Point is, for you to get the full sketch points, you have to put a little bit of a curve, and then you have to make it go all the way up like that very violently. Okay? So a lot of blah blah, but I do want you to have all the tools available. So one of the tools is clearly making a small table, finding each of the values, ¿cierto? Using the table function. But the more friendly one, to my knowledge, is simply just graphing, acknowledging what is x min, x max, y min, y max. And if you want, you can change the SCL. It wasn't completely necessary. Really, for sketching, especially an exercise like this, you need to nail like the general form. So the one point is definitely going to be landing the curve. And the other point is going to be landing that here it goes straight up. Straight up near x equals 0. See, so near x equals 0, it goes straight up. You got to acknowledge that, right? So on the one hand, it's the curve. On the other hand, it's just straight up. So if you actually look at the mark scheme, you find something very similar to that. It says on the one hand, you get a point for the correct shape. The curve must be smooth. Asymptotic behavior, which is it going all the way straight up. And generally, you just get points for like nailing the dimensions of it. See, so nailing that the minimum is somewhere near there, that the highest point is somewhere near here. I mean, all that kind of stuff, you can do it if you eyeball it correctly. See? So sketching is easy points. You just have to make sure you replicate correctly how it should look like. See? You have the graphing calculator at hand, so do not hesitate to use it. Okay? I think the friendliest approach is literally just changing the window and graphing. But it will show you all the tools because you never know. Yeah? So that's for part AI. For part A, double I, we need to write down the x-coordinate of the local minimum point. So clearly, you need to find the point that's somewhere down here as the minimum. Okay? Back to the graphing calculator. From here, now that I have it all nice and graphed, there is a minimum function you can use. Okay? And you will be calculating the minimum, which is why you need to press second and then trace in order to hit calc. Here are all the functions you need to use. Finding zeros, finding minimums, finding intersects. In this case, we will use minimum, of course. So what does it ask for? Notice, it asks for a left bound, and later on it asks for a right bound. And I'll explain this in a second. So if my left bound goes from here to here, for example, all it's going to do, notice the dotted lines that it's putting up there. See? Not all calculators show the dotted lines, but all calculators are doing the dotted lines behind the scenes. So basically, you're asking the calculator, within this area, within these two bounds, give me the minimum. And the last thing you have to do is press guess. And this is only if within those two bounds, you have more than one minimum. Your calculator doesn't need help guessing, let's be honest. But the guess function helps you choose a minimum in case you had more than one. In this case, there's only one, so you press anywhere near, boom, there's the minimum. Okay, so the x-coordinate of the local minimum for part A, double A, you have to specify that your y1 was this guy here, so your y1 is 3x squared. And this is just for the procedure point, just in case. So your y1 is this, then you did calc min, and you ended up with negative 0.941. Three significant figures, I can leave it like that. Actually, I'll show you how I do that in a second. So this is the x value, and then this is the y value, 7.9699. If you want to do significant figures, you have to count 1, 2, 3. Do you round it up or keep it the same? You keep it the same. So you can leave it, your final answer, as negative 0.941, comma, you count 1, 2, 3, round it up or keep it the same. You round it up, comma, 7.97. Okay, so the x-coordinate for the local minimum point, so x-coordinate min point is negative 0.941. And just so that you all trust me, it's showing right there. Okay, yeah. So that is for part A double A. Then for part B, we need to use the graphing display calculator to find the solutions to the equation f of x equals 20. Now, this is extremely easy, but it's probably hard to interpret, okay? It's probably hard to understand what it's actually asking for. So, first things first. Guys, at some point, probably between middle school and high school, you started realizing that this inside is your x, okay? And this whole thing, f of x, is your y. That's all that's happening, see? Why is it useful to write it like this? Because then you can end up with tables like this one, which is basically asking, this one up here is saying, when x is -1, what is y? That is why it's useful to write it in these sort of parentheses. Okay, when x is -1, what is y going to be? So basically here, what it's telling you is that it's putting in a y equals 20. I need to find the solutions to the equation of y equals 20. The other way that you can think about it, because I think visually it's extremely appealing what I'm about to do, technically you can draw a line at y equals 20. How would a line at y equals 20 mean? Well, in Desmos, if you go ahead and put y equals 20, what do you end up with? Well, think about it. You end up with a line that goes horizontally through 20. Now you might be thinking, why is it horizontal if we're talking about at a y value? Because your x value changes, but your y value doesn't. Notice, I always have a 20 here. The 20 is not changing. So for drawing a horizontal line, you have to leave a y value that is fixed. That's why it's y equals 20. And for drawing a vertical line, you do x equals, I don't know, 3. And so here you have a y value that changes, an x value that doesn't. So I hope you learned something new. Anyways, so back here, if you think about the solutions to y equals 20, you're putting a line that goes like this. Just like that. See? And so what are the solutions here? Well, the solutions here would be wherever my function, which is the line that I'm putting in red, the curved line here, and this line here, it's wherever the purple meets the red. And so your solutions are how many, you guys? Are 3. You have this solution, and this solution, okay? And there's a couple ways to find it. On the one hand, you can do an extremely hardcore math way, which is saying, okay, I need to have that f of x equals 20, and I also know that my function is f of x equals 3x squared minus 5 over x. So technically, you can combine these and say 3x squared minus 5 over x equals 20, and try to solve x from here, and eventually you're going to find that you have 3 different x values, and through that you will be solving the solutions. Figuring out the solutions. So that's one way you can do this, okay? Now that sounds like a headache, let's be honest. Solving this looks insane. But what you can do is notice, here they are equaling each other. But really these are 2 lines, right? The horizontal line and your function. And so wherever they're equal to each other is where they intersect. Bada bim, bada boom, that is our procedure now. So you go back here and you say, okay, this is going to be y1, this is going to be y2. And so you go back to your y equals, you put y2 as 20, you graph it, and it's the same thing that I drew up here, but the color is a little bit different. Whoops. And you can go second, trace to hit calc. Now you're calculating intersects. And now is when the guess function makes a lot more sense. So the first curve is the blue one, makes sense. All around it, it's the blue one, ¿cierto? And the second curve has to be the one that's red, okay? As long as you press left to right, you're gonna be fine. The only mistake that can happen here is you press up or down. If you press up or down, you do jump from one function to the other. So just focus on that, press left to right. So the first curve is the one in blue, the second curve is the one in red. And with the guess function, now again, your calculator is not dumb. It knows all the intersects. It knows the 3 intersects. But what it does need to know is, okay, which one do you want? So we're going to start with the one on the left. So guess around near it. And there you have it. So the first intersect, we're going to write it as, well, I'll leave it in light green. So the first one is at negative 2.45. Okay? I'm leaving it in significant figures, you guys. Okay, you can leave the whole answer, it doesn't matter, it's still gonna work. Yeah. For the next intersect, again, you gotta go second trace, go to intersect. Same idea. First curve, make sure you're clicking the first curve, the blue one. Second curve, make sure you're clicking the red one. Again, you gotta guess for the one you want. It's around here. There's my intersect. So your second answer is going to be negative 2.52, negative 0.252. All right, and this last one over here, running a little bit out of space, but I think you guys can figure it out. So here's my first x, here's my second x, here's my third x, my third solution. So that for the last time, I go to intersect. First curve sounds fine, second curve sounds fine. And for the guess, I'm gonna go all the way to the right. Go ahead and press enter. There it is. So for this last one, in significant figures, it would be the 9 is going to turn, well, you're going to round it up, so you actually end up with 2.70. Awesome. So 2.70 will be the last solution. So using the graphing display calculator, finding the solutions, it's 3 solutions because it touches 3 times. Using calc intersect, you found all 3. You go over here, and there they are. Negative 245, negative 252, and last but not least, 270. All right. How do you show your work? Well, actually here there aren't any method points. Okay. I'm kind of surprised there aren't any method points. It's kind of weird. But just if you're a little bit nervous and want to show your method points, this right here is good enough. You're showing that you're putting into your calculator as y1 as y2, and that you're doing calc intersect. Write that down somewhere. Make sure you get those points, okay? That is for part B. And then part C is very easy, and you can actually do it skipping part A and skipping part B. Part C, you need to write down the equation of the vertical asymptote for the graph of f. Now, first things first, what the heck is an asymptote? Guys, an asymptote is a number, okay, that your function gets very close to, but it never touches. Keep in mind that you have 2 types of asymptotes. You have vertical asymptotes and horizontal asymptotes. Okay, so for example, yeah, you have vertical asymptotes and horizontal asymptote. In this case, you have a vertical asymptote which actually runs, or goes through. Let me raise a little bit of this because there's a lot of stuff written on here, see? But keep in mind, so an asymptote is a value or number that your function never reaches. And that can be for x or it can be for y. That is why we talk about horizontal asymptotes and also vertical asymptotes. So in this case, you have a vertical asymptote that goes like this. Wabow. This is a value that your equation will never touch. Visually, it makes sense, and there's one other very strong argument. Okay, so guys, first things first, this is a vertical line. And what did we say about vertical lines? For putting vertical lines, you need to leave an x value that is set. See? Because again, you have all these different y values, but the x value stays the same. And so in this context, the equation of your vertical asymptote is x equals 0. But wait, you saw that before, right? Earlier we said, and this is very interesting, earlier we said that the domain was that x could not equal 0. And so because x cannot equal 0, the vertical asymptote, its equation, is at x equals 0. And so because x can never equal 0, your vertical asymptote is at x equals 0. And I know that's a little bit weird, so let me talk a little bit more about it. Let's remember, I said an asymptote is a number that your function gets very close to, but it never touches. And so because x up here cannot equal 0 because it's on the fraction, on the denominator, ¿cierto? That means that if I were to say All right, because x does not equal 0, that means at x equals 0, I have an asymptote. Because the asymptote is the number that you get very close to, but you will never ever touch. Okay? So fairly simple. The equation of the vertical asymptote is at x equals 0. See? A very common mistake is that people say, okay, the equation is that x does not equal 0 because I associate it to asymptote, so I'm good to go. Nuh-uh. It's not exactly like that. Because x cannot equal 0, your vertical asymptote is x equals 0. If I were to be very rigorous with this, it's basically because this is your domain, then your vertical asymptote has to be this. Right? That's the way you think about it. This is your domain, and because of that, your vertical asymptote has to be that. Okay? Ladies and gentlemen, part C, just so you know, you can solve it without doing part A or part B. Once you get familiar with domain and how all this stuff works, you can actually get this point very quickly in less than a minute. I mean, you can look at it and immediately say, boom, that has to be a vertical asymptote. Okay, so keep in mind, that's the sort of stuff that gets you that gets you points, especially when you're low on time. Okay, be on the lookout for these type of exercises. For part C, you do not need part B or part A. Okay, so keep that in mind. Even if you suck at sketching, you can do part B without part A. Okay, you just pop it into a calculator and work from there. You don't need part A for part B. You don't need part A or part B for part C. So be on the lookout for those kind of details. They will give you points, especially when you're low on time and you need to be ultra mega efficient. Keep in mind, just whatever helps you, whatever floats your boat. I hope it helped. And that's number 11. I'll see you around. All right, you guys, for number 12, we have that in a game. Balls are thrown to hit a target. The random variable x is the number of times the target is hit in, important, 5 attempts. The probability distribution for x is shown in the following table. So, let's understand this a little bit more. Up top, you have x, right? And so x, they told us, is the number of times the target is hit. So, number of hits. Well, down here, when they put the big P, parentheses, big X equals little x and all that stuff, all it's really telling you is the probability of that. And when I say that, I mean this. If the number of hits are 0, the probability of landing it 0 times is 15%. If the number of hits is 1, the probability of that is 20% with the 0.2. So notice how this is hitting the target 5 times. That is why the different scenarios is hitting it 0 times, once, twice, thrice, 4 times, or 5 times. Okay, that is why you have 0, 1, 2, 3, 4, 5 up top, and the probabilities of that are on the bottom. Just to further finish explaining what's going on here, the probability that you landed 5 times, so 5 out of 5 basically, is 25%. The probability that you land 4 out of 5 is 2k. The probability that you land 3 out of 5 is 0.16%. Okay? So that is what's happening. And for part A, all you need to do is find the value of k. So how the heck do you find the value of k from here? There's only one key piece of information you need to have in mind for this part. Okay? And that's the following. In probability, all your scenarios must add up to 1. And this, once you understand this thoroughly, you're going to be able to solve any probability problem. Well, almost any, okay? What do I mean by all my scenarios must add up to 1? When I say all your scenarios, by your scenarios, really, I mean all your probabilities. Probabilities must add up to 1. All right? This is the thing. You have 6 scenarios here for landing it. In this case, right? You're trying to hit a target 5 times. You have 6 scenarios. You either land 0 times, 1 time, 2 times, 3 times, 4 times, 5 times. There is nothing more, nothing less. You can't land it -1 times. You can't land it 6 times. It's only 0, 1, 2, 3, 4, or 5. and respectively, the probabilities have to add up to 1. Because there isn't a 6 here, and because there isn't a -1 or anything crazy like that, then you need to be able to cover all scenarios, so you have to cover all probabilities. In other words, all I'm really telling you is that over here, this has to equal 1. So for part A, it's a quite simple sort of line of math. All you need to do is add all the probabilities. So 0.15 plus 0.2 plus k, so that's these three right there, plus 0.16 plus 2k plus 0.25, which is these other three. So all of these probabilities added together, as I say here, in probability, all your probabilities must add up to 1, all your scenarios must add up to 1, have to equal 1. Now some of you might be thinking, why the heck does it equal to 1? Well, that's the thing. Here you have a whole number, here you have a decimal, but this could also be percents. So notice 0.15 as a percent is 15%. 0.2 as a percent is 20%. And so if suddenly you look at these as percents and not decimals, what you're actually doing is adding 15% plus 20% plus some k percent plus 16% plus some 2k percent plus 25% has to equal 100%. And that's the main idea I was trying to tell you earlier. This 1 is the same as saying 100%. Okay, so keep that in mind. It equals to 1 because it equals 100%. So all your probabilities added together, all your scenarios added together have to equal 100%. You have to be consistent in that sense. So whether you think about it in terms of percents or you think about it in terms of decimals, you have to acknowledge it has to equal to 1 or it has to equal to 100%. Got it? So enough blah blah. For part A, well, you can pretty much just use your calculator here. And so on my calculator, I will be adding up all of these guys. See? So all of those guys ends up giving me we have 0.15 plus 0.2 plus 0.16, and on the other side we have 0.25. So those are the random decimals I have lying around, and I can also add up this k with this 2k, right, which is just going to be 3k. So for part A, what I end up with, all right, at the end of the day, is 3k plus what I got from my calculator, 0.76, has to equal 1, the 100%. And so to get 3k from here, you can do minus 0.76 onto both sides. So 3k has to equal 0.24 divided by 3 divided by 3. K has to equal, I think it's 8. It's 8, yes. So k has to equal 8, all right? So the main idea here that you have to embark upon is that in probability, your probability has to add up to 1, has to equal 1, because you acknowledge all scenarios. So if you acknowledge all scenarios, it has to be one of them, right? So if it has to be one of them, it has to equal 1. All right, there's a couple ways to explain that. That's what I chose to do for today. That is for part A. Then they tell us that the player has a chance to win money based on how many times they hit the target. Okay. The gain for the player in money is shown on the following table, where negative gain means that the player loses money. So if a player, for example, lands 0 hits, they lose $4. If they land 2 hits, they lose $1. If they land 4 hits, they earn $1. And if they land 5 hits, they earn $4. And so for part B, we actually need to determine whether this game, and this is a huge buzzword, we need to determine if the game is fair. Now, what do you think makes a game fair? A game is fair if your earnings equal your losses. For example, in a casino, contrary to what some millennial memes talk about, you always lose when you gamble, okay? I mean, in theory at least, you always lose when you gamble because the casino has a little bit of an edge. Okay, the casino usually wins at least by a little bit. Okay, but if the casino were made in a way that all its earnings, in probability at least, equal its losses, it would have to be fair. So how can I calculate the earnings and losses on all that stuff? Well, here, the idea we need to talk about now is an expected value. That's the main thing you should maybe be Googling or thinking about right now. The expected value of something, which is in your formula booklet, by the way. All right. Your expected value has to do with, if you run the numbers, what should come out. See? So think about it this way. The probability of landing 0, right? And really focus on this part. This is the biggest part. ¿Vale? The probability of landing 0 is 15%. And if you land 0, which has a 15% chance, you have to pay $4. So you can also think about it this way. The probability that you pay $4 is 15%. The probability that you pay $3 is 20%. The probability that you earn $4 is 0.25%. I mean, it's 25%. So that is what you have to do. So for the expected value, all you really have to do is take those two tables and have them interact with each other. So, as I said, the probability that you lose $4, so -4, and now it's going to be for expected value, yeah? So expected value is going to be the probability of paying on $4 is 15%. Plus, the probability of paying $3 is 20%. Probability of paying $3 is 20%. Plus, the probability of paying $1, right, is k%. And k we said was 8. So the probability of paying, was it $2? Sorry, the probability of paying $1, ¿vale? So this one right here is k%, k is 8. So -1 times 8. Plus the probability of the probability of paying 0, so basically nothing happens, is 16%. So 0 times 16, 0.16 I mean, plus the probability of earning 1 is 2k, which is 16%. So probability of earning 1 is going to be 16%, so 0.16, plus the last parentheses, which is the probability of earning 4 is 25%. So earning 4 times 25. Got it? So if you put all of this into your calculator, you will end up with, give me a second, why is it not working? Yeah, there it is. So on the one hand we have, and just so we show you once again, ¿cierto? So paying $4, right, this -4 here, the probability of that is 0.15. Plus paying -$3, so losing 3, right? The probability of that is 0.20. Plus probability of losing $1 is k. K was 8, so 0.08. Actually 0.08. I might have written that wrong down here. This is supposed to be times 0.08. K is 8, so that's 8%, right? 8% is going to be 0.08. Small detail, I missed it down here. Anyways, coming back up there, we keep adding onto the parentheses, so now we're onto this one, right? So probability of paying nothing, so just 0, is times 0.16 plus the probability of earning $1 is 2k, which is 0.16, right? Plus the probability of earning 4, so that's this 4 here, is going to be 25%. And here's the thing. Within this chain of math that I just did, earlier I told you earnings have to equal losses. Now if earnings equal losses, that means that this that I'm putting in red, which are my losses, has to equal my earnings, which are in green. Well, technically not that one, only these two, these earnings. So if these are equal to each other, then the game is fair. But notice, the losses have negative values and the earnings have positive values. So the other way you can think about it, and it's probably more friendly, is that it's fair if the expected value equals 0. So if this cancels out with this, then the game is fair. If it doesn't, well, then it's not fair. See? So let's go ahead and press enter over here, see what we get. Negative 0.12. So what this is telling you is that the expected value that we just calculated gave me negative 0.12. So the other way you can think about it is that when you play this game, if you play it a bunch of times, on average, you are losing $0.12. I mean, you're losing 12 cents. The bigger point here, though, is that your expected value did not equal 0, so then it's not fair. So this down here is not fair. This up here is fair. If it equals 0, it's fair. If it does not equal 0, it's not fair. That it? So that is a way in which you can justify your answer. It's very important. This is worth 3 points. So on the one hand, we probably had some sort of procedure method by plugging this in. And on the other hand, you have your justification or your argument, which is what I'm putting right there. If it equals 0, it's fair. If it doesn't equal 0, it's not fair. If we go ahead and check the answer key, so this is for number 12, you can see there's my value for k, right? The 8, the 0.08, right? Because within this context, yes, I left it as 8, but technically it's 8%, 0.08, ¿cierto? Or actually, correcting myself, good thing I checked, when you take this 0.24 and divide it by 3, it does give you 0.08. My bad, I was thinking 24 divided by 3. Dale? I'm going to leave it in the video because everyone makes mistakes sometimes. I still wrote 8%, so I probably would have gotten the right points or answer anyways. But small detail, I was thinking out loud as 24 divided by 3 when it's 0.24 divided by 3. All the more of an argument to always check with your calculator. See? So k is 0.08. And the procedure for the expected value is right there. So because it does not equal 0, the game is not fair. See, so that is one of your reasoning points. The other one is the answer, which is reaching the negative 0.12. And the other point is using the right method, which is the expected value method. Okay? Ladies and gentlemen, a fairly easy problem. All you really need to do is understand the big buzzword of fair. Whenever you run into fair, you need to be thinking expected value, and specifically that when it equals 0, it is fair, and when it does not equal 0, it is not fair. Okay, those are the things you need to keep in mind. All right, acknowledge how to solve it, and also that in probability, it has to equal to 1. See, those are the two main things. Once you establish that and see how they connect with each other, it becomes much more easy. Ladies and gentlemen, enough talking by me. I hope it helped. That is for number 12. All right, you guys. So for number 13, I'm going to mention one thing right away. Number 13 is a trapezoidal rule problem plus integrals. All right, and I probably wrote trapezoidal wrong. Trapezoidal. Trapezoidal. Okay. So this is a trapezoidal rule plus integrals problem, and so just a quick heads up, I'm gonna have a lot of context at the beginning. Like the first 5 or 7 minutes is probably just gonna be a bunch of blah blah, and only then will I jump to parts A, B, and C. So make sure you use the timestamps at the bottom if you already feel good about the trapezoidal rule. If you don't, the context is going to help you a lot. So enough talking, or get ready for some talking, better said. We have that. An engineer wants to calculate the cross-sectional area of a dam. The cross-section of the dam can be modeled by a curve and 2 straight lines as shown in the diagram. So the curve is this curve right here. And then the 2 straight lines, which is much more apparent, is this line and this line. All right. And important detail, but this is all in meters, so my answers will be in meters as well. The curve is modeled by function f of x. The following table gives value for f of x for the different values of x in the interval from 0 to 3. So basically, what we have in pink, okay, the line in pink is for this table here. Notice it goes up to 3, and so does the line in pink, all right? The curve in pink. So that's basically what's happening. These are just a bunch of different x and y values. For example, this is telling you the point 0, 3. This is telling you the point 0.5, 5.13. This is telling you the point 2, 19, which makes sense because at 2, it does look like I have a 2, 19, okay? So that's all that's really happening. It's a table with different x and y values. So for part A, we need to calculate an estimate, okay, calculate an estimate for the area in the interval from 0 to 3 using the trapezoidal rule with 3 equal intervals. So there's a lot going on here, and this is where the context I talk about will begin, okay? So the trapezoidal rule problem usually follows the same sort of like procedure or stuff you have to do, and let's first talk about it, see? So for some reason, an engineer decided to hire a high school student for calculating the cross-sectional area, okay? So the cross-sectional area, just take it as the area under these 3 lines, all right? That's why it's cross-sectional. It's kind of like, it's a couple different shapes, okay, whatever. So you cross-sectional area of the dam. Now, for calculating this area, the lines that are straight in green, it's a little bit more friendly because you can just make like, well, that would be like a rectangle, and this other one would pretty much be like a triangle, right? And so calculating the area of the guys in green, it's not that hard to do, right? I mean, it's pretty basic geometry. Here you would have a rectangle, and over here in dark green, we would have the area of a triangle. So you definitely have the formulas for that. Not that hard, but what we have in pink, you guys, what we have in pink, there isn't a name for this shape. There literally isn't. And so here the big issue is that there is a curve. And so how do you calculate the area under a curve? That's what it is. So for area under a curve, the main tools you have for estimating, so an approx, okay, is going to be the trapezoidal rule. And the exact, all right, is going to be with an integral. So that's the first thing I'm going to establish. The trapezoidal rule is only for a approximate, while the integral is for an exact value. See? So that is why for part A, it is literally asking for an estimate, because the trapezoidal rule is indeed an estimate. Yeah. Now the trapezoidal rule, well, what is that? Where do you find it, etc.? This is in your formula booklet. So I go straight to the formula booklet and I try to find it. So eventually, after searching for a while and trying to spell it correctly, you find it right here. See? Now, this equation, I will go piece by piece how it works, how to do it, etc. But the general overview that I need you to have for now is, first of all, here you have an integral. This symbol that I'm putting in red is the symbol for an approximate. And so the trapezoidal rule itself, which I'm now putting in light blue, is all of this guy here. So all of this guy is the trapezoidal rule, right? So notice, the trapezoidal rule, what it does is that it helps you make an approximate to what the integral would be. That is what I mean earlier by, the trapezoidal rule is an approximate, it's an estimate, while the integral is the exact value. Now you might be telling me, okay, why is this relevant? It's relevant because further down the line, and in a lot of these types of exercises, part A is for the estimate, and part C is for finding the actual area. So if you want to find the actual area, you're not using trapezoidal rule, you're using integrals. So that kind of language is important to keep in mind. Okay, that's why I'm going over that in the first place. Secondly, let's talk about the trapezoidal rule, what this formula has, what it doesn't, etc. See? Now, if you were to want to understand this, or if you want to write down like the cheat sheet or like the way to solve it immediately, and it will go piece by piece, but for now, this A is your smallest X value. This B is your biggest X value. And so B for biggest and A is the other one, so A is going to be for smallest. Okay? You can also think about it like B is up top, so it's bigger. A is on the bottom, so it's smaller. Okay, whatever. See? A is going to be your smallest X value, and B is going to be your biggest X value. Now you might be thinking, isn't that on the integral side? And I say, yes, it's on the integral side, but it's also what you need for finding H. And H is in the trapezoidal side, trapezoidal rule side of the formula, see? So anyways, for all this stuff that you eventually end up plugging in, let's understand piece by piece. A is the smallest X value. B is your biggest X value. Now, everything else is going to be Y values, see? So for example, this Y0 is your first Y value. This yn is going to be your last Y value, okay? And this that I'm putting now in orange, all these different Y values, okay? I know it looks kind of crazy, like Y1, Y2, Yn minus 1, like what is that? See? What I need you to understand is that within this parentheses, all that you're going to put, adding each other, so all that you're going to put is all the other Y values. Okay, this is a lot more friendly to understand than if I were to talk about Y1, Y2, Y3, and all that stuff. See, I'm going to talk about it anyways because, you know, I should so that you understand it. But understand this. See, for the trapezoidal rule, on the one hand, you first need to calculate H. See, H, you're going to need the smallest X value, which is going to be A, ¿cierto? And the biggest X value, which is going to be B. You also need N, okay? And N is actually going to be technically N, let's take it as amount of, how should we do it actually? Yeah, amount of points used minus 1. Okay, and I'll talk about that more later. For now, if you want to write down like immediately how to use it and solve it and etc., this is what you would write down. See? Now seeing it in action, you're going to understand how I get N, how I get Y0, how I get Yn, how you get B, how you get A, and all that stuff. See, but for now, I highly suggest you write down somewhere that this is the how the trapezoidal rule works. See? It's no use having the formula in front of you if you've never actually used it or don't know how it works. See? So on the one hand, you're calculating H, which uses the biggest and smallest X values alongside the amount of points used minus 1. And then you have two main parentheses. The first main parentheses, which I'm going to put now in whatever in red, so this parentheses is simply the first and the last Y value added together. And then the second parentheses is all the other Y values added together. All the other Y values added together. So let's go back to the exercise and try to identify some of this stuff. Again, the trapezoidal rule is not used for the entire figure. It's only used for the areas under a curve. And so we're going to be using it for this part in pink. For this part in pink, I have this table here, right? For these different X and Y values. Now careful. You're not going to be using all of these X and Y values because the exercise is specifically asking for you to use 3 equal intervals. Now, usually in my experience, you do use the whole table and forget about it and bada bim, bada boom. But if they want 3 equal intervals and this goes from 0 to 3, well, from 0 to 3, clearly you have 3 meters, right? And so if you were to divide these 3 meters into 3 equal intervals, you would have to go 1 meter at a time. All right, so the equal intervals, which I'm going to be putting now on your screen, go like this. This is your first interval. This is your second interval. And then this is your third interval. Okay? If you were to try to do it at a different amount of intervals, for example, increasing by 0.5 each time, this is one interval, this is another, and then this is your third. And so that would be 3 intervals, and you don't reach 3. You would have to add a bunch of more, and then you don't have 3 equal intervals, you have 6 equal intervals. See? So for the equal intervals, clearly you gotta go 1 whole meter at a time until reaching 3. And so if you go 1 whole meter at a time reaching 3, that means you're stopping at 1, stopping at 2, stopping at 3. So you don't care anymore about this point at 0.5, or the one at 1.5, or the one at 2.5. So now these are the values you're working with. Okay? Once you establish that, we go back to the formula booklet and we first need to realize, okay, what is the smallest x value? See, for A, what is the smallest x value? It's this guy here. So this will be A. So A equals 0. Which one is the, and let me put it in blue. See, so we just got the smallest x value. What is this biggest x value? So biggest x value is right here. So this is the biggest x value we said was B. B equals 3. So now we can check over there, right? What else do you need to identify? Well, you need to identify the first y value. So the first y value is going to be my first point. It's right here. So this is y0. y0 equals 3. Check, right? And then we also need to identify the last y value. And so the last the last y value, notice they call it yn. So my last y value is this guy here, and I'm going to say that this is yn, and that yn is going to equal 42. Now I'm going to make a quick disclaimer here because I think it's worth doing it right now. See? This is your last y value, right? And so if this is your last y value, then this is yn. Now notice, how many n's do you actually have? How many n's do you actually have? All right, so if this 42 is yn, then it's your last y. So that's your last sort of set of points that you're going to be using. But here's also an interesting observation, right? And this is also going to help you understand why you have y1, y2, y whatever over here. See? Technically, if this guy's y0 on 3, then the one right next to it is going to be y1. And then the one right next to it is going to be y2. And so then the one right next to it is not only yn, it's also y3. So, that's what's happening here. So the yn is signifying that's your last y value. But depending on the context, maybe you have 10 y's. Maybe you have 20 y's. Or maybe you only have 4 y's, and because you start counting from y0, then that means that your yn is y3. So that's also an interesting sort of observation. So your first y is at 0. And I know that seems very troll, but I'm just being honest. That's what the formula says. So get used to it. Your first y is at y0, okay? And so if your first y is at y0, and here technically I have 4 y's because we do have 4 sets of points, 1 set of points, 2 set of points, 3 set of points, and 4 set of points. If your first y is at y0, then your last y, in this case, is y3. So notice, 4 points means last y is at y3. So be very careful with that. See? I highly suggest you do the same that I did here. Go to your table, start counting from y0, figure out which y you reach, and whichever y you reach is going to be your yn. So yes, you have 4 points, but your yn is y3. And if yn is y3, then the obvious conclusion is that n has to equal 3. Okay? So yes, you can memorize, it's the amount of points you used minus 1, or you can go one by one, and by like intuition or just concluding, looking at the last one, like, oh, this is y0, this is y1, this is y2, this is y3, but it's also my last y. So if y3 has to be my last y, then clearly n equals 3. All right, that's what's happening here. Okay? So enough blah blah. Looks like we identified pretty much everything we need. See? So we talked about the first value of y. We talked about the last value of y. And if this is my first and this is my last, y0 and yn. So if this is my first and then this is my last, okay, notice I'm putting it in red. So for the first parentheses in red, that's my first, that's my last. For all the other y's, which is for the second parentheses in orange, it's going to be this y and this y. Okay? So now I can check over here as well. Vale? I already got the value for b, the value for a, and the value for n. So now we're good to go and plug in. See? So if I were to go ahead and plug in, well, first let me rewrite the equation over here because I do want to have it in hand. And so the equation is, for trapezoidal rule, 1/2 times h, big parentheses, y0 plus yn, plus 2 on the outside, times y1 plus y2 plus who knows what else, and then close parentheses. Remembering that h equals b minus a divided by n. Okay? So now I'm like more reaching like the heart of part A. See? So for part A, once we understand trapezoidal rule and you identify each one by one, okay, we can now safely say, and understanding the formula at a deeper level, you can have 1/2 times h, parentheses, first y plus last y, close parentheses, plus 2 times all other y's added together. And then close parentheses. See? Here's a bigger parentheses as well. Let's remember that for the first and last y, it's the ones I'm putting in red. And for all the other y's, it's the ones I'm putting in orange. Okay? So again, understanding the formula is probably the hardest part for this exercise, right? For h, it's going to be, well, b we said was 3, a we said was 0, n we said was 3. So h is actually just going to be 3 over 3, which is just going to be 1. Okay? So now I can plug into my calculator everything I have here. See? So I have to put 1/2. I'm going to use it as a fraction. So alpha y equals, and the first one, so 1/2 times h, which we just said was 1, times, and then here is the big parentheses. See? So first the parentheses in red, which we said was first y plus last y, which clearly has to be this 3 plus this 42, close parentheses, plus 2 times the parentheses is in orange, which is all the other y's added together. So it's going to be 8 plus 19. Make sure you close the parentheses as you should. And then that is for part A. See, so for part A, you plug into this equation here. Make sure you write it out to show the procedure of the trapezoidal rule. But you do end up with 99 divided by 2 meters, which if you don't like fractions, because let's be honest, almost nobody does, you can leave it as 49.5 meters. Okay, so that is for part A. Then they tell us that it is known that the derivative version, because notice it has a little bit of a thing there, the derivative version equals this in the domain from 0 to 3. So in the domain from 0 to 3, we're still simply under the curve, the curve that is pink. Yeah. And so for part B, you need to find an expression for f of x in the domain from 0 to 3 still under the curve. Now here's another big sort of concept I need to go over. It's the following. On the one hand, the three types of functions you're gonna like run into, okay? It's that you have the original one, the classic, right? It's just gonna be f of x. Then you have the derivative, which we just talked about, which is, it's like the classic, but it has a little bit of an apostrophe here. See? The same that is appearing right there. So that is for derivative, right? That literal apostrophe thing. And then the last thing you can encounter is the inverse. For the inverse, it's very similar to the original, just that it has a -1 up there. Okay? So these are the three things you can encounter. Now, a big brain play, okay, is the following. To go from the original to the derivative version, what do you have to do? Pretty obvious. You gotta do the derivative. However, ladies and gentlemen, and this is the thing you have to know for this exercise, to go from the derivative to the original, you gotta do the integral. And so, will you look at that? You can go from the original to the derivative, doing the derivative, and go from the derivative to the original, doing the integral. So for part B, they gave us the derivative version, which is 3x squared plus 4. And so if you apply the integral to this guy, you're going to end up with an OG. Yeah? So, an integral. I know that's probably spooky, and trust me, it sounds spooky, but it's not that terrible. See? So because we're talking about an integral, you're going to go to the formula booklet and ask for help. And eventually, you're going to find this guy here. See? The only integral you have to know is the integral of an exponent. Okay? Here they put it as x to the power of something. It's the same as the integral of an exponent. Okay? Now, if you follow this formula, you're going to be just fine. See? The other observation I can do is that this is basically like what you do with a derivative, but backwards. So if you want to think about it that way, you can. An integral is a derivative backwards. That's also why I drew this diagram here. So if you're really good at the derivative of an exponent, well, now just apply the same thing, but thinking backwards. What's the integral of it? Go from there. Yeah? So, clearly, all you really have to do is take whatever your variable is, ¿vale? And then the exponent, you're going to add 1 to it. And your exponent, right, is also going to go on the bottom. And you will be also adding a constant, which I'll talk about in a second. See? So let me actually go first over the constant, because that's probably the weirdest part. See, this is the constant. It's a classic. You pretty much have to include it for integrals. ¿Vale? Imagine a random example that I'm making up on this spot. Imagine you have the original function, x squared plus 2x plus 1. If you were to do the derivative of this guy, you end up with 2x plus 2. Why does this happen? Because the derivative, all it really does, notice the derivative, this n, right, goes in front, multiplying, and then you do -1 to it. And so here what happened was that this 2 went in front multiplying, so it was 2 times 1. Then we did -1, so you ended up with 1 up here. That's why you still have an x surviving. See? Then for this guy here, you have x to the power of 1, so it was 1 times 2. You end up with only the 2. Here, there's technically an x to the power of 0. Anything to the power of 0 is equal to 1, so you just leave it like that. And for this last one, technically there's an x to the power of 0, so 0 times 1 makes it go away. So notice, here we went from the OG to the derivative. And if I were to do the integral here, in order to reach the OG, well, what happens? If you were to do the integral of the derivative in this context, in an attempt to reach the OG, you're going to get really close. So on the one hand, following the formula, all you have to do is take the exponent you already have and add 1 to it, And your exponent will also go on the denominator. So from here, the 2 that I'm putting now in red, in red. So this 2 will remain unaffected. What will be affected, and this is the part of like the integral of the formula, see, is that this x will have 1 plus 1 up top, because it is to the power of 1. And then down here, you will have the exponent. So you're going to have 1 plus 1. See? Close parentheses, plus 2. And then here's the same idea. Here you have x to the power of 0. So technically from here, again, you put the 2 on the outside, so untouched. But you will put a big parentheses. Here's the part of the integral. You're going to do x to the power of 0 plus 1 divided by 0 plus 1. And from here, you also need to put plus c. Let me keep going. So if you keep going from here, you end up with 2 times x squared divided by 2 plus 2 times x to the power of 1 divided by 1, right? Now divided by 1 does nothing, so you're just going to erase that right here. 2 divided by 2, it's also going to go away. And then you have the plus c, which is mandatory because of the formula right there. So you have to include the constant. But notice, so you have f of x equals this whole guy. See? And so we used to have plus 1. And because this is the thing, because in the derivative, this 1 disappeared, then when you do the integral, you have to put plus c. You have to say, there's a constant there that could have been there, right? I don't know if it's plus 1, if it's plus 2, if it's plus 420, plus 100, like who knows? But you have to acknowledge when you did the integral from the derivative, there could be a constant that you're missing. So that is why you put plus c. It acknowledges the plus 1. Now technically from here, if I observe just from here, right? If this is the screenshot that I'm taking, you have no idea what that constant is. Because of context, you know that it's plus 1 because I made it up earlier. See? But technically, you have to find out what that constant is. Dale? So that was a quick 101 on how integrals work, especially from the derivative, which is exactly what we gotta do down here. So doing the integral from the derivative from here is the same idea. So you're gonna end up with the original function. This 3, again, you will not touch it. You will not touch the 3, but you will do the integral of the x squared. So the 3 remains outside, and here you follow the formula. So in the formula, you will be taking your exponent and doing plus 1. So you take the exponent, which is 2, so x squared plus 1, and then you divide by the exponent. Notice what I'm putting circled in green, or actually let's be very, very clear, what I'm putting circled in whatever, pink. See? So this is my exponent, which goes on the division denominator thing as well. See? So 2 plus 1, 2 plus 1. Close parentheses, plus this 4 will also remain untouched, right? Technically, right now, there is an x to the power of 0, ¿cierto? So that means I am doing big parentheses, x to the power of 0 plus 1 divided by 0 plus 1. All right? And follow the formula. There's a plus c. So here I put the plus c. You work this out a little bit more. You end up with f of x equals 3 x cubed divided by 3 plus, this is multiplying, plus 4 times simply x, right? Because this would be x to the power of 1 divided by 1. No need to put it. I can just leave it like this, plus c. And the last detail is that this 3 goes away with this 3, okay? So this is my original function. But notice for part B, you need to find an expression for f of x. And this is almost done, because you still have a c that's going around. So how do you solve for that c that's going around? Well, notice, right now you technically have 3 variables. So your 3 variables are x, both of these x's, the y, which is the entire f of x, and the c. And so the big trick, which you will pretty much always do, so just write it down somewhere, is that you're going to plug in a set of points. And if you plug in a set of points, you're going to figure out a value for x, you're going to figure out a value for y, and now you can solve for c. So just go with the flow for now. See, The big step I need you to acknowledge is that after the integral, you gotta plug in a set of points in order to figure out what c is. And so the set of points that I will be plugging in can be any of these four. And I'm gonna choose it to be the first one because, well, it looks like the friendliest one. See, 0, 3, why not? Yeah. So from here, I can just plug in the first one. I'm going to be plugging in 0, 3. So that means I end up with 3 equals 0 cubed plus 4 times 0 plus c. This goes away with this. This goes away with this. C has to equal 3. And so if c equals 3, your OG function now ends up a lot more pretty. And this is the final answer. See? So f of x has to equal x cubed plus 4x plus 3. Let me put it in blue so that we all agree that this is the final answer. There it is. A little bit of a lengthy process, but the cool thing about it is that it's always the same process. See? So very trainable, very attainable. Huh, that should be like a quote. If it's trainable, it's attainable. Dude, you guys got this. All right, that was for the doing an integral from the derivative to find the expression of the OG. See? So keep it in mind. If you have the derivative, do the integral, you end up with the OG. Yeah, the line that I'm doing in blue. All right, and last but not least, you need to do part C, which says find the actual area of the entire cross-section. And so the entire cross-section, what you will be adding is 3 shapes. So the first shape is this guy in pink, which I will be calling number 1. Then we have light green, which is this rectangle, right? And then we have the one in dark green, which is this third one, which is a triangle. Okay? So from here, find the exact area of each. Now, I did say way back in my day that the exact area will be used or will be done with an integral. And so right now, all you have to do is do the integral of the function of the first curve. And the function of the first curve found from part B is this guy here. Okay. So technically, I'll do it up here because I guess there's a little more space. So technically, what you have to do for this part, ¿cierto? Is that you need to add, let me make a little bit of space. From this part here, what you need to do is that you need to add the area under the curve, that's the thing in pink, plus the area of the rectangle, which is light green, plus the area of the triangle, which is in dark green. Okay, so if you add up these 3 exact areas, you're going to be good to go. Yeah, so let me make a little bit of a visual component. For the first one, it's a little bit of like the curve thing, right? For the second one, it's the rectangle. And for the third thing, it's the triangle at the end. Okay, so for the area, I'm going to put big A for area. See, so for the area of the curved part, we said that we need to use the integral. So here you do the integral, okay, of your function. So the area, your function we said was this guy here. So we're going to be doing the integral of this. And I'll show you how it works, don't worry. But for now, follow the idea. For the exact area, you got to do integral. So from here, you can do integral of your answer from part B, which is x cubed plus 4x plus 3. Let me double check just in case. Sounds good to me. See? Now, the other thing you have to do is that much how over here, right, for the trapezoidal rule, you talked about A and B. Okay, you also have to define that. See? So A is your smallest x, B is your biggest x. So A is 0, B is 3. That will apply over here as well. So this is going to be 0. This is going to be 3. This is your, what we call y, so your function. And here you put dx. So let me talk a little bit about what's happening here because I know it's kind of crazy. So on the one hand, what you're doing is, this is what you're going to be telling, like in math terms, this is what you're saying. Of this function, I need to do the integral in respects to x. That's why you're saying dx. And I need you to find the area of this function from 0 up until 3. That's what's happening. Let me go over it one more time because it's very important that you have it clear. So right here in math terms, you're saying of this function, I need to do the integral in respect to x. And I need you to do the integral from 0 up until 3. That's all that's happening here. So once we bring the math over to more intuitive terms, it makes a lot more sense. See? So this is going to be for the area in pink. Then we have to add the rectangle, which this is a little bit more friendly. See? So for the rectangle, you can observe, right, that it goes from 3 to 4, right? So over here, the dimension of the triangle is a distance of 1, right here. That is going to be a distance of 1. And then the height, well, notice this point here, right, is at 3,42. So over here, you have a height of 42. So that means my base of my triangle is 1, and the height of my triangle is 42. And for the area of a triangle, I actually don't know if of a rectangle. I don't know if we have the formula here. I mean, you should probably know it, but area of a parallelogram works. See, so base times height. Base is going to be 1, height is going to be 42. So for the area of the rectangle in green, we're going to be doing 1 times 42. This is for the area of the rectangle. And now for the last part, you need to do the area of the triangle. And so the triangle, well, area of triangle is right here. Base times height divided by 2. The base goes from 4 to 6, so that's going to be a base of 2. And then the height is once again going to be 42. And yeah, so base times height divided by 2. So it's going to be base times height divided by 2. So this is going to be the area of the triangle. See? So that's going to be the area of the triangle. Notice that I can do this because I can observe that this touches here on the 0, right? And I know that these are straight lines because the problem told me earlier, here you have 2 straight lines. See? So those are very important observations that we have to do. It allows me to talk about the problem like this. See? So all of this, you got to pop it into your calculator and you will solve it. See? Now the weirdest thing for you probably is popping this into your calculator. So let me help you piece by piece. Open up your graphing calculator and go to math, because this is a very mathy thing to do. Go to math, and here you have a bunch of mathy stuff. See, when you're doing crazy mathy stuff, you gotta press math. Yeah. On your first tab, on the math tab, eventually you're gonna find fn int, and what this is saying is the function of the integral, or something like that. See, like function integral, I don't know, whatever. You press here, and look at that. It's everything you need. So you're gonna be putting 0 up until 3, so that it's following the procedure from earlier. This is your function, or your y, ¿cierto? That's going to be your entire expression. So x cubed plus 4x plus 3. And all of this will be done in respects to x. See? Just so you trust me, I can technically press enter, and that's going to be the exact value of my integral. See? Now, just to be a little more fancy, you can do it all in one line. So that's going to be your integral. Then you can add on to it the rectangle that's in green, so 1 times 42, plus the rectangle, plus the triangle, sorry, which is going to be 2 times 42 divided by 2. So I can do it all together in one line. I end up with 131.25. If you want to go piece by piece, you can go piece by piece. I went ahead and got fancy and did it all in one go. Either works. So the area, the exact value of the area has to be 131.25 meters. And since they're asking for exact area, I'm going to leave it with the decimals and everything. See? So that would be for part C. Let's check our answers just in case. But it looks pretty good to me. So on the one hand, here's the 49.5 from the trapezoidal rule. Notice that you have to first put the equation of the trapezoidal rule. You have to be showing as a method point that you're trying the trapezoidal rule. See? Then recognition of needing to integrate. That is why the context is so important of understanding that, yo, if you have the derivative version, do the integral for the original. See, that is a very important piece of information for these exercises. And they always, from what I've seen, they always want you to figure out what C is. See, so again, for finding C, maybe write this somewhere. See, for finding C, plug in a set of points. So plug in an x comma y. If you plug in an x comma y, you're going to find the value of C 100% of the time. ¿Vale? And then for part C, well, there's a couple different methods, but the main one, the friendliest one, in my opinion, is understanding what I said earlier, which is, yo, this is the first part, this the curvy part. This is going to be the rectangle, and this is going to be the triangle. See? For me, that is the most friendly way to approach it. And you end up with 131.25. Do not forget your units. I put meters, but this is for area. So this is actually meters squared. So we all make mistakes. I just did one. No one's human. Don't be so hard on yourself. That is how you solve number 13. It's pretty crazy. But in my opinion, once you understand how the trapezoidal rule works and the integrals, everything becomes much more friendly. Do not fall into the trap that, oh, I have my formula booklet, so why do I need to, learn the formulas like to the dot? And you have to learn them to the dot, because what use is having these formulas if you don't understand how they work? I mean, I'm sure a lot of you, maybe they read trapezoidal rule in this exercise, that went to the formula booklet, you looked at it and you said, I have no idea what's going on. Starting off with the fact that the first y value is y0. Why is it y0? What is yn? What is going on? Like, that's the kind of stuff you have to know. See, there's no use in having the formula if you have no idea how it works. So I hope this video helped a little bit with that. That is for number 13, and I hope it helped. I'll see you around.